4 options and we must choose the most correct option. Now we have 3 forces that are acting, okay, on an object as shown, so that the resultant force is what? 0. So each of the following vector diagrams is correct representation. So if I'm to look at this with the format of the vector diagrams, which is the head to tail, A cannot be, C cannot be. But when I look at D and B, there could be something there. An example, if this one starts from here and goes up, this one goes down, this could be the resultant. Okay, so if this one, then that. So I'm gonna take B to be my correct answer for this case, okay? I'm taking B to be my answer. Please, you help us in the comment section if you differ with what we are choosing, okay? 1.2, we have 2 large objects, P and R, each with mass M, and placed between the centers R meters apart. They exert a gravitational force, which is M. So we know that the formula for the gravitational force is G, mass 1, mass 2, over R squared. But then they're telling us that the mass of the second one is being increased by 2, or is increased to 2M, okay? So you're gonna have a 2M, which is like a times 2 there. And then the distance is now increased to 2R, okay? So meaning that we're gonna have G, M, and M. Let me call this M1, M2, but it is 2 times. Over, now when I get the 2R and I square it, I'll get 4R squared. When I simplify this, we're gonna get a half. So that's gonna be a half G, M1, M2 over R squared, of which this represents our force. So my option will be for that case. Then 1.3, the velocity versus time graph sketched below for the motion of a ball that's projected vertically upwards, top of a building. Okay, so it was thrown upwards, okay, with a certain velocity. It comes, it reaches the maximum height above the ground, and then it hits the ground and then bounces off and then reaches the maximum height again, another height. So we know that S is always smaller than Q, okay? Because at this point, the velocities are 0, which means those are like maximum points. It's more like bouncing because of the amount of energy. The energy at Q is greater than the energy at S. So the ball reaches highest height above the ground at a certain time. Which point of the graph corresponds that? So I'm going with Q, okay? That's 1.3. And then 2 hard objects collide inelastically in an isolated system. Which of the following sets of statements will be correct? So both total momentum and kinetic is conserved. No, we know that momentum will always be conserved regardless. No? But when it comes to the kinetic energy, for as long as it is inelastic, kinetic energy will not be conserved. So neither total, this is wrong. Total momentum is not conserved, that's wrong. So option D is the best. So the total momentum is conserved, but the total kinetic energy is not. Then 1.5, we have an engine P, which has a greater maximum power output than engine Q. Which of the following is correct when P and Q operate at their maximum output? Now, the fact that P is having a greater maximum power, it simply means that it can finish the work within the shortest time possible, for as long as the work to be done is basically the same, okay? So if the work done is not the same, which means that P can do greater work compared to Q if the time varies. Okay, so they're telling us Q does more work than P in the same time. Q has a smaller output, so it cannot be. Then we're saying that P and Q do the same amount of work at the same time. This is wrong. P and Q do not do the same work, but Q does it in a short, no, it cannot be a shorter time for Q. It's a shorter time for P. P and Q do the same amount of work, which is correct, but P does it in a shorter time. Option D is the best. 1.6, we have the absorption spectra of the same elements surrounding both star A and star B as observed from the Earth. The spectral lines from star B are more redshifted than those of star A. So how do the frequencies compare? So with 1.6, I'll go with C, because the frequencies observed from B will be lower because the wavelength is higher. And then the speed is going to be greater. Okay, then 1.7, telling us R and S are two small charged spheres. Okay, we don't know what's happening here. So when I look at R, okay, because they gave us the net electric fields. This is R, and then this is the electric field due to R. Since the direction is in that sort, which means there's a repulsion. And we know that P is a positive point charge. Okay, so if that's a positive, this one must also be a positive. And then when I look at S and that, it's moving this direction. So meaning that S must also be moving that direction, which is attraction, okay? So that is gonna be a negative. Okay. So if S is a negative and R is a positive, which option do we have in that case? So it's saying R is positive, S is negative. So option A is what I'm going with. Then 1.8, the circuit below was used in a practical investigation. There's an EMF and internal resistance. We must ignore the connecting wires, okay? So we have graphs K and L below as obtained. So we have an adjustable resistor, which we know I call a rheostat. So we're saying that voltage against current, we have graph K, which obeys Ohm's law. And then this one does not obey Ohm's law. Now, the fact that this is a standard graph, okay? And we know that with the rheostat, what happens with the resistor, with the resistance, is not constant, it keeps on changing. Eh? So meaning that the voltage V2 should give us, or should represent the Ohm's law. And then the voltage V1 must be represented by the graph L. That's my understanding of this. So V1 is L, and then V2 is K. So K is V2, and then V1. So I'll go with C. I don't know what the masses have to say about that. 1.9, which one of the following is the function of the split ring commutator in an electric motor? So mainly it's to change the direction, okay, of the current. So ensures that the current, the external circuit changes direction. So option D would be the best then. And then 1.10, which one of the following statements correctly describes the photoelectric effect? So with this, I'm choosing option C, that an electron will absorb the energy of a photon and is ejected from the metal surface, okay, if the energy is indeed sufficient. Okay, so that is to do with question number 1. Question number 2. There's a crate of mass 25 kilograms that slides down a rough inclined plane, okay, at a constant speed of 2 meters per second towards point A. Okay, there's a force F that acts on it parallel to the incline as shown. There's a constant kinetic force, 40 newtons, and the incline is 30 degrees. Now they want us to state Newton's first law in motion, of motion in words. So this law simply tells us it's also the same as the law of what? Inertia. So what does the law of inertia state? That a body remains at rest. It's fine, let me write it this side. So this is 2.1. 2.1, they're telling us that a body remains at rest. Okay, a body remains at rest or constant motion or speed in a straight line, unless acted upon by a resultant force, call it the resultant force, or we can call it an external force. So unless we have something extra that is acting on it, we expect the body to continue moving in the same direction or resting the way it is, okay? Then at 2.2, they want us to draw the free body diagram showing all the forces acting on the crate as it moves towards B. So what we can see is that there is this force F that is acting in that direction, okay? But since the crate is moving downwards towards A, we're gonna have the friction force. The frictional force is also gonna act in that direction. I'll say F friction. We call it Fk. Yeah, let me call it Fk. And then now we're gonna have the weight downwards, and then we're gonna have the normal force upwards. We can have the Fg parallel here if we wish, but we already have enough forces for what they wanted. So 1, 2, 3, and 4 is enough for the 4 marks. Then 2.3, they want us to calculate the magnitude of F, which is the applied force for 3 marks. So you can use Newton's second law, whereby we know that the F net should give us the MA. Now down the incline, we know that we have the Fg parallel. We say the frictional force is gonna be acting upwards. So if I get my Fg parallel plus the Fk plus the F applied must give me the mass and then the acceleration. So my Fg parallel is mg, the sine of theta. My Fk was a 40, I will say negative 40. The F is acting in the opposite direction, which will also be a negative F, will be equivalent to 0 because the body is moving at a constant speed, which means there is 0 acceleration. Let me substitute the mass is 25 times 9,8 multiplied by the sine of 30. Now I'm subtracting 40. I should move the force applied that side. When I punch this into the machine, which is the calculator, okay, I'm ending up with a nice answer of 82.5 newtons. Okay, so this is our applied force as required by the question. Please just confirm with that. If I'm having the same, so we're saying sine of 30, and then we subtract a 40, 82.5. Perfect. Then we move on to the next question. And then they're telling us that when the crate reaches point A, it starts to act up, okay? The force F is removed, and then the angle of inclination decreases immediately to a certain angle, which is theta, so that the crate continues moving at the same speed. So we're maintaining the speed of 2 meters per second, but with a difference within the angle and then within the forces that are there. Now, for us to answer this, because now we're seeing this kind of scenario, then they're asking us to use the relationship between the forces that are acting on the crate between point A and point B to show that the mu k, okay, the correlation coefficient, the coefficient of friction is given as this, okay? Now, if the force F is removed, which means we are only left with the frictional force and the Fg parallel that will be acting downwards. So that's what I'm going to use here and say that we can still say that F net is equal to 0 because it's still moving at the same speed, and then Fg parallel is going to be mg, sine of theta is equivalent to, we know that frictional force is given as the mu k multiplied by the normal force. Let me just start by that, Fn. Then this is mg sine of theta. We know that it's going to be the mu k over the normal force, but normal force is given as the mg cos of theta. So I'll say over mg cos of theta. So the mg and the mg will cancel out, meaning that the mu k will be the sine of theta over the cos of theta. Okay. Then 2.5, they want us to get the, no, they're telling us that the coefficient of kinetic friction between the crate and the plane is 0.19. They want us to use this identity from trig. Oh Lord, why must maths always haunt us? Okay, let's use this identity, okay, to calculate the frictional force as the crate moves from point A up to point B. Now, one thing we need to know is that we know that sine of theta over cos of theta must give us the tan of theta. But we said this is representing the correlation coefficient. So what is that going to be? I'm going to say, let me change this around. and say that the tan of theta is equivalent to 0.19. So let me get the theta, which is the shift tan of 0.19. Okay, so shift tan of 0.19, that gives me 10.76. Okay, degrees. So this is the new angle, okay, that we're dealing with. Now the question wants the frictional force. Then we shall go down and say that our frictional force, Fk, is given as the mu k multiplied by the Fn. That's gonna be the mu k, which is the 0.19 multiplied by the mg cos theta. I'm using this, but there is also another way to do that, okay? The mass is 25, and then the 9.8, then we're saying the cos of 10.76. When we punch this, yeah, I'm getting a 45.73 newtons. Alternatively, somebody would have used, there's another approach that one could have used. And that is to say that this Ft parallel is equal to this. Okay, and just say that the mass times the gravity multiplied by the sine of theta. So that's a 25 multiplied by 9.8, and then the sine of 10.76. Let me just confirm and see. So 25 times 9.8, and then the sine of 10.76. Perfect. I'm getting a 45.7. Oh, yeah, just the difference of a 0.01, which is not bad. Okay, so either way, you'll always get the same thing. Then question number 3, I'm telling us that there's a ball that is dropped from point A and reaches point B, which is h meters below A in time t. The ball takes a further 2 seconds to fall from B up to C. The distance between B and C is 8 h meters, 8 times the original height. We are ignoring friction as always. Then they want us to define what free fall is. So free fall is just a motion. Okay, it's a motion of an object. It's motion of an object that is under the influence, okay, under the influence of only the acceleration due to gravity, or it's just under the influence of the gravitational force. Okay, then 3.2 show by Newton's calculations that t is a 1 second. Perfect. I love such questions where they even give us answers. No? We can never go wrong there. Okay, so for us to show that, I'll have this as my displacement. Okay, so I'm going to use the second equation of motion, okay, which says delta y should be v initial multiplied by delta t plus a half g delta t squared. Okay, so h is going to be, our initial is 0 since the ball was just dropped. So it's going to be a half times 9.8 t squared. I'll call this equation 1. Okay. So if this was a t and this was a 2, okay, let me look at the, I don't know, should I look at the entire journey or just this other section of B? I can look at the B part, right? And say that still using the same formula, 8h is going to be still a half, but then that is going to be tricky for me. Let me use the total distance, which is going to be now 9h, because 1h and 8h is 9h. Then this is times 9.8 into a t plus 2, and then I square that. So where there is h, I'll replace with that. So this is equation 2. And then I'll say that I'm substituting 2 into, no, I'm substituting 1 into 2. Okay, so it's going to be 9 into a half times 9.8 t squared is equivalent to a half multiplied by 9.8 I'll have t plus 2 squared. So I'll have 9,8, half 9,8 dies out. I have 90 squared is equal to, that's going to be t squared plus 40 plus 4-ish. Now we have quadratics here. Okay, let's collect the like terms and let's create the standard equation. So that's going to be 8t squared minus 40 minus 4 is equal to 0. Divide through by 4. So t squared minus t. And then we have minus 1 is equal to 0. Then let's factor this out. Okay. So when we are factoring this out, we're going to have a 2t. And then we're going to have a t. This can be a minus 1. This is going to be a plus 1 is equal to 0. So the first bracket, t is negative a half. We can never have time as negative. And then t is a 1. So this is what the question wanted. So this is how I would have worked this out, okay? So if you have a better way, a quicker way, shorter way, please just help us, okay? Then 3.3. And they want us to use just the equations of motion only to calculate the speed with which the ball reached point C. So with this one, there's just a short and quicker way. Let's use the first equation of motion. V final is equal to V initial plus G delta T, since it's free fall, okay? Our initial is 0, meaning that V final is going to be 9,8 multiplied by the total time, because T is 1. So it's 1 plus 2, which is a 3. And then this becomes a 29, okay, 4 meters per second. That's what we do. This is the shortest, okay? The other alternative is by you going through the displacement approach and you use the Vf squared is equal to Vi squared plus 2G delta Y. Okay, you can also use this, but you'll have to find the total displacement first, okay? After getting your T as 1, you can go back and substitute and find the H and then, but this is a longer way, okay? Because that's what actually question 3.4 requires. That determine the height from which the ball was dropped, the total distance. So since we know that our H was given as what from one of the equations, we said a half times 9,8 t squared, okay? So a half times 9,8 t squared, meaning that's a half multiplied by, no, this is 4,9 t squared, where the t is 1, then the distance is going to be 4,9 meters. But this is just the height, h. Then the total height, okay? Total height is going to be 9 times, which is going to be 9 multiplied by 4,9. Okay, 9 times, we say 9 times 4,9, I'm getting, we said 4,9. I'm getting 44,1 meters, okay? Any alternative is also acceptable, okay? That is how I would have answered 3.4.1 for 2 marks. Then they want us to get the height. Is that the question? Okay, the height of the ball at B. Yes. Now at B, remember the total distance is 44,1. Okay. Now what is 44,1 minus 1h? Remember we say that 1h is what? Just 4,9. Okay, we are subtracting a 4,9. That gives me 39,2 meters. There we go. Okay. 3.5, they want us to sketch the graph. Okay, I'll just squeeze it here, guys. Yeah? Sketch a position versus time graph, motion where the ground is the 0 position. Okay, so that is the ground as our 0 position. Okay, this ball was projected up. What do they mean by that? So ground is the 0 position. If you go up, it's positive, which means the body moved in the negative direction forwards. Okay, so it's possible for us to have something like that, where this is going to be our 44,1, and then the object moves up to that point. So this is the C point. And then we can have our 39,2. The 39,2 comes after. Isn't that too far? Isn't that too far? Let's change it and say if this is 1, 2, and 3. So just this point here, which is the 39,2. And then this is gonna be the point B, which is 1 second, 2 seconds, and 3 seconds. So this is the time in seconds. This is gonna be the position in meters, or the Y in meters. Okay, we can have it like this, or somebody would have drawn it like this, and then you indicate this kind of thing. Okay? So that is your B, this is your A, and then that is your C. Okay, so something of that nature, this or that. Then question number 4. We have a trolley A of mass 1,5 is resting horizontally on a frictionless surface. The second trolley B of mass 2 kg travels horizontally at constant speed V and collides with A. Trolleys stick together and move at a constant velocity to the right. Okay, this one is resting, right? Right. Okay. There's a distance covered in 2 seconds. Okay, state the principle of conservation of linear momentum. So we know that in an isolated system, we're going to say question 4.1. Okay, in an isolated system, the total linear momentum is conserved. Okay, so that's what you have to say. In an isolated system, the linear momentum is conserved or remains constant. And then 4.2, what do they want? They want us to calculate the speed V with which B moves before the collision. So let me summarize this nicely, and we've seen that if we have A, we have B. What are the masses? We know that the mass of A is 1,5. The mass of B is 2. The velocity initial for A is 0 since it's resting. This one velocity initial is just a V. Okay, we know that the velocity final and the velocity final is just the same. Now, they want us to calculate the velocity V, this one. But we can get our velocity final first, because we know that the velocity final will be the displacement over the change in time, which was 0,8 over 2, meaning that our final velocity is 0,4 meters per second. Then we apply the conservation of momentum. We know that mass A, initial velocity of A, plus the mass of B, initial velocity of B, must give us the mass of A, the final velocity of A. Okay, since it is now one system, let me just combine everything at once and say plus mass of B into V final. Okay. Now, initially, this is going to be 1,5 multiplied by 0. This is 2 multiplied by V is equal to 1,5 plus 2 multiplied by 0,4. Going to have a 2V being equivalent. Okay. That's going to be 3,5 multiplied by 0,4. I'm getting a 1,4. And then V becomes 0,7 meters per second. Okay, so that is 4.2 that the question wanted. Then 4.3 is the collision elastic or inelastic. So without a doubt, this is, I did not say inelastic. I said inelastic. Okay, it's inelastic. Why? Remember, there is no energy within trolley A. Okay, but the energy of B initially and the energy of the combined system after cannot be the same. Energy is going to be lost, okay, in one way or the other, given the fact that the final velocities or the velocities are not maintained. This is a 0,7, which is higher. The final is 0,4, which is lower. So there was energy that was lost. So that is inelastic. We don't have to prove or give a reason. Then 4.4, they are telling us that during another collision, okay, so if there's another collision, trolley B exerts a greater force on trolley A. and the change in momentum just stays the same. Okay, how is the time for the collision affected? Choose increase or decrease. So in this case, I'm going to say decrease, or because the change in time is going to be shorter. And then they want us to write down a relevant equation to support the answer. So we know that force multiplied by delta t should give us the change in what? Momentum, the impulse. Then we're saying that delta t is the same as the change in momentum over the force. So remember, the change in momentum is the same for both, whether A to B or B to A. So if that is the same, if the force is greater, the time must be smaller, because time is inversely proportional to the force. Okay, so this decrease and then this formula is perfect enough. That is 4.4 and question 4 as a whole. Then question 5, there is water that is drawn from a water source that is 12.5 meters below the ground by an electric pump. The water is lifted vertically upwards at a constant speed as shown in the diagram. Okay. Then they want us to define the term non-conservative force. So we know that this is a force, okay, in which the work done by the force is dependent. Why can't I say the work done by the force depends on the path taken? Okay, on the path taken between the 2 points. Then they want us to draw a free body diagram showing all the forces acting on a fixed mass of water as it moves from the source to the ground. Okay, so if a fixed mass of water, let's say it's somewhere there, this water is gonna experience what we call the weight. Okay, is there any other force that is gonna act on this water? Not really. I don't think there's any other force unless if. But the other one that I could think of is the fact that the water is going upwards, there should be the force by the pump. Okay, force by the pump. So meaning that we're gonna have the force pressure by the pump, and then we're gonna have the weight downwards for 2 marks. It's reasonable. As much as we might have friction by the pipes and what, but that is usually because they told us to ignore the friction and capillary effects. So if there's no capillary effects, which means it's just the force by the pump and then the weight that's acting downwards. But since the pump is greater, then the water will go up. Then 5.3, because they told us that the pump lifts the water at this rate. The pump lifts 200 kilograms of water from the source to the ground at a constant speed. Calculate the work done by the pump. Okay, so we know that the work done is going to be the mass multiplied by the gravity multiplied by, so it's more like the gravitational pull, okay, which is going to be the mass, which is 200 multiplied by 9.8 times the 12.5. So this gives us 24,500 joules. Okay. Then they want the constant speed at which the water is lifted. Constant speed at which the water is lifted. Let me jot it this side. So it's the 5.3.2. So it's a tricky question. 5.3.2. So if we are lifting 200 kilograms at basically 2.5 kilograms every second. Okay, so this is 2.5 kilograms in 1 second. How about the 200 kilograms? How many seconds are we gonna need? So let's just divide this. So 200 over 2.5. This gives us let's just confirm that, please. Let's double check. Okay, so we're saying 200 divided by 2.5, which gives me 80 seconds. So it's gonna take 80 seconds to move 200 kilograms of water. Now, for me to get my velocity, okay, I'll get the displacement, okay, I'll say delta y over delta t. Now my delta y, the distance through which the water is going to move, is 12,5. The delta t is going to be 80 seconds. Then 12,5 divided by 80 gives me 0,156, which is approximately 0,16 meters per second. Okay, so that is the velocity that the question is asking for 3 marks. Then 5.3, they want the average power that is dissipated by the pump. So for average power, I can as well get the work done divided by the delta T. So the 24,500 divided by the delta T, which is 80. Wow, it was a tricky question, but I believe it was a doable work energy kind of question. So that is 306,25 watts for the power. Okay, so that is question number 5. Then question number 6 are telling us that there is a bat that emits sound waves with a frequency fs as it flies at a constant speed vv towards a vertical cliff. Okay. Then the waves reflect off the cliff with the same frequency that they strike the cliff, and with the wavelength of this much as shown the simplified word. So the bat is moving. The bat emits with the frequency as it flies at a constant speed. So if the speed of sound in air is that, okay, name and state the phenomenon. So that phenomenon is what we call a Doppler effect, okay? And then we just have to state Doppler effect because we know that this is the apparent change in the observed frequency, okay? And the reason as to why there is a change in the observed frequencies compared to the frequency of the source is as a result of the change within the velocities of the sound source as well as the listener, okay? Difference in the velocities of the listener and the sound source. So that statement of Doppler effect should be well stated. Then 6.2, they want us to show that the frequency or the frequency of the source is given as this. So what we need to do is that we need to start by finding the frequency of the listener. We know that V is equal to F lambda. So we know that that's going to be V over lambda. We know that our V is 340. And then our lambda that we're given was 0,016. If you divide that, that is number 1. Now, if this is true, we can go to the Doppler formula, okay, and substitute. Okay, so then I'll go back to the Doppler formula. Let's see, let me put it here and say that frequency of the listener should be equivalent to V. Okay, I'll say velocity of the listener over V. I'll say minus. This is going to be velocity of the source multiplied by the frequency of the source. Now, we know that the bat is the source in this case, and it's also going to be the listener. So let's take it to be moving in this case. So our FL that we got was 21250 is equivalent to 340 plus, if the listener is stationary, that's going to be a 0 over our 340 minus VB multiplied by the frequency of the source. Now remember, we're looking for the frequency of the source. Okay, then I'm just going to multiply through. So I have my 340 minus VB multiplied by 250 is equivalent to 340 Fs. So let's divide through by 340. I don't want to open those brackets. So 250 divided by 340 gives me 62.5. Okay, that's 62.5. we have 340 minus VB is equal to frequency of the source. Then when I open this up, meaning that this 340 cancels that, is going to give me 21250 minus 62.5 VB. So that's the frequency of the source that the question technically wanted. Okay. Then next, 6.3. They're telling us that the frequency of the reflected sound detected by the bat. Now, if it is detected by the bat is now the listener. Okay, which means the frequency of the listener is 850 higher plus the frequency of the sound waves emitted. Okay, so it's 850 plus the frequency of the source, which is going to be 850 plus this whole thing or this whole scenario. So what does that give us? Okay, let's go down again. We're still using Doppler, the formula for Doppler. So this is 6.3. Okay, 6.3. So we shall say that V plus VB over V minus VB must give us, I'm just gonna say frequency. Okay, I'll just put the simplified version of it that I'm having 1, okay, plus 850 over Fs, technically. Okay, so when I substitute, I have 340 plus VB over 340 minus VB, is equivalent to 1, plus the 850 over Fs. And then we know that our Fs was that 2, let me just replace it now, and say that 21250 minus VB. Okay, so what do we do next? Just have to simplify this. Okay, let me simplify. So 340 plus VB over 340 minus VB. Cross multiply, we're gonna have 21250 minus VB plus 850 divided by 21250 minus VB. Okay, I have a whole lot of VBs now. Yo. Okay, 340 plus VB is giving me, what's 21250 plus 850, that is 2200. Minus VB. This is gonna be 340 minus VB. And then this is what are we doing? Okay, that is fine. This is 21250 minus VB. We're multiplying it by that. Okay, so when I punch this into my calculators, it's huge. 21250 times 340 is giving me 7225000 plus 21250 VB minus 340 VB and then minus VB squared. I must do the same thing here. Okay. 340 times 100 is giving me 7514,000 minus VB squared plus 22100 times 340. We're done with that. We're looking at the VB now. It's going to be 22100 VB plus VB squared. Okay, so meaning that this is gonna, oh, it's not gonna cancel. Only one that is canceling is this one. Wait a minute. Why am I having? What am I doing? Hello. That is that. No, I think I'm messing up somewhere here. I'm doing a mess here. Okay, 340 on this, we get that. 340 on that, we have negative 340 VB. Okay, this and that is negative 2 to 100 VB plus that, okay? Then let's see. So this 340 is going to cancel with that 340. Then 21, that is going to be different. Let me move everything out to the left or to the right. So I'm going to have 2 VB squared. Okay. And when I move this on that side, it's going to be negative 2 to 100 minus 21 to 50. It's going to be minus 43350. Then when I subtract that, 7514. Okay. So is equal to that. So when I solve this, the end of the day, I'm getting my VB to be 6.8 meters per second. Guys, please help me with what you got in that kind of regard, okay? Then question number 7, they're telling us that a small negative charge Q placed at a fixed distance from charged sphere R experiences this kind of force as shown in the diagram. So if the force is moving towards Q, okay, meaning that there's some bit of attraction in this case, meaning that this must move. And since this is negative, then automatically this must be positive. They want us to draw the electric field around the positive. So something like that. Okay, field lines must be moving out. Then 7.2, there is sphere S that is attached to a ceiling, and we have all that information. State Coulomb's law. So Coulomb's law simply tells us that the electrostatic force, okay, between point charges is directly proportional to the product, okay, to the product of the charges, okay, and then inversely proportional to the square of the distance between them. That is what we have there, okay? Then 7.2.2, draw a free body that is looking at S, okay? So with S, we're gonna have one, the weight. We're gonna have the tension, and then we're gonna have the Coulomb's force there, the force that is as a result of R. All right, then they're telling us that sphere S is positive 6 nanocoulomb. That is R, and then S is 3 nanocoulomb, and then the mass is 0.15. Calculate the angle, theta. So for us to get the angle, okay, for us to get the angle, we need to know that this body, S, is going to experience this force. So let's first calculate the force, which means it's a K multiplied by Q1, Q2 over R squared. So 9 times 10 to the 9 multiplied by 6 times 10 to the negative 9 times 3 times 10 to the negative 9. I'm dividing this by 0.03 squared. This is giving me an answer of 0.00018. Okay, so that is more like the force that we're having. Okay, then if I'm to break this down, we know that there's going to be a component here. If this is a theta, meaning that that must also be a theta. So this is going to be a T cos of theta. And then this is going to be the weight. So we know that T cos theta is equal to the weight. And then meaning that T is going to be the weight over the cos theta, which weight is like, we had 0.15. We change this to kilograms, you divide by 1,000. Okay, let's see. 0.15 divided by 1,000, we're getting 0.00015 times 9.8 over cos theta. This is my T. Then I know that this force here will be having the component, the horizontal component here, which is the T sine of theta. Okay, so T sine of theta, I'll equate it to my weight there, which is 0.00018. Then where there is T, I can replace it with this whole thing. Meaning that I'm gonna have a 0.00015 multiplied by 9.8, okay, over cos of theta. I'm multiplying by the sine of theta, should give me 0.00018. You can use your simplified decimals or exponents, and then you're good to go. Then I'm gonna divide this thing on this other side, okay? And we see what we end up with. So we know that sine over cos, that's going to give us the tan of theta. 0.00018 divided by 0.12315 times 9.8. Let me put this in brackets, nice. Okay, so if I put in the brackets, I'm getting 0.12245. Okay, then the shift tan of this is giving me 6, okay, I'm saying shift tan of the answer, I'm getting 6.98, which is approximately like 7 degrees. Okay, so that is your theta that they need. Then question 8, they're telling us that in a circuit diagram below, the battery has an EMF of 24, the internal resistance is that, and we have all those resistors. Can we state Ohm's law in words? So we know that the current, okay, through a conductor, current through a conductor is directly proportional to the potential distance, or some people call it the voltage across, okay, across a conductor at a constant temperature. Then when both switches are closed, they want us to get the current through L. Where is L? This is L. But then they're telling us that the reading here is 0.8. So if we have this current, we have this resistance, we can get the voltage here. Okay, so I'm gonna say that the voltage is gonna be 0.8 multiplied by 13 from our Ohm's law. So this gives me a 10.4 volts. Now we know that since this resistor, this and this, they are all in parallel, the voltage is going to be the same. So the voltage or the current, from this formula, we know that current will be voltage over the resistance, meaning that 10.4 divided by 9.5 must give me 1.09 amps. They want the reading of A2, so A2 is like the total current through the circuit. So I have the current here as 1.09. I have the current as 0.8. I need to find the current here. Okay, so still the voltage is the same even for the 9. So I'm gonna say that voltage in the 9 is gonna be, no, I'm not saying the voltage, I'm saying the current in the 9. Okay, current is in 9 is gonna be 10.4 over the resistance, which is 9, and that gives me 1.16 amps, meaning that the total current that we're gonna have should be 1.16 plus 1.09 plus the 0.8, and this must give us at 3,05 amps. And then they want us to get the total resistance R. Now, since these three are in parallel, I need to find the effective resistance of this parallel combination. Okay. So I'll say that the parallel, R of the parallel is going to be 1 over R1 plus 1 over R2 plus 1 over R3. It's going to be 1 over 9,5, 1 over 13 plus 1 over 9. Okay, so when I flip it around and find my R of parallel, this is going to give me 3,4 amps. Okay, if that is true, then I can use the EMF formula and say that my EMF is current into the R external plus the internal resistance. Now this R parallel will be in series with the R of interest. So this is going to be a 24 is equal to 3,05 into R plus the 3,41, now plus my internal resistance, which is 0,3. I'll start by dividing both sides by 3,05. So 24 divided by 3,05, that's going to give me a 7,869. I'm subtracting 3,41, I'm subtracting 0,3 to get my R, meaning that my R is 4,16 ohms. This is what I'm getting. Please, you can tell us what you got there. Then they're telling us that switch S2 is now opened, okay? So if S2 is opened, meaning that the current will just bypass L and then just complete the circuit. So this 13 and the 9 is out. Now, if that happens, how this affect the reading of the A2? So how does the current go via that? So we know that initially when the two switches are closed, our effective resistance is going to be 7, something, because we have this 4,16. Now we're creating it, so we have 7,8 as our total resistance there. Now, when we remove those two, the resistance is going to increase, okay? When the resistance increases, the current must decrease. So we're going to say it's going to, how will this affect the reading? Okay. So he's saying the reading is going to decrease. The reading, the current reading in the ammeter is going to decrease. Okay, that it decreases. The reason, because of the increase in the resistor, in the resistance. Then how will the brightness be affected? We must choose increase, decrease. So now when the resistance is decreasing the resistance, how is that so? Because now look, let's look at this. If we are having just these two, this and that, we're going to have a total of 13, something, meaning that the resistance increased. If the resistance increased, the current must decrease. And how does this affect the brightness? The brightness will definitely decrease. Reason, we know that power is directly proportional to the current, okay? We can see that power increases, power decreases, okay? The power decreases. As the power decreases, there will be less current, okay? And then the brightness will also be less. Then we have letters A to F. So they want us to look at S1 being opened and S2 is closed. So this one is open, this one is closed. So the circuit is not complete. So, okay. So if it's not complete, which quantities will be equal to 0? That is the current, which is C. Okay, then question number 9, they're telling us we have an AC generator. Which polarity? So using the right-hand rule, the polarity of A is basically the north. State one way in which the induced EMF of this generator can be increased. You basically need to increase, okay, the number of turns of the coil, okay? You need to increase the magnetic strength. Okay, you need to use a stronger magnet. That's what we mean. You must increase the speed of rotation and so on and so forth. Then they want us to sketch the graph. So the graph is going to be simply something like that. Okay, this is time in seconds, and then this is the induced EMF. Okay, then 9.2, we have an AC generator that produces maximum voltage. Okay, so Vmax is 340. We have the power of 1.2. Define the term root mean square. So we know that root mean square is basically the equivalent constant current, okay, that would offer the same power to a resistor as the actual one, okay? So we just need to write that definition. The 9.2, they want us to calculate the root mean square current that is passing through. So what I'm gonna do, I will use the P average being the V RMS multiplied by the I RMS. But will this make sense? Yes, we have the power, which is 1.2. For us to get the V RMS, we must get the V max, we divide it by the square root of 2. So this is 340 over the square root of 2 times the I RMS. When you do your magic and push everything that side, the I RMS that I'm ending up with is a 4,99 amps. Okay, 4,99 amps. Then they want us to get the resistance within the kettle. So you can say resistance is V squared over R, meaning that the R is gonna be V squared over the power. Now we know that our V squared, we're looking at the V RMS, okay, which is a 340 over square root of 2. This is squared. We're dividing it by 1.2, meaning that that resistance of ours is more like a 48,17 ohms. Okay, so that is what I would have done with question number 9. And then question number 10, they are telling us light of different frequencies is incident on a metal plane. The sketch below shows the relationship between the maximum kinetic energy of the photoelectrons and the energy that will be incident. Define the term work function. So work function is more like the minimum energy required. Okay, minimum energy required to remove an electron. To remove an electron from the metal surface. From the metal surface. Now they're asking us to write the numerical value of the gradient. So what's happening here with the gradient? The energy of the photons and the EK max. So EK max over the energy of the electrons. Which constant is that? It's the numerical value. Anybody to help us? What we have there? EK max, the constant is gonna be, I'll write the Planck's constant here. Okay, because that's more like the gradient that I can only think of whenever I have graphs of this. And we know that Planck's constant will be 6,63 times 10 to the negative 34 joules second. Then they want us to calculate the maximum speed of the photoelectrons when photons with energy Y, as shown, strike the metal plate. So we know that the energy, the EK max is 2,99. They want us to get what? The maximum speed. So let's just put it aside. That is 10.3.1. Okay, so 10.3.1, what I'll do is I know that my EK max is given as a half mv squared. That's 2,99 times 10 to the negative 19 is equal to a half. The mass of an electron is 9,11 times 10 to the negative 31 v squared. Do your magic. Okay, if I do my magic, I'm ending up with a v of 8,1 times 10 to the 5 meters per second. And then 10.3.2, they want us to get the value of y. So what is the energy of the photons? Now we know that this is the work function, okay? That is our W naught. the work function that we have. So the formula that combines work function and EK max, do we have anything like that? Yes. So we could use something like seeing a formula here that says that E is equivalent to W naught plus EK max, EK maximum kinetic energy. Now, the energy that we need is what we are calling the Y. I don't know why this question is from us, unless if I'm getting it wrong. Okay. Do we need the frequency? The frequency, that's going to take us some other time. Okay, so what I'm going to do, I'm just going to add the two, whatever the two values. So it's going to be 3,68 times 10 to the negative 19 plus my energy, my EK max is 2,99 times 10 to the negative 19. So 3,68 plus 2,99, that gives me 6,67 times 10 to the negative 19 joules. So that's what I'm getting them. Then 10.4, they're telling us we have photons of this much energy that are striking the metal plate, or the, okay. Then the number of these photons with this type of energy is increased, okay? How will the maximum kinetic energy be affected? So this is more like when you increase the number of electrons, you're basically increasing the intensity. So how does intensity affect the kinetic energy? So in this case, it's just gonna remain the same. Okay, so what is the explanation? We know that intensity, okay, does not increase. Okay, we can say that intensity, yes, it increases the number, okay, of electrons, but not the energy, not the energy. All right, guys, so that is that with the paper, and I can maybe see out of 100, it was something like 95% doable, okay? So guys, that's where we stop. I wish you all the best, and as you prepare for your paper too. Okay, let's meet then. Bye-bye for now. Hello, welcome to yet this episode where we shall be looking at the proposed memorandum for the Physical Sciences Paper 1, with 12 May, June 2025. Okay, so in this paper, we have 10 questions that we shall be looking at, and we shall be exploring, okay? So with question number 1, which is the multiple choice, they're telling us that we have 4 options and we must choose the most correct option. Now we have 3 forces that are acting, okay, on an object as shown, so that the resultant force is what? 0. So each of the following vector diagrams is correct representation. So we're going to start with section A, which is multiple choice. We have around about 10 questions, and each question carries 2 marks. Okay, so question number 1. They're telling us that there's a book that rests on a table. Which of the following forces will form an action-reaction pair? So an action-reaction pair is basically a pair of forces that must counteract each other. An example, if a book is resting on a table, we know that 1, there's going to be the weight of the book that will be acting on the table, and then the table in reaction to that must create a force that must act on the book, okay, from Newton's third law, whereby action and reaction must be equal but opposite. So when we look at the options, they're telling us the force of the earth on the book. That's not true. The force of the book on the earth, that is also not true. The force of the book on the table? No, the force of the table on the book. So the correct option there would be option D. So I'll take D for question 1.1. And then 1.2. Telling us a person is standing on the bathroom scale in a moving lift. Which of the following motions of the lift will result in the smallest reading? Okay, the lift, when the lift accelerates upwards, when the lift accelerates downwards, when the lift moves upwards at a constant velocity, or when the lift moves downwards at a constant velocity. So I'm going with option B. When the lift is moving downwards, that's when the reading will tend to be smaller. Okay, we can explain that if we have, let's say, a free body diagram of the weight that's acting downwards and then the normal reaction upwards. Now, if there is a lift now, and then there is also the weight of the lift, the fact that acceleration due to gravity will always act downwards, so the amount of force downwards will be less, so the reading will also tend to be smaller. Then 1.3, the velocity versus time sketch graph shows the motion of a ball which was in free fall. So for free fall, that is basically motion under the acceleration due to gravity only. So the ball struck the ground after 30 seconds. And then the question is, which of the following statements will be correct about the ball? Okay, so the ball was dropped from a height above the ground. A height above the ground. Okay, there's some bit of sense there. But when you say it was dropped above the ground, when we look at the graph, at a time t, the velocity is 0, which simply means that this ball moved up, reached its maximum, and then went back below the point of projection and so on and so forth. Okay, so this narrative of drop from a height, no, I'm refusing. It's not making sense. Not now. Then it was thrown vertically upwards from the ground. This is also not making sure, as much as the vertically upwards is correct. It was thrown vertically upwards from a height above the ground. Then it was thrown vertically upwards from a height, no, downwards from a height. So this is also out, because if it was thrown vertically downwards from a height, then we don't have a maximum height where the velocity is a 0. So this is out. The first one is out. We are left with just B and C. But now, since we are having issues with B, I'll choose option C to be the reasonable option there. Then 1.4, they're telling us the vector diagram below shows the initial momentum P1 and the final momentum P2, and then the change in momentum. So with vectors, we know that the length of the line will always represent the magnitude. Okay, so we know that this positive magnitude is bigger since the line is longer. And then if we look at P2, we're seeing also a slightly smaller momentum compared to P1. Then remember, for us to get the change in momentum, it will be the P2 minus the P1. And since the P2 is smaller than the P1, that's why the direction is in the opposite. So which of the following sketch graphs correctly shows the momentum of the car for the time the car moved on the road? So you can see that initially the momentum was higher, and then the momentum dropped. So which option is going to make sense? Option B is out, because it's showing us that the momentum was lower than increased. When we look at option C, it was higher and then dropped into the negatives. Okay, and then it was lower and then increased. So D and B are out. Our problem now will be C and then A. So when I look at A, I think it would make the best option compared to C. Momentum just decreased because it shows the momentum of the car as it moved on the road. That's fine. Then 1.5, a stone of mass M dropped from a height h above the ground. Ignore the effects of air friction. Which of the following combinations correctly represents the kinetic energy? 1, and then 2, the total mechanical energy of the stone at the instant the stone has fallen through a distance of a quarter height. Okay, so what we can see is that if we have probably a building or a height h here, and then we are being told that the stone has fallen up to a certain height, which is a quarter h. We know that at the top of this height, the stone is going to have the maximum potential gravitational energy, and then 0 EK. And then at the height of a quarter h, the stone is going to have what we call mechanical energy, which is a combination of both the EK and the EP. Okay? But from the law of conservation of energy, we know that energy can neither be created nor lost. So the EP max at this height should be equal to the mechanical energy at this point. So let's get our EP max at a point h. Okay, know that EP is mass, gravitation, and the height. So you're gonna keep it this way since we don't have any values. Then at a point, a quarter h, our EP is going to be a quarter h multiplied by the mass multiplied by the gravitation. So which means it's a quarter mgh. This is our EP. Now for us to get the EK, we just need to subtract this from this. So that is 1 mgh minus a quarter mgh, which gives us 3/4 mgh. So this is going to be my EK. Okay, let's read the question again. Stone of mass is dropped from a height of the ground. Ignore the effects. Which of the following combinations correctly represents the kinetic energy and the total of the stone at the instant has fallen through this? So we're not using the ground as a reference, we're just using the point of projection as a reference. So our mgh, or our EP, so EP is going to be a quarter mgh, and then the EK must be 3/4. So a quarter mgh, we said, so kinetic energy, we said is 3/4. So which options are 3/4? We have A, and then we have C. Then they are also asking for the total mechanical energy. We say total must be equivalent to EP max. So I'll go for option C. Option C. That is showing us the kinetic energy and the total mechanical energy. Okay, so C is the correct option for 1.5. And then 1.6, they're telling us a spectrum of helium emitted from a star moving away from the Earth is compared to the spectrum of helium that is found on Earth. Which of the following statements is correct? The observed line spectrum from the moving star will have blah, blah, blah. So the star is moving away. So for as long as it is moving away, number one, what we need to remember is that the wavelength is increasing, okay? And then for as long as the lambda increases, okay, the frequency must decrease from V or from C is equal to F lambda. We know that if I make F the subject, it will be C over lambda, which means the two are inversely proportional. So what I'm going to say is that the frequency is lower, the wavelength is longer. 1.6, I'll go with option A. Okay, so A is my option. Then we move on to 1.7, talking about the magnitudes of electric fields generated by different point charges and measured at fixed point. For each measurement, the distance between the fixed point and the charges are the same. Okay, which of the following shows the correct representation for the relationship between the magnitude of electric field and then the charge? So from the formula of electric field, we know that it is F over Q. Then when you replace this F, Coulomb's law of electrostatics, Q1 over Q2 over R squared, and then you're dividing it by Q. So this Q cancels that Q, so which means you're just left with KQ over R squared. So you can just get this from the formula page straight away. Okay, so we can see that the electric field is directly proportional to the magnitude of the charge. Okay, so option A will be perfect. So as the Q increases, so will the electric field. All right, then 1.8, the diagram below represents a circuit in which all the external resistors have the same value. Okay, let me take this to be 2 ohms. Everywhere, 2 ohms, 2 ohms, 2 ohms. Then the question is asking, write or which one of the ammeters in the circuit will have the lowest reading. It's in capital letters. So we have an ammeter here, this A, will give us the reading of the current within the circuit. Okay, so we expect this current to be bigger than this and that. Same applies with A4. So A1 and A4 are going to have the same readings since they are just connected to the circuit outside. They are not affected by these resistors. But we know that this resistor here and this one, they are in series, okay? But then these two form a parallel combination with this resistor by A2. So if I combine these two, it's going to be like 4 ohms, which means the resistance here is going to be bigger compared to the resistance here. So which means there's going to be less current that is flowing via this route. So the reading of the ammeter with the smallest value will be the A3. So I'll take C to be my option. Okay. And then 1.9, the following diagram is an electrical machine which is shown below. Okay, what type of machine is this? So before we draw the conclusion, we need to see which features are surrounding this machine. Number one, we have a source of energy, which is maybe a battery or something. So this is a DC source. So for as long as there is a DC source, it cannot be a generator. So C is out, D is out. Now, by virtue of the rings are split. Okay, so for as long as the rings are split, then this becomes a motor. So this is going to be a DC motor. Okay, so splitting the rings becomes a DC motor. Okay, so option A is 1.9, and then 1.10, which of the following combinations is correct for a line absorption spectrum in terms of the energy transitions of the atoms and the appearance of the narrow lines? Okay, so we know that whenever there is an absorption spectrum, like for as long as the particles or the electrons gain energy, they'll move from lower energy levels to higher energy levels. Okay, so option A is out, that is moving from lower, that is when they lose. That will be like emission. So this one is also out. So I'm going to focus on B and C, where there is lower to higher. Okay, and then what is the appearance of the narrow lines within that? Are they going to be colored or are they going to be dark lines? Correct option is C. They are going to be dark lines. Okay, they can be of different sizes, but they will be dark lines. So that is how question 1 would be answered. All right, so we move on to question number 2. Okay, so question number 2, they are telling us that block A of mass 4.1 is connected to block of mass 0.3 kilogram by an inextensible string passing over a frictionless pulley. Block A is at rest on a rough horizontal table and block B hangs vertically as shown in the diagram. So we have a frictional force. Okay, so frictional force is 49 newtons, and then it is applied to block A at an angle of 50 degrees to the horizontal. Okay. Okay, and this causes the block A to accelerate to the left. Okay, so which means everything is moving to the left. And then they also gave us the coefficient of kinetic friction to the surface to be 0.35. Okay, so with all these details, we just need to, okay, so which means the entire system is moving in that direction. Okay, then 2.1, they're asking us to state Newton's law, second law in words. Okay, so what we know about Newton's second law in words is that when a net force, let me just try to write it here. Okay, so we're saying when a net force acts on an object, the object will accelerate. Okay, object will accelerate in the direction of the force. Will accelerate in the direction of the force, and the acceleration is directly proportional to the force and inversely proportional to the mass of the object. Okay, so that would be your 2.1. And then 2.2, they want us to draw a free body diagram that is showing all the forces that are acting on A as it accelerates to the left. So looking at A, we can see that there is going to be normal force, there's going to be weight that is acting downwards, and then there's going to be this applied force. Remember, the surface is also rough, so there's going to be frictional force acting in that direction, but there's also this tension force. Okay, so since we're having 5 marks, we should expect something like 5 forces. So 1, 2, 3, 4, then 5. So I'll just try to draw that free body this side. So that is my body. We say there's tension, and then there is frictional force, and then there is the normal force, then we have the weight, and then we're going to have our force applied somewhere there. So this becomes our free body for this particular diagram, for that particular question. And then we move on. So this is 2.2. All right, 2.2. Then we move on to 2.3. 2.3 is asking us to calculate the magnitude of the frictional force that is exerted on block A. Magnitude of the frictional force that is exerted on block A. Okay, so when we look at the body A itself, okay, we can see that this applied force is at an angle, so it has the components. Okay, so if I'm to break this down, Okay, I'm gonna have this and then that, okay, into two components. So this is going to be the F, the sine of 50, and then it's gonna be the applied force, the cos of 50. Okay, then I know that the upward motion weight is equal to the normal force plus the F sine of 50. You know the F is 49, okay? But now we want the normal reaction. Normal reaction is going to be the weight minus the F sine of 50. Okay, so we need to highlight this first. Then we know that the frictional force is given as mu multiplied by the normal reaction. Okay, so I'm going to jot it this side and say that my F is mu times the normal reaction, but we say that N is the same as weight, okay, minus the F sine of 50. Do the substitution, that's going to be 0.35 because we were given the mu, the coefficient of friction is 0.35, okay, into our normal reaction, which is given as that. So the weight is going to be mass times 9.8 because we know that weight is given as mg. What is the mass of the body? Is 4.1. Okay, so that's going to be 4.1 times 9.8 minus 49, the sine of 50. Okay, so when I punch this into my calculator, times 9.8 minus 49 sine of 50. What do you get? So I end up with 0.925. Let me just round it up to 2 decimals. So 0.93 newtons as my frictional force. Then 2.3.2, they want us to get the acceleration of block 8 by applying Newton's second law on each of the bodies or the blocks separately. Okay, so if I'm to look at that, we know that Newton's second law is going to be F net is equal to ma. What is the question asking for? The acceleration, which is the a. Okay, so for as long as the body is moving, then we're going to apply the F cos and then the F. Okay, so let's start by looking at body A with the motion. Okay, body A is going to have F cos of 50. It's going to have the tension and then the frictional force in that direction. Okay, this is A. When we look at body B, it's just the tension and then the weight. Okay, so those are the only forces that will be acting the two bodies respectively. So I can start by looking at body B. Okay, and say that when I look at body B, since it's moving to the left, which means the tension is going to be greater. Let me start by writing the formula that F net is equal to ma. Okay, just to get the mark for that formula. And then if we do the substitution, it's going to be tension is going to be equal to, no, I'll set tension minus the weight should give us the ma. Our tension we don't know, but then the weight is going to be 2.3 times 9.8. Okay, 2.3 multiplied by 9.8 should give us 2.38. I can move all of this to that other side. So I'll get 2.3 times 9.8, which becomes 22.54. So I'll have 2.38 minus 22.54. I'll call this my equation number 1. Then I'll look at body A. Still apply the same thing. F net is equal to ma. So remember we said it's going to be the F cos of 50 minus, I don't want to bring in the cos 180s and so. So let me just say minus, since I know that the tension and the friction are just in the opposite directions. Okay, so minus the frictional force, okay, minus the tension, must give me the mass and that. When I do my substitution, okay, this was a 49 cos of 50 minus the frictional force, we got 0.93 minus tension. Okay, we say tension is that. That's fine, let me just do that. Is equal to the mass, we said it's 4.1. Good. That's gonna be 4.18. Let me make T the subject so that I can equate both equations. Alright, so when I simplify these two, I have 49 cos of 50. I'm subtracting 0.93. That gives me 30,567 minus T should give us 4.18. I'll move the T that side, I'll move this on this side. So 30,567 minus 4.18 should give us a T. Then I'll call this equation 2 and equate both equations. So 2,3a minus 22,54 should give us 30,567 minus 4,1a. I'll collect the like terms. I'll move the 4,1 this side. I'll move the 22 this side. So 2,3 plus 4,1, that gives me 6,48. I move this side, it's going to be a plus, so 30,567 plus 22,54. I'm getting 53,107. Then I'll divide both sides by 6,4. Does that make sense? Did I do anything wrong? Anything wrong? Anything wrong? That makes sense for me. It's not going to make sense for me. Let me just go back and revisit this thing. Let me see. You said 31. 5. Why am I having 30.5? 49 cos of 50. Yeah, my numbers are not correct. Let's start with 2,3 times 9,8. Okay, so this is fine. Let's come here. We say we are saying did I do anything wrong? Anything that's not making sense? Did I leave out any force? Let me just go back to my free body diagram and see. Remember, we said we have this, which is applied tension, and then there is also friction. Okay, so I think this is meant to be a plus as our equation number 1. So I'm going to put a plus there, because when you transpose this negative to that side, becomes a positive. So the rest is fine. So we're going to subtract that. We're going to have a 30,567 minus 22,54. Let's not divide yet. Okay, so it will be 6,4a is equal to 30.567 minus 22,5, which gives us 8,027. We now divide both sides by 6,4, divide by 6,4, and then our a becomes 31,25 meters per second squared. Okay, this makes sense. Okay, then next question. Oh, that is it. That's all. It's question number 2. Because they only wanted the acceleration. Alright, then we move on to question number 3. Question number 3, we're being told that a hot air balloon moves vertically downwards at a constant velocity of 3,4. Okay, so if the velocity is constant, acceleration is going to be 0 for the balloon. When the balloon is 15 meters above the ground, a small ball is dropped. Refer to the diagram below. Okay, so since the balloon is moving downwards and then the ball is dropped, so the ball needs to continue with the motion of the balloon as initial, just from the law of inertia. Okay, so there's no reaching maximum height and then turning and so on. Okay, we go on and say that the ball strikes the ground and bounces vertically upwards. The hot air balloon continues to move downwards at the same constant velocity. Ignore the effects of air friction, and then they want us to define what the term fall is. So we know that free fall is a body, or it's just a motion. It's a motion, we can say, under which acceleration due to gravity. Acceleration due to gravity is the only force acting on the body or the object. So, or you can say it's the motion during which only force acting on the object accelerates due to gravity. Whichever way, as long as we get to know that it's only acceleration due to gravity that's acting there. Then the sketch below represents the positions of the ball relative to the ground. Okay, the time it was dropped up until it reaches maximum height at the first bounce. Okay, then the question is 2.3 points. Was the ball in free fall between T1 and T2? Just write yes or no. The answer is a no. For as long as the ball leaves the air and touches the ground, it's no longer free fall. Okay, because the force that is entirely there is not only acceleration due to gravity. So the answer there will be a no. And then 3.3, they want us to get the value of T1. So T1 is the time when the ball strikes the ground. How do we determine that? So we know that the initial velocity of the ball was 3,4 meters per second, because that is the velocity with which the hot air balloon was moving. So from the equations of motion, what I can do, I'll just put it inside and say 3.3.1. I can use now my change in y. Okay, is given as the v delta t plus a half a delta t squared. Write the formula for your mark. Since the stone or the ball fell through 15 meters, so our change in y is going to be a 15. We're looking for the t, but the initial velocity was 3,4. Let's do the substitution. So change in y, we're saying is a 15. Okay, is equal to 3,4 delta t plus a half. We know that the g is the same as the a, which is 9,8. Since it's moving downwards, I'll take it to be positive, then multiplied by t squared. When I simplify this, I'll get 4,9 t squared plus 3,4 t minus 15 is equal to 0. Now when I use my quadratic formula of negative b plus minus square root of b squared minus 4ac over 2a. That's going to be negative 3,4 plus minus square root of 3,4 squared minus 4, the a is 4,9, the c is negative 15. Divide this by 2 times 4,9. So the first answer I get is 1,44 seconds, and then the second answer I get is negative 2,13. But we know that time should never be negative. Therefore, the t is going to be 1,44 seconds. Okay. So that is 3.3.1. Then 3.3.2, they want us to get the height, the hot air balloon above the ground at the instant when the ball struck the ground. So we know that we shall be using the time that we obtained. This is 3.3.2. Okay, so the time is 1.44 seconds. Now we need the displacement, which is delta y. We know that the acceleration is going to be a 0 since there is no change within the velocity. Okay, so if I use still the same equation of delta y is equal to vi delta t plus a half a delta, that square. Remember, the balloon is not in free fall, it's having a velocity. So the acceleration here is a 0, which kills this entire thing. So we're looking for change in y, which will be the 3,4 multiplied by the 1,44 plus, that's a 0. So 3,4 multiplied by 1,44, that gives me 4,896. I'll just call it 4, okay, let me just write everything there. 96 meters. But the question is asking the height of the air above the ground. So the hot air balloon would have moved this towards the ground. So the height above it will be 15 minus 4,896. Okay, so I'll say 15 minus the answer. I'm getting 10,104, which is like 10,1 meters. All right, so that is 3.3.2. And then 3.4, the ball was in contact for just 2 seconds and then left the ground with an upward velocity of 7,2. Use the equations of motion to calculate the value of T3. Where is T3? So at T3, that's when the ball reaches the maximum height. But we know that at maximum height, the V final is 0. They gave us the V initial to be 7,2. Let's determine the maximum height. We don't need the maximum height, but just the time within which the ball reaches the maximum height. So 3.4, we're saying that at maximum height, after the bounce, the V final is 0. The V initial was 7,2. What we want is the delta t. The ball will be moving with 9,8, which is the same as the acceleration. Okay, so we can use the first equation of motion. V final is equal to V initial plus a delta t. Let's do a substitution. That's a 0. V initial is 7,2. Is that correct? Yes. And then plus, since the ball is moving now upwards, I'm going to take the a to be negative 9,8 multiplied by delta t. So move the 9,8 that side, saying 9,8 equal to 7,2. I'll divide by 9,8 divided by 9,8. Okay, 7,2 divided by 9,8. I'm getting 0,735. 0,735 seconds. Okay, so that is the time it took the ball to reach the maximum height. So now if this time the interval here is 0,735, the interval in between is 0,2, and then from there to there is 1,44. We need to just add up all the three values to obtain the actual value of T3. So T3 is going to be 1,44 plus 0,2 plus the 0,735. If I do my additions, I'll have 1,44 plus 0,2, which gives me 2,37. Okay, seconds. Just jot it this side. We shall say 0,735 plus 0,2 plus 1,44. So it's 2,37 seconds. All right, so that is question number 3. Let's look at question number 4. Being told that trolleys A and B of masses 3,2 and 2,6 respectively are held at rest on a horizontal friction less. Okay, in other words, there is no friction there. With a compressed spring between them, okay, after the trolleys are released, the spring extends its natural length, then falls onto the trolleys. Trolley A now moves with a constant velocity of 0,4 to the left, and B moves with a constant unknown to the right. B reaches the end after a time of 1,3 seconds. Okay, state the principle of conservation of linear momentum. So this simply tells us that the total linear momentum, okay, total linear momentum of an isolated system, remains constant, or you can tell us is conserved. All right, then 4.2, they want us to calculate the distance that is traveled by trolley B. Remember, they told us it traveled that distance in 1,3 seconds. Initially, it was at rest, so the V initial is 0. But before you can get the distance, we need to get at least the V final. For us to get the acceleration, at least we need the final velocity. So we can apply the conservation of momentum and then get our V final before we can determine what the question wants. Okay, so that is 4.2 that we're answering. So 4.2, we're going to say that momentum before, or the sum of momentum before, must be equal to the sum of momentum after, which is mass of A, V initial of A, plus the mass of B, the V initial of B, should give us the mass of A, the V final of A, plus the mass of B, the V final of B. So the mass of A is 3,2. Okay. Initially, it was at rest. Mass of B is 2,6. Initially, it was at rest. Is equal to the mass of A, which is 3,2, but then the velocity of A is 0,4 in the opposite direction. So I'm going to take that to be negative 0,4. Plus mass of B, which is 2,6 times the V final B that I don't use. So play with that. That's going to be 3,2 multiplied by 0,4, which gives me 1,28. Negative 1,28 plus 2,6 VFB must give us a 0. So I can move this to that side. 1,28 is equal to 2,6 VFB. Divide both sides by 2,6 by 2,6. So my final velocity of B becomes 0,49 meters per second. Okay. Now, having obtained the 0,4 meters, 0.49 meters per second, now I have my velocity final. Then I can go down and determine my displacement. Okay, so I cannot use the first equation of motion, but I can use the last one, which is V final squared is equal to V initial squared plus. Will this help me? Because I need 2A and then the displacement. Do I know the acceleration? I can get the acceleration though. I can get my acceleration, but that is going to take some bit of time. Okay, if I get the acceleration, V final minus V initial over delta T. Our final is 0,49 minus 0 divided by 1,3. 0,49, 0,49 But why not use the first one? V final is V initial plus A delta T, but we need the acceleration. Fine, let me use this. 0.49 divided by 1.3 seconds. That gives me 0.377 meters per second squared. And then I can just substitute there. So V final 0.49 squared is equal to the 0, which is the initial, plus 2 multiplied by the 0.377, then multiplied by the delta x we need. Then I can get the 0.49 squared. Why don't I just say delta x is 0.49 squared divided by 2 times 0.377 straight away. Okay, 0.0.0.49 squared dividing it by 2 times 0.376. I get 0.318 meters. 0.318. This is one approach. If I am going to go with that as my answer. All right, so 0.318 meters. That's the displacement. And then the next, they're telling us the average force exerted by the spring on the trolley while they are in contact is 4.2 newtons. Calculate the time it took the spring to exert the natural length. So the average force when they were in contact. So this is more like the impulse. Or you can use the impulse formula anyway, whereby F net should be equal to the impulse which is over change in time. The question is asking for the time. So that's going to be 4.2 is equal to the change in momentum. I can use 2.6. Okay, we know that 2.6 is for B. Our final velocity is going to be 0.49 minus 0 divided by delta T. I'm going to get my T alone. It's going to be 2.6 multiplied by 0.49. I'll divide it by 4.2. If I punch that into the calculator, 2.6 into 0.49, dividing it by 4.2, that becomes 0.30. Okay, so delta T is 0.30 seconds, or 0.303 seconds. All right, question 4.4, trolley B is now replaced with trolley C, which has a larger mass. Okay, and then the same compressed spring is replaced or is placed between trolleys, and the trolleys are then released. The average force exerted on the trolleys remains as 4.2 newtons for the same period of time as calculated in 4.3. Okay, how does the magnitude of the velocity of trolleys compare to the magnitude of velocity of B that was initial? The reason is going to be increasing the mass, okay, will increase what we call the momentum. Will increase the momentum. But we know that mass is inversely proportional to velocity. We know that momentum is mass times velocity. So if we make m the subject, it's going to be momentum over v. So mass is inversely proportional to velocity. So increasing the mass will lead to an increase in this. But since mass is inversely proportional to that, So increase in mass leads to a decrease in the velocity of the body. Right, so that is 4.4. In question number 5, we're being told that a crate of mass 18 kilograms initially at rest slides down a frictionless slope from A to point B, and the crate moves along a rough surface. Okay, so there's a rough surface there. Towards point C, point A is 3 meters above the horizontal surface in the diagram below. State the principal conservation of mechanical energy. So is the same. Total mechanical energy in an isolated system remains constant. Okay, or you can tell us it's conserved. And then 5.2, using the energy principles only, calculate the speed of the crate at energy principles. So energy is conserved. So one thing we know that at point A, when the crate is at rest, it will be having EP mix. The EK is going to be a 0. At this point B, the lowest, the EP is going to be a 0, and it will be just having the EK max. So since we want the speed, we have to use the EK. Since there is conservation, whatever is here, must be to that. So we're going to say that at A, we have the EP max and EK 0. And then at B, we have the EK max and EP being 0. But from conservation, the conservation of energy, or from the energy principles, we can say that the EP max must be equal to the EK max. This is at A and this is at B. So mgh must give us a half mv squared. Now since we're dealing with just the same body, we can just cross out the masses. It's fine. So that's going to be 9,8 multiplied by the height, which is 3 meters, should give us a half v squared. Multiply both sides by 2. So this cancels that. We have 2 times 9,8 times 3, which gives us 58,8 is equal to v squared. And then I'll have to find the square root. And then my velocity there is going to be getting 7,668, which is 7,67 meters per second. Okay, so that is 5.2. And then they're telling us that there is a constant frictional force of this much that is acting on the crate as it moves from point B towards C. And then the crate comes to rest at point C. So which means our V final here is 0. Our V initial there is 7,67. All right, take the work energy theorem. So we know that this simply states that the work done on an object, by a net force is equal to the change in the object's kinetic energy. Okay, the work done on an object is equal to the change in the kinetic energy. And then they want us to use the energy principles again only to calculate the distance that the crate traveled from point B up to point C. Okay, so let me just get down here. So we know that W net must be equal to the change in EK, which means that our W net is equal to the EK final minus EK initial. So as this body is just continuing to move, the only force that is acting on it will be this frictional force, so that it comes to a rest. And it's going to be acting in the opposite direction. So I'm going to look for the work done by all the forces. And the work done will be just by the frictional force. So I'll say frictional force multiplied by the delta x, okay, because that's what the question was, and then multiplied by the cos of 180. This should give us the AK final, which is going to be like a half mv final squared minus a half mvi squared. So our frictional force, they gave it to us as 40,6. Okay, 40,6 multiplied by delta x, and then the cos of 180 is equal to a half. The mass is 18 kilograms. Good. Times 18 multiplied by 0 minus a half times 18 multiplied by 7,67 squared. Okay, so on this other side, I'm going to have negative 40,6. Delta x is equal to negative, that's going to be 9 multiplied by, let's just say 7,67, but squared. It becomes 5.9. Okay, 46. Divide both sides by negative 40,6. Negative 40,6. This cancels that, which means our delta x is going to be 46. It's going to be 13,04 meters. Okay, so that distance is 13,04 meters. Then 5.5, we're being told that the height of the track is now lowered. So that point A is at a vertical height of less than 3 meters. Okay, so somewhere here or below. Okay, point B. Then same crate again is released from point A. How will the distance now traveled by the crate along the horizontal surface before it comes to rest compared to the distance that is calculated in 5 meters? Right, only greater, smaller, or equal to? Now we know that since the energy that we are dealing with is dependent, okay, so EP is directly proportional to the height. If you increase the height, you increase the energy, okay? Likewise, since the EP was the same as the EK, increasing the height will increase the EK. Now, the moment you reduce the height, you're reducing the value of the EP, you're reducing the value of the EK, which means the velocity with which the crate is going to move, or the crate is going to have at point B, is going to be smaller. And if the velocity is smaller, which means it's going to take a shorter period of time before it comes to rest, which means the distance that is going to be moved is going to be smaller than. Okay, so here we're going to say smaller than. Then we can say that a decrease in height, okay, decrease in height will lead to a decrease P and EK, which lowers the velocity and then thus the distance moved or the distance traveled by the crate is smaller or smaller than. Just something of the sort of. So that is question number 5. Question number 6. Question number 6, they are telling us we have a stationary listener that records the frequency of sound emitted by a siren of a police car when the car is traveling at a constant velocity of approaches the listener this is what was recorded. Okay, we can say that towards the listener, the frequency of the listener is 615. Then the car passes the listener at P1 and then moves away from the listener recorded. So when you're moving away, the frequency is 526. And then they want us to state Doppler effect in words. So we can say the apparent change. Okay, apparent change in the frequency of sound detected by the listener because the sound source and the listener have different velocities that are relative, that are relative to the medium of propagation. Just that. Then use the information to calculate the speed of sound in air. So this is a long question, but it's fine. We shall attempt it. Okay. So we're going to start by writing down the Doppler formula, where we know that the frequency of the listener is equal to V plus minus the VL over V plus minus the VS multiplied by the frequency of the source. Okay. Now we have two scenarios. When you're moving, or when the police car is moving towards, what is the recorded frequency? We said it was 615. Okay, 615 is equal to V that we need plus the velocity of the listener, which is a 0, over V. This is going to be minus 26 times the frequency of the source, which we don't know. When I play around with this, when I have 615 into V minus 26 is equal to F S times V. Can make Fs the subject, so that is 615 into V minus 26 divided by V. Call this equation 1. And then let me look at the other scenario where the police car is moving away. Just from the same equation, I'll just say 526 is equal to V minus 0 over V plus 6 times the frequency of the source. Do the same thing. 526 into V plus 26 is equal to V multiplied by F. Why can't I just simplify? We can't. I mean, this is VFS, VX, because it's the same velocity of sound that I'm looking for. It's the same frequency that is being used. Call this equation 1, guys. She's just making life hard. I'll call this equation number 2. Then I'll equate the equation 1 is equal to equation 2. Then I'll try to open this. It's going to be 615V minus, we have 615 multiplied by 26. That gives me 15990 is equal to 5263 plus, that is 26 times 5, 6, which is 13676. I'll collect my like terms. I'll move this side. I'll move this side. So 615 minus 526. That gives me 89V. Is equal to, it's gonna be 13676 plus 15990. That gives me 29666. Then I'll divide both sides by 89. Okay, so divide this by 89. I'm getting 333,325. Okay, also meters per second. That's what I get. Then calculate the wavelength of the sound emitted by the police siren. So we know that V is equal to F lambda. Okay, F lambda is the wavelength that they need. We know the frequency of the source? No, but we can get it. Okay. So since we had already created this equation, we can use it and say frequency of the source 615 into the 333, minus 26. I'm dividing it by the same velocity, which is 333,33. Punch that into the calculator. 615 into 333,33 minus 26. We are dividing it by 333,33. This gives me 567,03 hertz. Okay, so we know that V is equal to F lambda, which means that lambda is going to be V over frequency. So we know that the V was 333,33. Now I'm dividing it by this 567,03. Okay. So what do we end up with? What do we end up with? So 333,33 dividing it by 567.0 that. So that gives me 0.588 meters. Okay, so that is the wavelength that the question needed. And then 6.4, sketch a graph of the recorded frequency versus the time of the motion. Okay. This is frequency in hertz. Then this is going to be our time in seconds. One thing we know is that we need, as the motion of the car moves towards and passes the listener and moves away, label T1 as the time, no values are needed. So frequency versus time of the motion of the car as it moves towards the listener and then away. So we just need the observed frequencies. Okay, remember we had the 615 and then the 526. Yes. So the frequency started by being there. And then at a time T1, the frequency dropped to there. So this is what we need. And that is all. We don't need any values. Okay, so that is question number 6. We move on. Question number 7. X is a point that is 0.025 meters away from a 4 nanocoulomb charge. Then they want us to draw the field pattern due to this. So it's a positive charge. Yeah. Okay, we know that the field lines must be moving out. And then the arrows must be just in the direction. Okay, so that is what we have to do with 7.1.1. Then 7.1.2, calculate the magnitude of the electric field at X. So we know that electric field is given as E is equal to KQ over R squared. Okay, so our K is 9 times 10 to the 9. Our Q is 4 times 10 to the negative 9. This is nano. And then we are dividing this by 0.025 squared. Okay, so when I punch this into my calculator, I'm having that much over 0.025 squared, which gives me 5,7,600 Newton per block. Okay, then 7.2, 7.2, two identical neutral polystyrene balls A and B are suspended from a ceiling by insulated strings of equal length as shown in the diagram. Okay, they are hanging nicely. And ball B is given an initial negative of QB, some unknown magnitude. Then the balls attract each other, touch, then repel each other. Okay, and they get rest. Centers 10 centimeters apart, so that each string makes an angle of 90 degrees with the vertical, as we can see that. All right, then 7.2.1, they want us to state Coulomb's law in words. Okay, so with Coulomb's law, we can say that the magnitude, I'll just start it from here, and we say that the magnitude of the electrostatic force, okay, magnitude of the electrostatic force exerted by one point charge on another is directly proportional, okay, directly proportional to the product of the charges, the product of the magnitude of the charges, magnitude of charges, okay, inversely proportional to the square of the distance between them, the square of the distance between them. Okay, then 7.2.2, they want us to calculate the magnitude of the initial charge QB, given that P is having this mass. Okay, so what I notice, or what I can see that could probably help me, is if I look at this ball at this point, I believe there is a tension force there. If that is a 9, which means if I draw a vertical line like that, this must also be a 9. Which means there are two components that are acting here. Okay. So we have the T, this is going to be cos 9. And then we have the T sine of 9. So we know that the T cos of 9 must be equal to the weight of this body, of this ball. And then if I look at the horizontal, since there is repulsion, okay, of the forces, this one is pushing this side and this one is also pushing that side. Does that make sense? No, it doesn't. But it makes sense. Whereby this force is acting in that direction, this force is acting in that direction. Which means that the TS9 must be equal to that force of the repulsion. Okay, so that's the scenario that I'm looking at. First, the magnitude of the QB. So I can start by finding the force between them at this point when they are separated. Okay, so we know that it's K, Q1, Q2 over R squared. The force is what we need. Okay, that's 9 times 10 to the 9. And then I'm going to multiply it by Q squared, since both are having the same magnitude of charge. Then I'll change this to meters, which is 0.1 squared. Okay, I can call that my first equation. Then I come down and play around with another equation whereby T cos of 9 gives me the weight. Then for me to get the T, I'll get the mass, which is 0,012 multiplied by 9,8 over the cos of 9. Okay, then what answer do I get here? So 0,012 times 9,8, dividing this by the cost of 9. This gives me 0,119 newtons. Okay, then I'll go to the horizontal part and say, but my F, okay, is the same as T sine of 9. Okay, so where I see F, I'm just going to replace it with that. So T, we already have the value, so it's going to be 0,119 sine of 9 should give us 9 times 10 to the 9 q squared divided by 0,1 squared. Multiply both sides by the 0,1 squared divided by 9 times 10 to the 9. Okay, I need to get the value of q squared alone. Okay, so I'll end up with q squared being, let's see, 0,119 sine of 9. I'm multiplying it by 0,1 squared, and then I'm dividing it by 9 times 10 to the 9. Okay, this gives me 206,84 times 10 to the negative 16. Then I need to find the square root. Okay, square root of the answer. Oh Lord, why is it such a big question? So big an answer, is so small. So 1, 2, 3, 4, 5, 7. Okay, so I have 1,4 times 10 to the negative 7. So this will be coulombs. So that is just the Q. But then the question is how much charge was initially given to that. Remember, this Q that we are getting is what the bodies will have after the separation. Remember, before they separate, there is a Q on A, there is a Q on B, and then they have to separate. Okay, so which means if I get the Q on A plus the Q on B divided by 2 must give me what is on B. But since A was neutral, there was no charge there. So I just have to multiply this answer by 2. So my answer multiplied by 2 gives me 2,88. So 2,88 times 10 to the negative 7 coulombs. So that is what I'm having. That is what I'm having as for now. Alright, so that is with that question 7. Question number 8. Battery of EMF 12V and internal resistance 0,2. Okay, is connected to 3 resistors, voltmeter, and then 2 switches, then some wires. And the resistor Y is twice Rx. So this is the same as twice X. Okay. Then when both switches are closed, the reading of the ammeter is 5.5. So when the two are closed, we are given that. Can you give a reason why there is no current flowing through RZ? So what we can notice is that for as long as there is a switch over RZ, current tends to take a route with less resistance. Okay, so we know that current will just follow this route instead of going through this obstacle, which is the resistor. And that is the reason as to why the current will not go through it. So in other words, it's just a shortcut. What is going to be the reason? We're going to say that current uses a shortcut with no resistance. Shortcut via S1 with no resistance. Alright, and then 8.2, they want us to get the resistance of Y. I can just write it up here. So when both are closed, which means we only have these to be working. And then the current is 5.5. So what do we do? What do we do? Now, since we have our EMF, we can use the EMF formula, but let me first get the external resistance. And since the two are in parallel, I'll get my R effective as product over the sum. So it's going to be Rx plus, no, it's going to be Rx times 2Rx divided by Rx plus 2Rx. So that's going to be 2, let me just say x squared over 3x. 1x cancels that, so it's just going to be 2 over 3x or Rx. This is my effective resistance. Now when I apply the EMF formula, which is I into R plus small r, our EMF is 12, our I is 5,5 into 2 over 3x plus 0,2. So start by dividing both sides by 5,5. So 12 divided by 5,5 gives me 2,18. 18. Let me use it. Is equal to 2 over 3x plus 0,2. I'll move the 0,2 that side by subtraction, which means that the combination of the parallel is giving me 1,982, which is equal to 2 over 3x. Then I'll divide both sides by 2 over 3 divided by 2 over 3. And then the answer that I'm getting for x is 2,67 ohms. Okay. But now the question is asking for resistance Y. So which means this is going to be 2 times 2,67. Alright, so that gives me 5,35. 5, is what I'm doing. Set 1,982. Okay. Multiply by 3, divide by 2. I get 2, there's a problem, guys. What's wrong with my calculator? Getting a different answer. It's 2,973. So which means I need to multiply this with 2,973. Okay, which gives me 5,95. 5,95 ohms. Let's see again. 1,982. Said we are dividing it by 2 over 3. Oh, I did not use the bracket. 2,975. Which makes sense. So then 8.3, calculate the power dissipated by Rx, still under the same scenario. So when we look at Rx, we said it is 2,975. It's approximately 2,98, around about 3 ohms. Okay. They want us to get the power there. So I don't have anything to do with current. I know nothing about the current here. So all I need to get is the external PD, or the voltage. That is what's going to help me here. Okay. So how do I get my external voltage? I'll have my EMF, which is 12. Okay. Now let me get the internal one first. That's going to be easy. So V internal is going to be 0. How is that going to help me though? 0,2 times 5,5. We have the current already. Okay, 0,2 times 5.5. 5.5. Hello, it's 1,1. Okay, then I'll get external as 12 minus 1,1. Okay, that gives me 10,9. So that is the voltage across. Remember, this is parallel, so it's the same. Then for me to get the power, I can use V squared over R from the power equation. So my V squared is 10,9 squared over the R, which is 2,975. 2,975. Okay, when I substitute into the calculator, 10,9 squared, dividing it by 2,975, that gives me 39,94. 39,94 if you round it off. That is watts. Okay, so that power is sorted. Let's move on. Now, both switches are now opened. Both switches are opened. Okay, and the reading is this. Now, if this is open and this one is open, it simply means that the current that is coming is just going through RY, and it's also going through RZ. So these two are in series. And we know that the current will just be constant, which is 1,3, and the current here is also 1,3. What's going to be different is the potential difference. Across two resistors going to be different, but it will be equivalent to this external resistance, the external voltage 10,9. Okay, so what do they want? They want the reading on the voltmeter. But we know that the voltmeter is only connected across RY. So what I'll do, I'll just say my V is equal to IR from Ohm's law. So that's 1,3 multiplied by the RY, which was 5,95. Okay, 1,3 multiplied by 5,95, that gives me 7,74 volts. Okay, and then switch S1 remains open while S2 is closed. Okay, now the moment they said S1 remains open while S2 is closed, let's see. The moment they open that, which means now all the three resistors are playing a role within the circuit. What does the question want? The reading of the ammeter. The reading of the ammeter is what we need. Okay. All right. Let's see. So what we can start with is looking at the two scenarios of where all the three resistors are playing a big role. We already know the value of this resistor. We know the value of this resistor, which is 5,95. But I think we can still use this 1,3 to help us determine the resistance of RZ. That's what I'm saying. Now, since the total, that's not going to make sense. Let me use this 1.3 now as my current. Okay. So which means the EMF is I into R plus the small r. Our EMF was 12. The current is 1,3. Now this R is going to be the R effective, which is the external. I'm adding the 0,2. Divide both sides by 1,3 first. So 12 divided by 1,3. 12 divided by 1,3. That gives me 9,23. Okay. 9,23. I'm subtracting 0,2. 9,23 subtract 0,2. That gives me with 9,03. So this is the resistance effective. Okay, the effective resistance across. Now, we know that Y and Z are in series, but already Y is 5,95. So for me to get RZ, it's going to be 9,03 minus 5,95. Is that okay? Okay. Then we're saying we're subtracting 5,95. That gives us 3,08 ohms. Okay. So this is a 3,08 ohms kind of scenario. All right. What I need is the current. Good. So we can go back and say that initially we saw that this combination of the parallel was giving us a 1,982 ohms. We can just confirm that and see. If I get 2,975 multiplied by 5,95 divided by 2,975 times 5,95. Say plus. That gives me 1,982 roughly. Okay, so this entire thing is in series with this, which means that my effective resistance, okay, this is 8.5. Okay, I'll say 8.5. We said 1,982 plus what I just calculated, which is the 3,08, must give us 1,982 plus 3,08 gives us 5,062 ohms. This is the effective resistance. Then if I go back to the EMF, where I have I into R plus small r, we need the current, which is the EMF over R plus R. Substitute is 12 over, this is 5,062 plus the 0.2. Okay, punch this into the calculator. This is 12 over, you can say 5,262. 5,262. Then that gives me 2,28 amps. Therefore, the new ammeter reading is going to be 2,28. And just round it off to 2,3. So that is what we end up with. That is what I end up with question number 8. Then question number 9. Question number 9. The simplified diagram below represents an AC generator with a coil that is rotating clockwise. And wire to change the external circuit. Okay, so for as long as we're dealing with an AC generator, then we have to use the right hand rule. And the 9.1, what direction will the current flow? So using my right hand rule and then looking at the direction of the magnetic field, because now the direction is this. This is the B. And then it's turning clockwise. That's what they said. If I look at just this line alone, so which means the direction is up. Now that's the up first. Now they want the current. So the current must be moving from Y to X, which is that direction. So here I'm just going to say Y to X. You don't need to explain. Just use the right hand rule. Okay. So this is the right hand rule. That makes sense. Then 9.2 state the energy conversion that takes place within a generator. So we know that a generator is known for converting mechanical energy. Okay, mechanical energy to electrical energy. Okay, mechanical to electrical. All right, then they're telling us that the maximum voltage, we can say Vmax, is 125V. Can we define what the root mean square voltage represents? So it's gonna say this is the AC voltage. Okay. Why am I saying voltage? Yeah, I can use voltage. Let's be talking about voltage. So it's the AC voltage. Okay, which dissipates the same amount of energy. Okay, that is equivalent to a DC voltage. Okay. Then calculate the Vrms. So we know that from the formula page, Vrms will be Vmax divided by square root of 2. Just write that formula down, and then we do the substitution. So 125 divided by the square root of 2. 125 divided by square root of 2. 125. I'm getting 88,39. And then the total resistance is this, calculate the maximum current. So resistance has nothing like root mean square. There's nothing like maximum resistance or minimum whatever. So what we can do, since they want the current, we can just use the V is equal to IR straight away. Okay, since they want the current, we know that current is going to be V over R. Now, since they want the maximum, I can just say Vmax divided by that. They give us the Vmax as 125. So 125 divided by 42,4. So V is equal to IR. And then do that. So if I say 125 divided by 42,4, That gives me 2,95 amps. Okay. Alternatively, since we got the VRMS, we can also do the substitution using this. And we have our 88,39 divided by 42,4. Okay, 88,39 divided by 42. That gives us 2,084. Then we just multiply this by the square root of 2, multiplied by the root of 2, and then you'll be able to get the same value so that you can change it to maths. Okay, then 9.6, the generator induced current at a frequency of 20 Hz. Coils that rotating from the initial position as shown in the diagram. Okay. So for as long as the coil is horizontal, this is when we experience the maximum EMF that will be produced. Okay. And then for as long as the coil is perpendicular, then we shall have less or minimum. So they want us to sketch the graph for 2 complete rotations. So what I'm going to do, I'll just say this is my frequency in Hertz. Okay, and then I'll have something like that. It is 1 complete rotation. And then I'll have the same thing repeat itself. So that is 2 complete rotations. So this is going to be 20. Then down here, I'll have a negative 20. This is time in seconds. Because they said they want induced current. If I use the frequency, that is how it's going to be. So that is that. All right, then that is question number 9. Question number 10, the last question number 10. They want us to define photoelectric effect. So we're going to say this is a process, okay, whereby electrons are ejected. Electrons are ejected from a metal surface. Electrons are ejected from a metal surface. Okay. When light of suitable frequency, when light of suitable frequency is incident or is shown on the surface. Okay. When we shine light of required frequency, then electrons will be emitted. So that scenario is what we call photoelectric effect. 10.1. So light of wavelength 4,7 times 10 to the negative 7. Let me jot it this side. Okay, 10,2 telling us it is 4,7 times 10 to the negative 7 meters. Okay, it's shown on the surface of this metal. If the threshold frequency is this much, so I'll say frequency naught is 4,37 times 10 to the 14. Okay, calculate the maximum speed of the electron ejected from the surface. And so we know that our maximum speed, we can look at the formula page and have E being equal to the work function plus the kinetic maximum or the EK max. So if I just try to use the formulas and do the substitution, we know that energy will be given as the constant, Planck's constant times the frequency, which is equal to the work function, which we don't know yet. So I can use Planck's constant and the threshold frequency plus a half mv squared. It's going to be max. Now we need the Vmax. Let's do the substitution. yet. Do we have the frequency? No. They gave us just the wavelength, so this needs to change. C over wavelength is equal to HF naught plus a half mv squared max. Do the substitution, that's 6,63 times 10 to the negative 34. The speed of light is 3 times 10 to the 8. The wavelength they gave us is 4,7 times 10 to the negative 7. Let me subtract same time, because when I move this, it's going to be subtraction. So 6,63 times 10 to the negative 34 multiplied by the frequency threshold, which is 4,37 times 10 to the 14. This must give us a half, multiplied by the mass. Now this mass is the electron mass, which is 9,11 times 10 to the negative 31 v squared max. Okay, so let's simplify the left hand side. So when I subtract this, I'm ending up with 13,347 times 10 to the negative 20 is equal to, when I simplify this, I'm having 45,55 times 10 to the negative 32 v squared. Just punch that in the calculator. Okay. Then I'm going to divide both sides and then put everything under square root. So 13,347 times 10 to the negative 20 over 45,55 times 10 to the negative 32 will give me my Vmax. So that is 5,41 times 10 to the 5. That is meters per second. Alright, so that is 10.2. Then 10.3, we're being told that a simple electroscope consists of a thin metal stem and then a thin length of gold foil. When the electroscope is neutral, the foil just hangs back, as shown in the diagram. And then when the electroscope is negatively charged, the foil is repelled from the stem, as shown in the diagram. So we can see this, and see if it's negatively charged. Then when ultraviolet light is shown on the disk, it is negatively charged, the electroscope collapses. What this means that this light, after being shown, remember, this is negatively charged. So if the electrons are passed there and then we have negative and negative, that's why there is a repulsion. So what this simply means that ultraviolet takes away some electrons. Okay, and for as long as electrons are removed, the stem will be more positive and it will cause some bit of attraction. So in other words, it neutralizes the entire system again. Then the question is, how does the frequency of ultraviolet compare to the threshold of zinc? Is it higher than, greater than, or lower than? Now the fact that this light removes some electrons from this disk, okay, which means the frequency must be greater because it surpasses the threshold. So we're going to say higher than it. Okay, then we need to explain our answer. So one, we say that electrons will be emitted or will be removed from the disk. Now we can say electrons are removed from the stem via the disk. Same thing. Removed from the stem, via the disk. Okay. This makes the stem more positive or just neutral, which attracts, and the whole thing is back to zero. Then they're telling us that green light is now shown on another negatively charged electroscope. The foil does not collapse. What does this tell us? Will the foil collapse? The intensity of the green light is increased. Right, yes or no? Give the reason for that. So the answer is a no. I mean, the fact that the green light has failed to make collapse, which means the threshold has not been met. Okay. And then 2, okay, so we can say that, okay, 2, remember, intensity has no interference with the frequency. So what matters is just the frequency, regardless of how much you bring about of the green light. For as long as the minimum frequency is not met, then it's not going to help. Okay, so the answer is a no. You can say that electrons are only emitted or only ejected from a metal surface with a range of frequencies, okay, and kinetic energy. So the number of electrons depends on whether the threshold was reached or not. Was reached. Okay, so for as long as the radiation does not have the required energy and the threshold frequency, no electrons will be emitted. So guys, that is that. And then I just want to stop there and wish you guys all the best in paper 2. Remember the disclaimer, this is just the proposed or suggested, it's not the actual memorandum, okay? So if there are any mistakes, if there are any errors, please, you're more than welcome to correct us through your comments and all of that. Thank you very much. And then I sign out. So we're going to start with section A, which is multiple choice. We have around about 10 questions, and each question carries 2 marks. Okay, so question number 1. They're telling us that there's a book that rests on a table. Which of the following forces will form an action-reaction pair? So an action-reaction pair is basically a pair of forces that must counteract each other. An example, if a book is resting on a table, we know that 1, there's going to be the weight of the book that will be acting on the table, and then the table in reaction to that must create a force that must act on the book. Okay, from Newton's third law, whereby action and reaction must be equal but opposite. So when we look at the options, they're telling us the force of the earth on the book. That's not true. The force of the book on the earth, that is also not true. The force of the book on the table, no. The force of the table on the book. So the correct option there would be option D. So I'll take D for question 1.1. And then 1.2. Telling us a person is standing on the bathroom scale in a moving lift. Which of the following motions of the lift will result in the smallest reading? Okay, the lift, when the lift accelerates upwards, when the lift accelerates downwards, when the lift moves upwards at a constant velocity, or when the lift moves downwards at a constant velocity. So I'm going with option B. When the lift is moving downwards, that's when the reading will tend to be smaller. Okay, we can explain that if we have, let's say, a free body diagram of the weight that's acting downwards and then the normal reaction upwards. Now, if there is a lift now, and then there is also the weight of the lift, the fact that acceleration due to gravity will always act downwards, so the amount of force downwards will be less, so the reading will also tend to be smaller. Then 1.3, the velocity versus time sketch graph shows the motion of a ball which was in free fall. So for free fall, that is basically motion under the acceleration due to gravity only. So the ball struck the ground after 30 seconds. And then the question is, which of the following statements will be correct about the ball? Okay, so the ball was dropped from a height above the ground. A height above the ground. Okay, there's some bit of sense there. But when you say it was dropped above the ground, when we look at the graph, at a time t, the velocity is 0, which simply means that this ball moved up, reached its maximum, and then went back below the point of projection and so on and so forth. Okay, so this narrative of drop from a height, no, I'm refusing. It's not making sense, not now. Then it was thrown vertically upwards from the ground. This is also not making sure, as much as the vertically upwards is correct. It was thrown vertically upwards from a height above the ground. Then it was thrown vertically upwards from a height, no, downwards from a height. So this is also out, because if it was thrown vertically downwards from a height, then we don't have a maximum height where the velocity is a 0. So this is out. The first one is out. We are left with just B and C. But now, since we are having issues with B, I'll choose option C to be the reasonable option there. Then 1.4, they're telling us the vector diagram below shows the initial momentum P1 and the final momentum P2, and then the change in momentum. So with vectors, we know that the length of the line always represents the magnitude. Okay, so we know that this positive magnitude is bigger since the line is longer. And then if we look at P2, we're seeing also a slightly smaller momentum compared to P1. Then remember, for us to get the change in momentum, it will be the P2 minus the P1. And since the P2 is smaller than the P1, that's why the direction is in the opposite. So which of the following sketch graphs correctly shows the momentum of the car for the time the car moved on the road? So you can see that initially the momentum was higher, and then the momentum dropped. So which option is going to make sense? Option B is out, because it's showing us that the momentum was lower than increased. When we look at option C, it was higher and then dropped into the negatives. Okay, and then it was lower and then increased. So D and B are out. Our problem now will be C and then A. So when I look at A, I think it would make the best option compared to C. Momentum just decreased because it shows the momentum of the car as it moved on the road. That's fine. Then 1.5, a stone of mass M dropped from a height h above the ground. Ignore the effects of air friction. Which of the following combinations correctly represents the kinetic energy? 1, and then 2, the total mechanical energy of the stone at the instant the stone has fallen through a distance of a quarter height. Okay, so what we can see is that if we have probably a building or a height h here, and then we are being told that the stone has fallen up to a certain height, which is a quarter h. We know that at the top of this height, the stone is going to have the maximum potential gravitational energy, and then 0 EK. And then at the height of a quarter h, the stone is going to have what we call mechanical energy, which is a combination of both the EK and the EP. Okay? But from the law of conservation of energy, we know that energy can neither be created nor lost. So the EP max at this height should be equal to the mechanical energy at this point. So let's get our EP max at a point h. Okay, know that EP is mass, gravitation, and the height. So you're going to keep it this way, since we don't have any values. Then at a point, a quarter h, our EP is going to be a quarter h multiplied by the mass multiplied by the gravitation. So which means it's a quarter mgh. This is our EP. Now for us to get the EK, we just need to subtract this from this. So that is 1 mgh minus a quarter mgh, which gives us 3/4 mgh. So this is going to be my EK. Okay, let's read the question again. Stone of mass is dropped from a height of the ground, ignore the effects. Which of the following combinations correctly represents the kinetic energy and the total of the stone at the instant has fallen through this? So we're not using the ground as a reference, we're just using the point of projection as a reference. So our mgh, or our EP, so EP is going to be a quarter mgh, and then the EK must be 3/4. So a quarter mgh, we said, so kinetic energy we said is 3/4. So which options are 3/4? We have A, and then we have C. Then they are also asking for the total mechanical energy. We say total must be equivalent to EP max. So I'll go for option C. Option C. That is showing us the kinetic energy and the total mechanical energy. Okay, so C is the correct option for 1.5. And then 1.6, they're telling us the spectrum of helium emitted from a star moving away from the Earth is compared to the spectrum of helium that is found on Earth. Which of the following statements is correct? The observed line spectrum from the moving star will have blah, blah, blah. So the star is moving away. So for as long as it is moving away, number one, what we need to remember is that the wavelength is increasing, okay? And then for as long as the lambda increases, okay, the frequency must decrease from V or from C is equal to F lambda. We know that if I make F the subject, it will be C over lambda, which means the two are inversely proportional. So what I'm going to say is that the frequency is lower, the wavelength is longer. 1.6, I'll go with option A. Okay, so A is my option. Then we move on to 1.7, talking about the magnitudes of electric fields generated by different point charges and measure a fixed point. For each measurement, the distance between the fixed point and the charges are the same. Okay, which of the following shows the correct representation for the relationship between the magnitude of electric field and then the charge? So from the formula of electric field, we know that it is F over Q. Then when you replace this F, Coulomb's law of electrostatics, Q1 over Q2 over R squared, and then you're dividing it by Q. So this Q cancels that Q, so which means you're just left with KQ over R squared. So you can just get this from the formula page straight away. Okay, so we can see that the electric field is directly proportional to the magnitude of the charge. Okay, so option A will be perfect. So as the Q increases, so will the electric field. All right, then 1.8, the diagram below represents a circuit in which all the external resistors have the same value. Okay, let me take this to be 2 ohms. Everywhere, 2 ohms, 2 ohms, 2 ohms. Then the question is asking, write which one of the ammeters in the circuit will have the lowest reading. It's in capital letters. So we have an ammeter here, this A, will give us the reading of the current within the circuit. Okay, so we expect this current to be bigger than this and that. Same applies with A4. So A1 and A4 are going to have the same readings since they are just connected to the circuit outside. They are not affected by these resistors. But we know that this resistor here and this one, they are in series, okay? But then these two form a parallel combination with this resistor by A2. So if I combine these two, it's going to be like 4 ohms, which means the resistance here is going to be bigger compared to the resistance here. So which means there's going to be less current that is flowing via this route. So the reading of the ammeter with the smallest value will be the A3. So I'll take C to be my option. Okay. And then 1.9, the following diagram is an electrical machine which is shown below. Okay, what type of machine is this? So before we draw the conclusion, we need to see which features are surrounding this machine. Number one, we have a source of energy, which is maybe a battery or something. So this is a DC source. So for as long as there is a DC source, it cannot be a generator. So C is out, D is out. Now, by virtue of the rings are split. Okay, so for as long as the rings are split, then this becomes a motor. So this is going to be a DC motor. Okay, so splitting the rings becomes a DC motor. Okay, so option A is 1.9, and then 1.10, which of the following combinations is correct for a line absorption spectrum in terms of the energy transitions of the atoms and the appearance of the narrow lines? Okay, so we know that whenever there is an absorption spectrum, like for as long as the particles or the electrons gain energy, they'll move from lower energy levels to higher energy levels. Okay, so option A is out, that is moving from lower, that is when they lose. That will be like emission. So this one is also out. So I'm going to focus on B and C, where there is lower to higher. Okay, and then what is the appearance of the narrow lines within that? Are they going to be colored or are they going to be dark lines? Correct option is C. They are going to be dark lines. Okay, they can be of different sizes, but they will be dark lines. So that is how question 1 would be answered. All right, so we move on to question number 2. Okay, so question number 2, they're telling us that block A of mass 4.1 is connected to block of mass 0.3 kilogram by an inextensible string passing over a frictionless pulley. Block A is at rest. on a rough horizontal table and block B hangs vertically as shown in the diagram. So we have a frictional force. Okay, so frictional force is 49 newtons, and then it is applied to block at an angle of 50 degrees the horizontal. Okay. Okay, and this causes the block A to accelerate to the left. Okay, so which means everything is moving to the left. And then they also gave us the coefficient of kinetic friction to the surface to be 0.35. Okay, so with all these details, we just need to. Okay, so which means the entire system is moving in that direction. Okay, then 2.1, they're asking us to state Newton's law, second law in words. Okay, so what we know about Newton's second law in words is that when a net force, let me just try to write it here. Okay, so we're saying when a net force acts on an object, the object will accelerate. Okay, object will accelerate in the direction of the force, will accelerate in the direction of the force, and the acceleration is directly proportional to the force and inversely proportional to the mass of the object. Okay, so that would be your 2.1. And then 2.2, they want us to draw a free body diagram that is showing all the forces that are acting on A as it accelerates to the left. So looking at A, we can see that there is going to be normal force, there's going to be weight that is acting downwards, and then there's going to be this applied force. The sine of theta, which means it's W, the sine of theta, which will be a half of W. But then it's not only FG parallel that's acting downwards in this trolley. So A is out, then W plus F wouldn't make sense. W minus F still doesn't make sense, because remember they have to be equal to each other, which means if there's any subtraction, there's an addition that's taking place, everything must just reduce to a 0. And the last one, W sine 30, that is only representing the FG parallel. So this question doesn't seem to have any correct option. None of the options are correct for 1.1. Let's look at 1.2. A box M is being pushed horizontally at constant velocity on a rough surface by a force F. Okay, so we have the arrows that are indicating the directions. Okay, if the force F that is acting decreases, then what happens? If no force acting on the body decreases. Okay, that sounds correct. Velocity of the box decreases. That's automatic, because since the force is going to decrease, which means even the rate at which it's moving will also decrease. Acceleration increases, the acceleration will instead decrease. The normal force increases. So option A and B, I'll go for option B, which is kind of straightforward. The velocity of the box will decrease. Then now 1.3, the ball is dropped from the height. After it falls, the charge reaches a velocity. Which of the following is correct? after it falls 3 meters. Now remember this is VP. Okay. Okay, so since it's vertical projectile motion, we know that our V initial is a 0 since the ball was just dropped. Now we know that the delta y is a 5 Newton. The acceleration due to gravity is 9.8 meters per second. Okay. Now after it has fallen 2 meters, it reaches a velocity v. They want us to get a statement for 3 meters. Telling us at 3 meters, the velocity is going to be this. I don't know that. Let me first find what the speed is at 2 meters and then at 3. So if I use the VF is equal to the VI, I'll use the AT or the GT. So our V final is what I'm looking for. Initial is 0 plus 9.8. But this doesn't have time, which means not going to make sense. There's not time involved. You don't have anything to do with time. How about I use the V squared one? It makes sense, yes. VF squared is equal to VI squared plus 2S or delta X or delta Y. Then, so our VF squared, we initially say is a 0, 2 times 9.8 times 3. Okay, so when I get to my calculator, you know, 2 times 9.8, that's going to be 19.6. Then 19.6 times 3 is giving me 58.8. Then when I find the square root of the answer, gives me 7.66. So the velocity after 3 seconds, after 3 meters, has to be 7.6. Telling us that the velocity is 3, that is out. The acceleration is 3 now, then the acceleration must be 9.8, which means option C makes a lot of sense. Okay, we don't even need to look at it because the ball is right, which is also wrong. Okay, then 1.4. In which of the following rows does the type of collision match with the total momentum as well as the kinetic energy? So with elastic collision, momentum is conserved, kinetic energy is not conserved. This is one. Inelastic, momentum is conserved, that's correct. Kinetic energy is not conserved. So I think it has to be B. Because in B, we can see that everything is correct for the momentum and the kinetic energy. Then 1.5. A block slides over the rough horizontal surface and eventually stops after 1.5 meters. Which of the following is false for the movement of the block? Okay. Are telling us that the net work done when the block decreases its kinetic energy. This is correct. Because we know from the work energy theory that the net work done is equal to the change in the kinetic energy, the EK. Okay. Now, when a block is getting slow or eventually stops, you know that the final velocity will be 0. And if we use the 0 minus the initial, which means we're going to get a negative kind of work done, which means it decreases the kinetic energy, which is true. The net work done on the block decreases its mechanical, that is also true when you look at the conservation of energy. Then the network is negative, which is true, and then the block is slowing down, which is also true. Yeah. So which means all the options are correct. Just choose one. 1.6. Diagram below shows the absorption spectrum of an element. from hypothetical stars A up to B, as observed from the Earth. Which star is moving away from the Earth with the highest velocity? So from B is equal to F lambda. So if the velocity is high, then we expect the wavelength to also be long. Okay. So when we look at the lines, the red shifting and the blue shifting, I think the best option has to be A, because we can see a bigger difference within the blue shift, and we have the smallest distance within the red shift. So option A is the best. 1.7, the diagram below, we have 2-point charges, which is the +5 coulomb, and then the -4 coulomb at a distance of x meters from point P. So which means they are equidistant. Then they want the net electric flow in terms of P. So what we can see is that if I look at the P1 and the P, okay, so P1 is positive, and this is a positive charge, positive one. Okay, so positive charges, they will repel each other. Okay, so in other words, the force that is acting on P is going to be to the right. Okay, so which means if I'm looking for my electric field, KQ over R squared, it's going to be the K, which is a constant, the R, which is also a constant with X, and then this Q, which is now the 5 to the east. Okay, then let me look at P and the Q2. Okay, P and the Q2, this negative, this is positive. So they're going to be attraction, which means the force still acting on E. So then P is to the right. So which means my E is KQ over R squared. The Q is a 4. Okay, so if it's a 4 to the east, which means the net is going to be this 5 plus the 4, which must give me 9E to the right. Okay, 9E to the right, which is E. Okay, then 1.8. 1.8, we have the circuit below, which is set up. The reading of the EMF is 9. There's internal resistance of 0.2. And then the ammeter reading is 1.8. So which of the following is correct when 1 coulomb charge flows in the circuit? So 1 coulomb charge is more like the energy that is moving around all the. Okay, so when we look at this, we have some sort of internal resistance within the battery. Okay, so 1 coulomb charge flow. Let's see, they're telling us that 9V is the potential difference across the resistance. So if the current is 1.8, okay, now that V is going to be but we know this EMF is I1 plus I small r. They give us the internal resistance as 0.2. So what is 0.2 times 1.8? 0.2 times 1.8. That gives me 0.6. When I subtract that from the 9, 0.36, I'm getting 8.64. So 8.64. So the first option is wrong. Doesn't make sense. And then 9 joules of energy is dissipated within the resistor. So when you look at the power, you know that power is current times the voltage. Okay. So the voltage is 8.64. The current is 1.8. So 8.64 times 1.8, I'm getting 15.552. So this is also wrong. And then 8.64 amps is flowing the circuit, and that's wrong. Okay. That is wrong. And then 8.64 joules of energy is dissipated in the resistor. No, that would make no sense. That would make no sense. Then 1.9, an EMF and being used across a stationary coil gap, a stationary magnetic field. Now, using more turns in the coil, this can only increase. Changing the magnetic field, yes, that's very correct. Then 1.10, we have the diagram below shows the energy levels of an form. The energy needed to excite an electron in the ground state. The energy needed to excite an electron in the ground state to the first level. Okay, so this question, remember from the scope that we have, this was scrapped out. This was scrapped out. But what would be the answer? Energy needed to excite the electron from the ground state to get to. I'm not even going to think about this. Let's move on to question number 2. Okay, so 2 blocks are attached to each other by a light. Next was 3 moving over the frictionless pulley as shown in the diagram below. So we have a slope AB with 50 degrees, and then the slope BC is 30 degrees. Okay, then they want us to state Newton's second law of motion. Okay. So we say that when kinetic force acts on a body or acts on an object, the object will accelerate in the direction of the force, and then this acceleration is directly proportional. It's directly proportional to the force, and inversely proportional to the mass. Just as straight as that. Then they're telling us that the coefficient of kinetic friction between the slope BC is 0.2. They need us to draw the direct line at M2. So when you look at M2, one, we're going to have the FG parallel moving that direction. We're going to have the tension of the string. We expect to also have the normal force upwards. Let me just put it in. The normal force acting downwards, and then the FG perpendicular in this sort of direction. So what I'll do, I'll say this is my F normal. This is my FG parallel. And that is my tension. And then this is going to be the weight. I'm going to put the FG perpendicular. Real friction? Yes. That means there's also another friction force. Okay. So we have roundabout 5 forces. It's the force. Then they want us to calculate the magnitude of the acceleration of the system. Okay, so for us to get the acceleration of the system, it's either we look at the two combined bodies at once, that will give us an option of eliminating the tension, or we just look at the second law of motion of the F net is equal to MA, so that we can get our net force and then the acceleration in return. I don't know which option will be quicker and better. Let me just, what is happening with slope AB? The friction is small, which means there's no friction. Yeah, we can do that. Let me try to look at the entire body. Just make sense. Makes sense, one makes sense. Let me look at body A, the M1. So when I look at M1, if I assume that this system is going to move in this sort of direction, which means the tension here must be greater. It's going to be F net is equal to MA. Okay. Then that's going to be the tension minus. Let's just put it aside. So we're saying the tension minus the FG parallel must give us the MA. Okay, we don't know the tension, but we know that the mg parallel is going to be mg sine of theta. Let me just substitute. So we know that the mass is 12 kgs. So that's a 12 times 9.8. And then the sine of 50 is equal to 12. Now, for that, my equation number 1. Then when I look at M2, and consider M2, so the FG parallel is going to be greater. So I have my definitive is equal to MA, which means my FG parallel minus the frictional force minus the tension must give me the MA. Okay, so what is the mass of this body? It's 70. 70. With the frictional force as well. So that is 70 times 9.8, the sine of it. That's correct. Minus the frictional force. Remember, frictional force is always given as the coefficient times the normal force, which normal force is mg cos of the angle of inclination. So I'm just going to substitute that. So minus the 0.2 times 70 times 9.8. The cos of 30 minus the tension, it must give me 70 times the acceleration. Okay, then since I'm not interested in getting the tension, I can look at equation number 1 and make tension the subject. Okay, so my tension will be 12A plus 12 times 9.8 sine of 50, getting 90, 0.0868. Okay, then I'm going to get this and replace it where I see the T. Okay. Then this is going to be 70 times 9.8 sine of 30, I'm getting 343 minus the frictional force 0.2 times 7 times 9.8 cos of 30, that gives me 118.819. Prefer 3 decimals. That's for the sake of accuracy. Then I'm replacing the T, which is 12A plus the 90.0868. We said it must give us 78. So when you subtract that, 3, 4, now let me just open the brackets first and then 343 minus 118.819. That gives me 227.181. So minus 12A minus the 90.0868 must give us 78. So I can move this 12A to that side. That's going to give me 82A. And then 224.181 minus 90.0868. I'm getting 134.0914. Then I'll divide both sides by 82. So over 82 over 82. Okay. Then I'm getting 1.635, which is approximately 1.64 meters per second squared. I think this makes some bit of sense. It's acceleration, not so big and not so small. Okay, so that is the answer, 1.64 meters per second squared for 8 months, okay? Then 2.3, they're telling us if the angle of BC is decreased, okay, to 20. Will the frictional force between the block and the slot increase, decrease, or remain the same? We don't need all of the dial. Yes, I don't skip anything. Will it decrease or increase? So in this case, remember our frictional force. We said it's mu mg cos of theta. We just need to look at what is the cos of 20, okay, and then the cos of 30. Okay. So if the angle is at 30, the frictional force becomes small. And when the angle is reduced to 20, the frictional force becomes big. Because in this case, to easily kind of drop or slope downwards. And then when it's a 20 slide, you're making it difficult for the block to slide below the incline. So in this case, we're going to say the frictional force will increase. And what will be the explanation? We know that frictional force is directly proportional to the normal force. Okay, so if the inclination is small, which means the normal force is going to be big. Okay, so I think that's enough. It's increasing because the frictional force is directly proportional to the normal force. Hence, the frictional force increases. The frictional force increases. Okay, guys, that's question number 2. Question number 3. I'm telling us we have a 25 round ball that's thrown vertically upwards. The ball leaves the hand 1.3 meters above the ground with the initial velocity of 7.27. On its way down, the ball bounces off the balcony at 3 meters per second before being caught at its maximum height after the bounce, ignoring friction and any horizontal motion. What's a projectile? Okay. So we know that a projectile is just a body that's just under. So someone asks what is straightforward, what is a projectile? So a body that's under the influence of the acceleration due to gravity. Okay. Right. Okay, so we're saying a projectile is an object. Okay. An object with, let's say, an initial velocity and then moves under the influence of the acceleration due to gravity. Remember, I said there's a difference between the free fall and the projectile. So with the projectile, you must give the object some sort of initial velocity. You must give it a push. You must kickstart it before acceleration due to gravity can take place. Okay. Then 3.1, they want us to calculate the maximum height above the ground that the ball will reach after it was thrown in the air. Okay, so they want us to do this. So what do we know about the initial velocity? We told us that the P.I. is 7.27 meters per second. They want the maximum height. Okay, so we know that at maximum height, the V final has to be 0. Okay, then we can use the V squared. So VF squared is equal to VI squared plus 2. Here you can see delta Y. Okay, since the ball was thrown upwards, I'm going to check my upward negative and my downward positive. So this is a 0 squared. It's equal to VI, which is 7.27 squared, plus 2. Our is now negative 9.8 times delta Y. So 7.27 squared is giving me 52. 857 is equal to 19.61. Okay, so this is going to be negative 19.6, but when I transpose it, I'll get a positive. Then I'll divide both sides by 19.6. We'll get in the 2.6965, which is like approximately 2.7. So which means from there up to there is 2.7. But the question was asking us from the ground. Remember, this ball was thrown 1.3 meters above the ground. So it will be the 2.7 plus the 1.3, which is approximately 4 meters. Okay. So it's approximately 4 meters. If I here in front of, it's going to be 2.697. And then I'll put my 1.3, which is 3.997. Which is approximately 4 meters. Okay, then 3.2.2, they want us to get the time that it takes until it bounces off the balcony for the first time. So we know that it goes up. And then it bounces. It bounces off with 3 meters per second. 3, when the time takes into it. So from the point of projection, up until it's there. What do you think? That's the point. So we could use the V prime is equal to V5 plus 80. Okay, so this parameters. And its weight bounces off the bottom because the perfect. So are we going to assume that it's a parameter per second? Well, that makes sense. No, it doesn't. It will not make sense. Because what I can do is if now the velocity of this mass is 0, I don't know the velocity of this point, because that is after the bounds, which is not going to make sense. It's not going to make sense. But I can get the distance. Since I know from there, this maximum height up to below is 4 meters, I can subtract this 3.2. So at the distance I have will be my displacement. Yeah, makes sense. So let's see. So which means my delta one. Let me just put this. Okay, so saying my delta y is gonna be 4 minus the 3.2, which is 0.8 meters. Okay, so that's our displacement. Our initial velocity, since it was now maximum, is going to be 0. Because now I'm looking at the second journey. Okay, from maximum, now dropping down. Okay, if that is true, I need time. I need time. So the displacement should make sense that second of the delta y is equal to VL2 plus a half P.2 squared. Yeah, it would 0.8. So that's going to die out to be just a 0. This is a half times 9.8 and 2 squared. Taking the 9.8 to be positive, since now it's the second journey that is dropping down. Okay. So this is going to be 4.9 2 squared is equal to 0.8. Divide both sides by 4.9 and then find the square root of the answer. And we can see what making sense, which is my answer, which is 0.4 here. What other information do we need about time? So let's see the question. Let's see the question. Because that 0.4 is just for this root, which is for the coverage. The question asks the total time taken from the top. Oops. But then we have to do it back in the class using the change in y. So then what's going to be the displacement? Well, 1.3 up to that. answer you got was 2.7. So it means you can use the 2.7. 4 minus 1.3 plus 2.7. That's very hard. It's 2.7, I mean the time as well. So 2.7 is equal to now initial, which was 1.3. There's 1.32. Now I'm subtracting a half times 9.8 to square. Okay, so when I use my quadratic formula, 1.3 minus, I'm just going to say 4.9. Maybe there's something really wrong. See, let's see. So this was a zero control, we need this P2. And we need the time from the point of projection to the maximum. Well, now it's over P3. I use that P5. Equal to the initial plus A2. Yeah. So this one is a 0. Initial is 1.3. Now minus 9.6, 1.82. So which means our T is going to be 1.3 over the 9.8. 1.3 divided by 9.8, which is 0.132. Okay. So then I can calculate 0.4 plus the 0.3. So that's going to be 0.5. Why are we using 1.3 again? It's 7.27. So 7.27 divided by 9.3 is 0.74. Okay. So it has to be 0.74 plus the 0.4. 0.74. That gives me 0.1.7. 0.74 plus 0.4. That's 1.14. 1.14 seconds. Yeah. Then 0.3, they want us to stretch the graph of displacement. Before the interaction. We're using the ground as a reference point. Now, remember, with the different graphs is the displacement. So how is the displacement? Smaller position. Okay. So when code is the displacement in meters, this is the time in seconds. Okay, so what we shall notice is that this ball is going to start at a height of 1.3 meters. Okay. Then it will go up, reach a maximum at the height of 4 meters. That's what we said. Then it will come down after a certain time. It will bounce over that time that we just calculated the 1.14. Then it will bounce up again to another height, which is below the maximum height. So something of the nature will what perfectly just make it up. So something like that. After that, and that. So this we don't need to know it, but before we need to, for the sake we need the max, the height from which the ball was released, the 1.3. That is in 3 kg. The maximum height, which is a 4. The height of the balcony, that's the height of the balcony, it's 3.2. Which is that, and then the time it takes to bounce down. So something you can reach out would guarantee you the 5 minutes. Then question number 4, when a ball hits and bounces off the surface, it exerts a force on the surface. So some group of learners investigated how this force varies over time as the ball hits the force sensor and bounces up. We used the 50 grams of force from the height of 1.5 meters vertical above the sensor. Okay, and then the following part is derived. And then the first question comes, what has it else to define impulse? Okay, so when we are defining impulse, the definition is that it's the product of the net force that is acting on an object and then the time. The net force acting on an object and its time. Okay, so we say product of the net force acting on an object and the time that it takes. Okay. Now avoid using the change in momentum kind of terminology because that is more like an application. It's not a definition of impulse. Then they want us to use the information in the graph to determine the magnitude of the impulse as the ball hits and bounces off the sensor. Okay, now remember we said impulse is the product of force and the time. So we are indirectly being asked to determine the area of this triangle. So we know that area of the triangle is given as a half times the base times the height. So that's a half. Our base is 15. So from 0 up to 15. And then our height is going to be 64.13. Okay, so a half times 15 times 64.13 is giving me 480.98. 480.98. But remember, this time is in milliseconds. So which means I have to divide that out and this means I have the 0.481 differences. Time as in milliseconds, so divide by 1,000 or multiply by 10 to the negative 9. Then 4.3, can we state the magnitude and direction of the change in momentum of the ball? So what we can see is when the change in momentum, mass or change in momentum is the same as interest. We don't need to go back to the mass and the velocity. So this 0.48, since it's positive, we're going to take it to the upwards. Okay. But then, what is the question asking for? The magnitude and direction. So 0.481 newtons upwards. It's upwards, positive. All right, then if the velocity of the ball just before it hits the force sensor is this downwards, can we calculate the velocity with which it bounces off the sensor? So then you can use the F net formula. F net times delta T, that's the impulse now, is equal to the change in momentum. What is the question asking for? Calculate the velocity with which it will bounce off. So it is M, V final minus V initial is equal to F net and delta T. So we know that the F net times delta T will give us that 0.48 volts, which is the impulse. Okay. So we shall say 0.481 is equal to the mass, is very close to 25 grams. 25 or 50? It's 50. It's 50 grams. So convert the grams to kilograms. That's going to be 0.05 kilograms divided by 1,000. I'll open this. The final minus the initial, which is 5.14. I'll start by dividing both sides by 0.05. So 0.481 divided by 0.05, I'm getting 9.62 is equal to V final minus 5.14. Then I'll move this 5 to that side, which will be 8. My sense correct, because the final is moving upwards, and then the initial is moving downwards. So it's a minus, that's a plus, so which means I'm going to subtract. So 9.62 minus 5.14. That's giving me 4.2 meters per second. Okay, so that's our final. So the final is going to act upwards. Then 4.5, we're being told that the ball is now replaced with a hard ball. Remember, the previous one was a soft ball. Hard ball of the same size and mass. Will the force on the sensor increase, decrease, or remain the same? Now, with a soft ball, we know that it will tend to take more time in contact with the sensor, whereas with a hard ball to take less time. So in this case, it's going to increase. Why? Because the change in momentum, let's say the hard ball takes more time. Takes more time. It's the soft ball that takes more time. You say the hard ball takes less time to bounce back compared to the soft ball. Okay. So this can be seen under the applications of the air bags of the cars, let's say in car crashes and things like that. So what this means that the force will be inversely proportional to the time, and hence the force will increase if the time is less. That is question number 5. Question number 5, the 5 kg body or box moves up and down at a constant velocity in the force F is applied. Okay. We want us to calculate the magnitude of the force F if the power that is used to move up the box is this. So we know that the average power will be the same as the force applied times the velocity. Okay. So we have our power, we have our velocity. So we're going to have the 57.6 is equal to the velocity, which is 1.2 F. Then divide both sides by 1.2. So 57.6 over 1.2. 57.6 over 1.2. And get to 48 newtons. Okay, so this is the magnitude of the force that's pulling this object. Then they want us to state the work energy theorem. So this tells us that the net work done, okay, the net work done is equal. The net work done, let's say by net force, by the net force is equal to the change in energy, which is equal. Okay, so if that is true, then they were telling us that the box now slides down this. So still, since the velocity is constant, which means even the force is kind of constant. So if the coefficient of the kinetic friction between that is this 0.25, calculate the velocity at point C using the energy principle on it. So it all depends on how you want to approach this question. Remember, at point B, this object or this box will have mechanical energy. Okay. We have mechanical energy, which is a combination of the kinetic as well as the gravitational potential. And then at point C, we're just going to have the EK to be maximum, since there is no height. So the gravitational potential will be a 0. That's my argument. And remember, energy in any sort of system will always be conserved. Energy will always be conserved. So what do you think? What do we think? Okay, so saying the work net, W net is equal to the change in kinetic energy, which I will just say EK plus the EP. The change in EK and then the change in EP. So we know that our work done is given as F times the displacement. So we have our power, we have our velocity. So we're going to have the 57.6 is equal to the velocity, which is 1.2 F. Then divide both sides by 1.2. So 57.6 over 1.2. 57.6 over 1.2. And get to 48 newtons. Okay, so this is the magnitude of the force that's pulling this object. Then they want us to state the work energy theorem. So this tells us that the net work done, okay, the net work done is equal. The net work done, let's say by net force, by the net force is equal to the change in energy, which is equal. Okay, so if that is true, then they were telling us that the box now slides down this. So still, since the velocity is constant, which means even the force is kind of constant. So if the coefficient of the kinetic friction between that is this 0.25, calculate the velocity at point C using the energy principle on it. So it all depends on how you want to approach this question. Remember, at point B, this object or this box will have mechanical energy. Okay. We have mechanical energy, which is a combination of the kinetic as well as the gravitational potential. And then at point C, we're just going to have the EK to be maximum, since there is no height. So the gravitational potential will be a 0. That's my argument. And remember, energy in any sort of system will always be conserved. Energy will always be conserved. So what do you think? What do we think? Okay, so saying the work net, W net is equal to the change in kinetic energy, which I will just say EK plus the EP. The change in EK and then the change in EP. So we know that our work done is given as F times the displacement. If displacement can be, let's say, delta X, and then the cos of theta, because that will be now the work done by the gravitational force. This is equal to the change in X is going to be a half m v final squared minus a half m v initial squared. And then the EP is going to be mgh final. Okay. And then the mgh initial. Something like that. Now we know that the force was 48. But remember, this F is for the frictional force, the work done by the frictional force. Because if you look at the free body diagram of this thing, I don't want to use those things of the free body and the forces and so on, but we can also use that and get the velocity. Okay. So let me stick to this. So we know that the frictional force is mu mg cos of theta. Okay, so our mu was a 0.25. Okay, times now the mass of the body, which is 5 times 9,8 times the cos of 32. Okay, that is just the F. Now the displacement, I do not know it. Okay, I don't know the displacement, but I can get it. How? Since I know this is my H, and then this is my 32, I can use the sign. We know that the sine of 32 is equal to the opposite, which is 1,6 over the hypotenuse, which is BC. So which means BC is going to be 1,6 divided by the sine of 32. What does it give me? It gives me 3, something. Let me just do that right away. So my displacement, okay, we get to 1,6 over sine of 32. And then we multiply by the cos of theta, which cos of theta is like cos of 180 since friction is in the negative direction. So when I simplify this, remember this is just the left-hand side. So 0.25, okay, times 5 times 9,8. The cos of 32, okay, times the 16 over the sine of 32, and then the cos of that. I'm getting a 313,665. Okay, but that is negative. Then when I look at the right-hand side, let me look at the B case. It's going to be a half. The mass is 5 into my V final, which I don't know, minus my V initial. What was the V initial? It was 1,2. And then when I look at my EPs, the mass is 5, the gravity is 9,8, the height is 0. Okay. Then I'm subtracting the 5 times 9,8, and then the 1,6. So 5, 9,8, and then the 1,6. So when I simplify this, I'm having 5 over 2 VF squared. This is out. And I open this, what is 1,2 squared times 5 over 2. That's gives me 3,6. So minus 3,6. Then minus 5 times 9,8 times 1,6. That is 78. Okay, so this is what I'm having by my right hand side. This is what I'm having by my left hand side. So now it's time for me to compare the two sides. So 5 over 2 VF squared minus, okay, this is 3.6, I'm getting 82. So minus 82 is equal to the 3,13,665. Okay, so 313,665. So 32 multiplying by 2 dividing by 5. I'm getting that. And then I'm getting 9,6. Doesn't make sense for me. Did I do something wrong? We have a visit this and it's let's see if I did something wrong, something wrong, something. That's calculus. It is a 1 minute. We said 5 times 9,8 times 1.6. That is 78. Okay. The 0 is out. 1,2 squared times 5. We get to 3.6, which is 5. And we have a half of that. So which means divide that side. Okay. So from the follow through, let me just go back to my previous pattern, which is 0.25 times that. Which is that. So my correspondences are still fine. It's 5 over 2 VF squared minus the 80. They divide both sides. No, not the 82 first. The 82. Dividing by 2 and dividing by 4. That's okay. I'm just going to ignore the sign here. Make it positive. This is going to be so it's 313,665 minus 82. I'm getting the 231,668 is equal to 5 over 2 v squared. And I'm dividing this by 5 over 2. Okay, I'm getting 92. And when I find the square root, I'm getting 9.6. Okay, 9.63 meters per second. All right, then question number 6. They're telling us that in the diagram ABC below, the wave patterns are shown for the sound. So this is A, this is B, and then this is C. Can we define the Doppler effect? So we know that the Doppler effect is just the apparent, okay, the apparent change in the frequency that is received by the listener as a result of the change in the velocities and so on. Okay, but alternatively, we could just put it as the apparent change in the frequency or pitch of sound as detected by the listener because of the sound and the listener having different velocities. Okay, so that is that. Then 6.2.1 for questions this, we must state A, B, C for each. Okay, so where is the source stationary? Okay, I think it's option A because there is no change. We're not seeing this decrease or the increase and so on. So A, source is stationary. So when is the source moving away from the observer? So when you're moving away from the observer, what happens? The wave increases. So I'll go for C. And then you must give a reason for 6.3.2. So the frequency, okay, saying the frequency decreases. Or you can tell us that the wavelength increases, because this point will be the source. So this distance is increasing. So the wavelength increases, the frequency is decreasing. Then 6.3, they're telling us that if an ambulance that is moving right from the observer at this speed, and the frequency of the siren that is heard is at this frequency. I feel the frequency of the observer with the speed of air is that an ambulance is moving away. So one thing we know about the Doppler formula is that the frequency of the listener is equal to V plus minus V of the listener over V plus minus velocity of the source times the frequency of the source. Now, since the ambulance is moving away and the listener is stationary, okay, moving away from one side at the speed. So that's 340 over 340 minus. It's going to be minus or a plus? Because an ambulance is moving away from one side at this speed. Also, this has to be a plus so that we have a smaller object. Then multiply by the frequency of this source, which is 900. Okay, so 340 over 340 plus 25 times the 900, we get to 838.36. 838.36 hertz. Okay, then the hydrogen spectrum line from the sun has a wavelength of this. The spectrum line of the nearby star has a wavelength of 657. What can be confident about the relation of the starting relation to the sun? Okay, so we can see that the wavelength of the spectrum lines of the hydrogen atom from the star is longer. Okay, the wavelength is longer because this is 656, this is 657. So the star has a longer wavelength than the hydrogen atom of the sun. So which means this is going to be a redshift, and this simply means the star is moving away from the sun. Okay, question number 7. Question number 7. An investigation was carried out to show how electric field varies at this distance with positively charged field. To achieve this, positive charge Q was varied and so on. So the following table. So you have the charge in nanocoulomb and then the electric field. Okay, then define the term electric field at a point. So this is the force. Okay, the force that is experienced a unit positive charge at that point. So when you check out the videos of electrostatics, you get that definition or the definitions. Then they want us to draw the electric pattern for positively charged. So when it is positively charged, we expect the field lines to be moving out. Okay. Remember, these field lines should never cross. So that is that. And then 7.3, they want us to plot a graph of P versus Q. With the graph we have the P versus Q. So I'll just try to put that sketch. There's a graph page. Let's say 1, 2, 3. I'm just gonna use 2, 4, 6, 8, 10, and so on. Then here I can use transit. It makes sense. 10, 20, 30, 40, 50, and so on. So we know that 1 is with a 4, which is somewhere there. And then 4 is going with 16, which is slightly below. And then 8, this is 8. It's going to go with 42. It's slightly above. 14 or 11 is slightly above 44. And so on. So just plot the points, but you're going to notice that these points are not forming like a normal straight line. So it means you need to draw a line of best fit, a line where all the points are close to that line. Okay, all the points may not pass through the line, but all the points must be close to the line. So that is the graph that will be needed for you to get the formats. And then you need to use the graph only to answer the question. Identify the controlled variable. So in this case, the controlled variable, if you have to look at the graph, remember it is the E versus the Q. Okay, E versus the Q. Now it's the other way. This is the Q, that's the E, not the E versus the Q. So the only thing that is controlled here, because they said the distance is varied and the distance away from the positive charge, fixed distance. So that is the controlled variable. So the distance. Okay. And then the dependent is the E, the electric field. Remember, in any graph, whatever appears on the y-axis becomes the dependent. The x-axis, the horizontal, is always independent. And then determine the fixed distance between the charges. So in this case, we can find the gradient which gradient will be the E over the Q. Remember from our E K Q over R squared. So which means this gradient must be equal to K over R squared. That's what I'm seeing from this formula. If I can get E over Q, which is the gradient, then I have. So we need to find the gradient. So with the gradient, we can find, I don't know, we can use the gradient, so we can even just gradient with this graph of mine that's not accurate. It's going to be a bit weird. But no, it's fine. We can get any points. Let's say I'm using the first point and then the last point. Okay. First point and then the last point. Okay, so I'll try to use my first and last values, okay, to get the gradient. So that's going to be 55 minus 4 over 14 minus 1. This must be equal to K, which is 9 times 10 to the 9 over R squared. Okay, so 55, okay, which is going to be a 51 over 15. When I do my cross multiplication, that's going to be 51 R squared is equal to 9 times 10 to the 9 times 13. So R is going to be the square root of 9 times 10 to the 9 times 13 over 51. Let's see, 9 times 10 to the 9 times 13 over 51. And 13 higher becomes 1. Did you do the correct things? Because it's going to point us. It's going to point us. I'm getting 4, 7, 8, 9, 6, 4, 9, 4, 8. Let's go back to the graph and see. Because this was the nanocoulombs. Okay. And then this is a K, which is like a Q. Okay, we can now see. So nano and kilo. So the Q is times 10 to the negative 9. And then this is times 10 to the third 2. So when I simplify that, okay, I should change a whole lot of things. This and that. It's gonna give me now the 51 times 10 cubed. But why am I doing that? Just say 10 cubed. And then this is times 10 to the negative 9. Let me just include it there. Times 10 to the negative 9. And then times 10. Yeah, perfect. So I'm getting 0.04789. I'll just make it 9 meters. Perfect. So guys, that's the answer. Then question 8, a battery in the circuit below has an EMF of 6 and internal resistance of that. With S1 and S2 open, can we give the reading on V2? Where is V2? This is V2. So V2 is connecting the EMF, which has to be 6 volts. Okay, it's connecting to the battery. Then with S1 closed, if this is closed, it means the current is now taking this route, passing through R and then this. Okay, telling us that the reading that was recorded is 0.75 for the ammeter. explain the meaning of this. Okay, so in a charge of 0.751, I don't know, are they asking us to explain what current is? Okay, so you can say the charge of 0.75 coulomb traveling in 1 second, because that's what current is. Then with S1 closed, you want us to calculate the internal resistance. Okay. So we can use the EMF formula. Okay, which EMF is I into R plus small r. We now know the current is 0.75. Our EMF was a 6, 0.75. Do we know the external resistance? No, that's what they want us to do. The internal resistance, they give us a 0.4. Divide both sides by 0.75. 6 divided by 0.75, I'm getting 8. And then 8, I subtract 0.4, I'm getting 7.6. Okay, same divide. 8 minus 0.4 will get that. So 7.6 ohms. Then they want us to get the value of R. Now remember, with capital R, still S1 is closed on. With this capital R, it's more like a parallel combination. So what I'm going to do, I'm going to combine. Let me just write it in. So I'm combining this and that. So let me combine the 3 and the 1 to give me 4, so that I have R and then a 4 ohm. Okay. These combined together must give us the 7.6 ohms. Since it's parallel, I can use the product and sum. So product over the sum is giving me the 7.6 ohms. My product is going to be 4R over 4 plus R must give us 7.6 ohms. If I try to cross multiply 7.6 times 4, I'm getting 30.4 plus 7.6 R must give us 4 R. It's the product over the sum. Why am I getting something different? Is it going to make sense? 7.6 minus 4 is 3.6. 30 divided by the answer, you get to 8 point something, which doesn't make sense. Let me see. Oh, sorry guys, sorry. We also have another 4 ohm. There's another 4 ohm there. We are such honestly. Was not making sense. So let's see. So we have we said product over the 4 plus R. Now plus this 4 ohms must give us the 7.6. Move the 4 that side. 4R over 4 plus R must give us the 3.6. Cross multiply 3.6 times 4, I'm getting 14.4 plus 3.6 R. When I move the 3.6 that side, I'm going to end up with 0.10. 0.4 R is equal to 14.4. Divide by 0.4, divide by 0.4. So my R is going to be 36 ohms. So this R is 36. So what I did, I first combined these two since they're in series directly and got the 4 ohms. And then since these are two resistors in parallel, we say the product over the sum, we give you the effective resistance of just the pair of combination. Okay. Alternatively, what someone can do, if you can have the 7,6, okay, we subtract this, then I'll be left with 3,6. So which means this pair of combination is equivalent to just 3.6. Oh, makes sense. Then 8.4 S1 is now open and S2 is closed. How will the power dissipated by the 4 ohm change? Okay. So if this is open and this is closed, which means the power will just take this switch. Remember, this whole thing is a 3,6 ohms combined. This is a 4 ohm. Now, if this is off, which means we only have 4 ohms within the circuit. So the total resistance will be 4 ohm, and then that internal resistance, which is always a must. So one thing we have to do, we have to say that the resistance is going to increase. That is 45. Okay, it will increase because the external resistance has decreased. Okay, so the power, we're saying the power increases because the external resistance has decreased. Then you can tell us, or you can use the formula of power being directly proportional to I squared R. Okay. Then 8. They are telling us that 12 learners conducted an investigation to determine the internal resistance of the battery, the circuit below is that. Okay. And then a graph was plotted. From the graph, can we deduce the EMF? So EMF is basically where the graph normally starts. As long as this potential difference, that means the current. So this graph is starting from 4.5. So the y-intercept, that is the EMF. Then calculate the internal resistance. So internal resistance will always be a gradient of this graph. The gradient, because if this is potential difference in the current from EMF is equal to 5R. If we get the EMF over the current, we end up with the internal resistance. So the gradient, so we consider the change from there up to there is going to be 4.5 negative. Because I'm getting the negative of positive. So whichever you look at it, you can have 4.5 to 0 minus 4.5, which is negative 4.5. Then I'm dividing it by from 0 to 7.5, which is positive. So I'm going to get a negative answer. Why? Because when you consider this line is having a negative gradient. So it's negative 4.5 divided by 7.5, that's giving me negative 0.6. So which means our internal resistance is 0.600. Question number 9. Study diagram below and answer the questions that follow. So what type of generator is shown in the diagram? You must motivate to answer by referring to the specific names of the components. Okay, so this has to be, we have this and this, and then we are calling it a generator. So it's an AC generator. Okay, number one, it has two slip rings. That's number one. And then number two, it has a handle, which handle will be turned for you. Okay. So if it was connected to, let's say, power supply or something, then it will definitely reduce it. Then indicate the direction in which the current will flow in section A. So since we've seen the field to be moving in this direction, we want us to get the current. So using the correct right-hand rule or the correct hand rule, we can see that it's moving that direction. So it's going to be B2. It's going to be B2. And the 9.3, the following graph was obtained from the generator. How many rotations are we having? So it's seen that from here up to here. Does that make sense? No, from here up to here. That's one rotation. Okay, the trough, and then the crest, one rotation, and then this is a half. So we can say that it is 1.5 rotations, or 1.5 times. And then they want us to define root mean square, RMS. Okay, so root mean square current is saying that is the alternating current, which produces the same amount of energy as the equivalent of the DC. This is saying is the AC current that produces AC current, which dissipates, or we can produces same amount of energy. And amount of energy as the DC. Then calculate the average power. So with average power, remember we need to know the maximum power. Okay, so if we have I RMS, we shall get our I max divided by the square root of 2. And we know that power can be given as I squared I. Okay, we have the resistance, or we need the current. In the question, they told us what is going on. And we can see from the graph that the current is 15. So what we're going to say, we're going to convert this maximum current, which is 15, over the square root of 2. I'm going to square this, and then I'm going to multiply by the equation. So it's saying 15 over square root of 2 squared times the 30. That's giving me 3375 watts directly. So if you have decimals, because of being this separate and rounding it up, no problem, but the answer should be close to the same. The 9.4 is a hair dryer, not a chair dryer. A hair dryer that is rated at 2.2 watts. Okay. At 240 volts. Then assume that the hair dryer is secure resistor, that is the maximum current that flows through the hair. So what we can see then is that we have the power. Okay, so we know that. Let me just choose a different color. Okay, the P average is I times P. Now, what is our power? It's 2.2. What is our current? What is our current? Our current, we don't know, but we have the voltage, which is 240. I'm just going to say 240 I. Then when I divide 2.2 by 240, I'm getting 9.16. 9.1667 amps. Question wants the maximum current. So for us to get the maximum current, you must get the IRMS times the square root of 2, which means my answer of 9.167 times the square root of 2, I'm getting 12.196 amps. That is 9.5. In question 10, diagram below shows a photo tube that was used to demonstrate the photoelectric effect. Demonstration was carried out by shining a light from a red, green, ultraviolet into the surface. Okay, they gave us the demonstration number, the color of the light, and then the ammeter reading. Okay. Can we explain what is meant by photoelectric effect? So we know that this is just a process by which electrons, okay, so electrons are ejected. And so electrons are ejected from a metal surface. From a metal surface after a light of sufficient frequency, and a suitable frequency is incident on the surface. So in other words, you first shine the light on the surface, and then electrons will come off, but the light has to have sufficient energy. And then explain why there's no reading on the ammeter when the red light is shown on. So we know that for red light not to show, we know that the frequency is low. Okay, so the frequency of the red light is lower. The frequency of the red light is lower than the minimum, which minimum is normally known as the threshold, the minimum frequency needed. Then for the following statements, use increase, decrease, and so on. So the kinetic energy of the photoelectrons dash when an ultraviolet is shown in the surface. So in this case, we're just going to say increase. Okay, and ultraviolet, and the reading is a yes, so it increases. Then the reading on the ammeter dash when the green light. So green light is also a yes of higher intensity. Explain the observation. So since the ammeter reading is a yes, which means this increases also. Ammeter reading increases when the green light is of higher intensity is shown. We need to explain that. Okay. So what you need to know is that with intensity increases the number of electrons, or the number of photons, not electrons. So the number of photons will increase by unit time. Okay, so if the number of electrons are increased by unit time, which means the rate at which they will be striking the metal surface is going to increase. Hence, the number of electrons that are leaving the surface will also increase. Then 10.4, they're telling us that the cathode is made up of copper with a work function of this. Okay, so which means W naught is 3.52 times 10 to the negative 19 joules. If ultraviolet with a wavelength of 390 times 10 to the negative 9 meters was used during the demonstration, calculate the speed. They want us to take the beat. Now we know that E, the energy, must be equal to W naught plus the EK max. Okay. So this E can be given as H lambda over C is equal to our W naught. Plus we can still take the EK max, and then we can do the substitution. So the value of H is always 6.63 times 10 to the negative 35 in this table. Times the wavelength, which is 390 for the seed 390 M. Why missing waiting fish? I think I've messed up this formula. Messed up that thing. Let me just manage. It's HC over lambda. Sorry guys, I apologize. It's HC over lambda. HC over lambda. So 3 times 10 to the positive 8 over now the 390 times 10 to the negative 9, since it was number. This must be equal to the work function that they gave us. Its work function was 3,52 times 10 to the negative 19 plus my EK max, which I don't know right now, but I'll sort it out. Let me first figure out what is this and that. So I'm going to move this to the side. Okay, so I have 6,63 times 10 to the negative 34, that's 7. Okay, I'm multiplying by 3 times 10 to the 8, that's the speed of light, over 390 times 10 to the negative 9. Okay, I'm subtracting 3,5 times 10 times 7 to the negative 19. So I'm getting 16 times 10 to the negative 10. Now I know that E mass, EK mass is a half times the mass of the axis of the electron, which is 9,11 times 10. 9,11 times 10 to the what? What is electron mass? Negative 31. Okay, so negative 31 this squared. Now I'm going to divide both sides by that. So divide by 0.5 times 9.11 times 10 to the negative 31. So getting a big answer. It's really big. It's really big. Okay, but I need to find the square root of the answer. Square root of the answer, which is the velocity, is giving us the big answer. Okay, so if I find, I'm getting 5, 9, 2, 6, 7, 3, 8, 9, 7. 1, 2, 3, 4, 5. So it's 5.9 times 10 to the 5. That's what I'm getting without the rounding offs and stuff. This is what I'm getting. Okay, so paper was out of 153 hours, okay, just as we discussed in the prediction. Okay, so let's look at the multiple choice. So they are telling us we have various options that have been provided. We just need to choose one. 1.1. Two forces, F1 and F2, are applied on a box that is lying on a frictionless surface as shown below. The magnitude of F1 is greater than the magnitude of F2. Okay, so what will happen to the box? The box will accelerate to the left? No. The box will accelerate towards the right. That is going to be correct. Will it move at a constant speed towards the right, move at a constant speed towards the left? So I'll go with the option of accelerating towards the right. Then 1.2, they're telling us that a 5 kilogram iron shot put and a 10 kilogram aluminium shot put with the same diameter both fall freely from a shelf that is 12 meters above the ground. So if we are to ignore the effects of friction, when the shot puts are 3 meters above the ground, the shot puts will have the same momentum? No. We can't go for momentum because momentum will be dependent on the masses, and since the masses are different, we cannot have the same momentum. Will they have the same kinetic energy? Kinetic energy depends on mass also, because it's mv squared. Potential energy depends on the mass, so it cannot be the same. So in other words, only option that is reasonable is option B. Acceleration needs to be the same, regardless of the mass or the height. Okay, 1.3. Two asteroids S and T are having masses m and 2m respectively. They are on the course for a collision. Okay? So if the magnitude of the acceleration on S is a, then the magnitude of the acceleration on T is. Now, for as long as the collision is going to take place, the Newton's third law will have to apply. So the F net on this case is going to be MA. And then the F net in this case must be 2m multiplied by A. Let me just call that AS and AT. But it's just the same acceleration, so let me just keep it the same. Just A and A. So for me to get this acceleration of T, the force that will be acting will be equal, but just in the opposite direction. So MA is equal to 2m80. Then I make 80 the subject. So the m will cancel the m, and then 80 is going to be a over 2, which is a half of a. And option B is going to be my option to go with. And then 1.4. A sound source approaches a stationary observer at a constant velocity. Which of the following describes the observed wavelength and the frequency from the sound source as it approaches? So the observed frequency, number one, for as long as the source is approaching, it must be greater. Okay, so we're going with option A and option D. Now, from V is equal to F lambda, or C is equal to F lambda, we can see that frequency and wavelength are going to be inversely proportional. So if one is greater, then the other one has to be less. So option D would be the best for that. And then 1.5, they're telling us two objects, M1 and M2, with a distance r apart, experience a force F. The mass M1 is now doubled and the distance is halved. The gravitational force between M1 and M2 now is. So from Newton's law of universal gravitation, we know M1, M2 divided by r squared. This is the original. Now, if we apply the conditions, it's going to be G 2M1, and then it's going to be M2, then divided by, say, the half r squared. So that's going to be 2gm1 m2 multiplied by 1 over 4r squared. When we simplify 2 divided by a quarter, that must give us 8. So which means it's going to be 8 times the force, which is option D. Then 1.6. If we have an object that is thrown vertically downwards towards the ground from a height h with a velocity v, the object strikes the ground and bounces upwards. Then it's caught when it reaches the maximum height. So at maximum height, the velocity has to be 0. So this one, I'll consider it to be an option. This one, I'll consider it to be an option. these two are out because we are seeing that after bouncing, I'm assuming this is the maximum height. Okay, or this is the maximum height, but then it just continues. Maximum height, but then it continues. So B and D, they're out. Now, when I look at the direction of the velocities, if a ball or an object is thrown downwards, we expect the velocity to increase and not decrease. So option A is going to be the best because velocity is increasing. And then the bouncing, and then it gets to 0. So I'm going with option A as my best option. And then 1.7, the crate is pulled up a slope. Which of the following forces will do 0 work on the object? The pulling force, this one is going to do work. The normal force, since it's acting perpendicular, it might not do work. Frictional force is going to do work. Gravitational force is going to do work, since there's a component of the gravitational force. So I'm going with option B, which is the normal force. Then 1.8. Okay, 3 identical spheres X, Y, Z are placed together in a triangular arrangement, each touching each other. The spheres are then moved back to their original positions. So for us to get the net or the charge on each one, remember they must all have the same charge after the separation. So I'll get the total -5. Okay, so that's a -5. What's happening to my pen? Okay, so -5 plus 0 plus 2. This gives us a 3 negative. Then divided by 3, we get a -1. So A is the best answer for that. Then 1.9. A positively charged object has fewer electrons, yes, but compared to what, neutrons? No. It has fewer protons. This is wrong. It has fewer electrons, yes, than the protons. This one makes more sense. Okay, if the electrons are more, then the object will be negatively charged. Okay, so I'm going with option C because it's the only one that makes sense, because this one more protons than neutrons, no, can only have more protons than electrons. All right, then 1.10, the minimum resistance that can be acquired from a connection of two 4-ohm resistors. So when we have two 4-ohm resistors, remember the connection can either be in series or in combination, or in parallel. Okay, so if I look at the series combination, I'll have a 4-ohm and then a 4-ohm. So a 4 plus a 4, that will give me 8 ohms. That is maximum. Okay, and then if I look at the parallel combination, I'll have my product, which is 16 over the sum, which is 8, and then I'll have a 2. So I'm going to go with option B. Okay, because we said the product over the sum. So it's 4 times 4 over 4 plus 4. 16 over 8, it's 2. This is the smallest resistance that we can have. Okay, so that is how my number 1 would have gone according to the way I understood the questions. Okay. Then question number 2. A block M, that is 10 kilogram, is connected to block small m with a 2 kilogram with a rope T of negligible mass. Okay, there is a pulley here. Okay. Both blocks are at rest, and then the slope is 30 degrees with the horizontal. The frictional force cannot be ignored. And then they want us to define the term normal force. So it's a force with which you can say a surface, a force which a surface exerts on an object, okay, with which we can say it is in contact. is in contact and perpendicular to the surface. So something like that. That could be the definition of a normal force. And then they want us to draw a labeled free body diagram of all the forces acting on the 2 kg. So when you look at the 2 kg, it's just the tension and then probably the weight. So we're not going to waste time there. We're going to say this is tension and then that's the weight. Then they want us to calculate the frictional force needed to keep the blocks at rest. The frictional force needed to keep the blocks at rest. Okay, so what I'm going to see, I can look at it block by block. Okay, if I look at T, I know that I'm going to have the frictional force. I don't know which direction should I assume the object is moving. So since the 10 kg is bigger, I'll assume the direction of motion is this side. So I'll have Fg parallel, then I'll have my frictional force there. Okay, let me try to make sense out of this. So when I look at the first body of the 2 kg, okay, so we're gonna say that with the 2 kg body, with tension, let me start with net force is equal to MA. Okay, so tension minus the weight must give me the mass and the acceleration. But the objects are at rest, which means they're not gonna move. So our acceleration has to be 0. So which means the tension is equal to the weight, which weight is gonna be 2 multiplied by 9,8. Okay, so when I punch that into my calculator, I'm getting 19,6 newtons. Then let me also consider the 10 kg body. So what we are saying is that we are assuming that the object is moving downwards. So which means the F net is going to be the Fg parallel minus the frictional force minus the tension must give us the MA. I don't know if that is going to make sense. So we're saying the Fg parallel minus the tension minus the frictional force must give us MA. But our MA will be 0. Then, since we're looking for the frictional force, we can just transpose it that side. Fg parallel is the same as mg, the sine of theta minus the tension is equal to the frictional force. The mass is 10 times 9,8. The sine of 30, I'm subtracting the 19,6. Why am I saying 19,n? Okay, I'll punch this into the calculator. 10 times 9,8 sine of 30 minus 19,6. This gives me 29,4 newtons. So this is what I'm ending up with as my frictional force. Okay, just to keep the object without moving. Okay, then 2.4. They're telling us that the rope snaps. Okay, and then M decides to slide down. The kinetic frictional force is 25 Newton. Okay, since there is no tension, the frictional force is going to be that much. Now they want us to draw a free body diagram on this 10 kg. So we can see that there is no tension. The friction is going to act upwards, and then we're only going to have the Fg parallel. We're going to have the weight, and then the normal force there. So how many marks is it? It's 4 marks. So you can have approximately 4 forces. Okay, so I'll just, let me put it this side. This is 2.4.2. 2.4, it's 0.1. Okay, so we said frictional force there. We said Fg parallel. It's saying the weight there. And then that's going to be our normal force. So that should be our free body. Then for 2.4.2, they are asking us to calculate the magnitude of the acceleration. Okay, so we need to get the acceleration with which the object will be moving downwards. So what I'm going to do is I'll still consider more or less the same thing and look at my free body and say that my F net is equal to, so I'll have my Fg parallel minus my frictional force must give me the mass multiplied by the acceleration. So mg sine of theta, my frictional force, we already have it, must give us the ma. I'll substitute, so 10 times 9,8 sine of 30 minus the 25 must give us the mass, which is 10, and then the acceleration a, which I don't know. When I substitute, when I punch these numbers, 10 times 9,8 sine of 30, then I'm subtracting 25, I'm getting 24 on the left. Okay, is equal to 10a. Divide both sides by 10, which means our a is 2,4 meters per second squared. Okay, so that is what I'm getting for 2.4.2. And then we move on to 2.5. They're telling us that block M, the small block, just takes a half of a second to reach the ground. They want us to get the final velocity. Okay, so what are we going to do? So they're telling us that the time, this is 2,5.1, is 0.5 seconds. What do they want? They want us to get the final velocity, Vf. So V initial, I'm going to be 0 initially when it was just hanging and dangling. Okay, so I'll use the V final is equal to V initial plus acceleration times delta t. So my V final is going to be 0 plus my acceleration now is going to be under free fall, which is going to be 9,8 multiplied by 0,5. And that's going to give me 4,9 meters per second. That's what I'm getting in that case. Since it's after the snapping, the object will just fall under the gravity. So that is 2.5.1, and then 2.5.2. How would the final velocity of M be affected if the mass was doubled? Okay, and dropped from the same height? Increase, decrease, or remain the same? So in this case, I'm going to go for remain the same. Okay, why? Because it's just more or less the same as the first question we answered under the multiple choice. Okay, so I'm gonna say it's just gonna remain the same, and the reason for this is that our velocity is independent of the mass. The velocity is independent of the mass, and the motion of the object will entirely be affected, I'll say, by only the gravitational force. Gravitational force. So in other words, it will be some sort of a free fall. Okay, so that is question number 2. Question number 3, they're telling us that the Curiosity rover was dropped from 125 kilometers above the surface of Mars The mass of the Curiosity rover is this much, and then the mass of Mars is this. The radius of Mars is 53.25% that of the Earth. Then they want us to state Newton's law of universal gravitation. So we know that objects in the universe, they exert a force between them that is directly proportional. Let me just write it this side. So it's saying 3.1. So the force between two objects in the universe is directly proportional to the product of the magnitude of their masses, and then inversely proportional to the square of the distance, between their centers. Okay, something like that. That would be universal law of gravitation. And then 3.2, they want us to calculate the weight of the Curiosity on Earth. So we know that weight is given as mass times gravitational force. We know that the mass is 899. We're multiplying by 9.8 because the gravity on Earth is 9.8. So 899 times 9.8, that gives me 8810.2 newtons. Okay, so saying this, 2 newtons. That is 3.2. Then 3.3, they want us to get the gravitational acceleration on Mars. Let me just write it. So we know that G is equal to capital Gm over r squared. Okay. So what is the value of G? G is given as 6.67 times 10 to the negative 11. What is the capital M? That is the mass of Mars, which is 6.42 times 10 to the 23. And now when it comes to the radius, we need to determine the radius of Mars. It told us it is 53.25, that of Earth. So for R, I'll say 53.25% multiplied by the radius of Earth, of the Earth. So I have to check the formula page. From the formula page, we can see that the radius of Earth is 6.38 times 10 to the 6. 6.38. Okay, so 6.38 times 10 to the 6. Okay, so what does this give us? 53.25% of 6.38 times 10 to the 6. So I end up with 3397350. Let me just use it the way it is. Okay, I'll substitute 6.67 times 10 to the negative 11 multiplied by 6.42 times 10 to the 23 over 3397350, but then I have to square this. Okay, so when I punch this into my calculator, times 10 to the negative 11 multiplied by 6.42 times 10 to the 23, dividing it by 350 squared. It's giving me 3.71. That's going to be meters per second squared. So this is the gravitational pull or the force acceleration. Okay, then 3.4. Would the mass of the Curiosity be different on Mars than on Earth? Yes or no? The answer is a no. And what is the explanation? So mass is always constant. Mass is constant, but weight will change. So you can just tell us that the weight is dependent on the gravity and not the mass. Mass is independent of the gravity. Remember, mass is just a measure of content that an object is having, whereas the weight is the product of the mass and then the gravity. So if the gravitational force is different, which means even the weight will change. So that is question number 3. Question number 4. They're telling us that a learner that is standing at the bottom of the building throws a ball A upwards at a constant speed, at a speed of 11 meters per second, and ball A reaches the maximum height T. Then after 0.72, another learner standing on top of the roof. But you're already on the roof. Why are you on top of the roof? Standing on the roof of the building, throws the ball B upwards. The two balls reach point T at the same time as shown in the diagram. All right, they want us to define what free fall is. So free fall is just a motion. Okay, it's a motion. We can say during which the only force acting on the object, is the gravitational force. Okay, so that is free fall. And then a projectile. So projectile is an object. Okay. Which object has an object which has an initial velocity. Okay. And this object will move, we can say moves under the influence of the gravitational force. Only. So projectile is there, and then free fall is there. Okay, then 4.2. They want us to determine the time taken by ball A to reach the maximum height. So what do we have? We have the V initial, which is 11. You know that our acceleration is going to be the G, which is 9.8. We know that the V final is going to be 0, since T is the final point. They are asking us to get delta T. Okay? So by looking at the information I have, I can use the first equation. Okay. First equation, whereby I will say V final is equal to V initial plus A delta T. Just write the equation, you'll get a mark for that. So when I do my substitution, we know that our A is going to be the G. So V final is a 0, V initial is 11, plus, I'm going to say negative 9.8 multiplied by T, or delta T. Then I can transpose the 9.8 to that side, is equal to 11, so delta T is going to be 11 over 9.8. Okay, with my calculator, I'm getting 1.12 seconds. All right, then 4.2.2. They're asking us to get the initial velocity of ball B. So the fact that ball A takes 1.12 seconds to reach the maximum, it simply means that ball B is going to take a shorter time. So the time for ball B is going to be 1.12 minus the 0.72, since they're going to reach the maximum height at the same point. So 1.12 minus 0.72, I'm getting 0.4 seconds. Okay, question wants the initial velocity. So V initial is what I want, V final is 0, my delta T is 0.4. So I can still use the same first equation. So V initial plus A delta T. So 0, that's V initial, plus gonna be negative 9.8 multiplied by 0.4. So I can move, no, let me just keep it there. So 9.8 multiplied by 0.4, that gives me 3.92. Move it that side, which means VI is 3.92 meters per second. Okay, then 4.2.3. They want me to get the height of the building. So what I can do for the height of the building, I can decide to get the displacement that the object A traveled. Okay, so the maximum height of A, and then I also get the maximum height of B, and then I subtract it, and I'll have my height of the building. So 4.2.3, I'll do it this side. So I'll see the displacement of A. I can use VI delta T plus a half A delta T squared. Okay. So my V initial was 11. My time was 1.12 plus a half. I'm going to use negative 9.8 multiplied by 1.12 squared. Okay, and I punch this into my calculator, I'm getting 6.17 meters. Then I'll do the same with B, which is V initial of B multiplied by delta T plus a half A delta T squared of B. So the V initial, we got it as 3.92. We are multiplying by 0.4 plus a half multiplied by negative 9.8 times 0.4 squared. I'm taking the upward to be negative. Okay, so when I punch this into the calculator, I'm getting a 0.78 meter. So the height of the building is going to be YA minus the YB. So 6.17 minus 0.78. I end up with a 5.39 meters. So that is question 4.2.3 and the entire question. That then 4.3. The following position time graph is given for the motion of the two balls A and B as described above. Study the graphs and answer the questions below. Okay, so ball A started from the ground and we said it reached point W, or it reached the maximum. So we are assuming this is our maximum point. So the maximum point was reached after 1.1 seconds. And then we saw that the maximum point for ball A is 6.17 meters. Even ball B reaches that height. But then the difference between the two, because it's going to be after 0.72, this one is projected. So the difference here is the 0.4 time it takes for this one to reach the maximum. Okay. And then the position, we say this one is at the top of the roof, on top of the building or at the roof. And then we say that height was 5.39. Okay, 5.39. Okay, so let me just punch those values down here. So my x is going to be 6.17 meters. Okay, my y, we are saying it's 5.39 meters. Okay, and then my z is 0.72 seconds, and then w is 1.12 seconds. So that is question 4. Question number 5. Okay, they are telling us that a wrecking ball is used to demolish an old building by smashing it. Okay, so this ball has a mass of 950 and suspended in air with a rope. They're at 3.5 meters above the ground. The ball is then released. So at the point of suspension, it's not moving. So our initial velocity is 0. The ball is at a height of h above the ground. Ignore that. Then 5.1.1 state the law of conservation of mechanical energy. So we can say that in an isolated system, the total mechanical energy, or the mechanical energy, is conserved or remains constant. All right, then 5.1.2, the ball swings and hits the building at a height h. Calculate the speed with which the ball hits the building using only energy principles. Okay, so when we are to use energy principles, remember, mechanical energy is conserved. So at a height of 3.5 meters, the ball is having EP max, and then the EK is going to be 0. But then at a height of 1 meter above the ground, the ball is having EP and EK, which must be equal to the EP max since there is conservation. What are they asking for? They want us to get the speed with which it hits. Okay, so what I'm going to do, let me get the EP max first, which is mass, gravity, and then the height. So 950 multiplied by 9.8 times 3.5. Okay, let me just combine the whole thing into the equation. Is equal to the EP at 1 and then the EK at 1. So which is 950 times 9.8 times 1 plus a half times 950 and then b squared. Remember, this is mgh, and then a half mv squared is equal to that. Okay, so my left hand side, we say 950 times 9.8 multiplied by 3.5. I'm getting 32,585. And then when I use 1 as a height, I'm getting 9310 is equal to 950 divided by 2 is 475. 475 is squared. Okay, so I need to transpose this that side. 32585 minus 9310. Okay, I end up with 23275 is equal to 475 b squared. So divide both sides by 475, and then let's take the square roots on either side. So 475 and then square root of that, which means our V, I'm getting a 7 meters per second. All right, so that is 5.1.2. Then 5.1.3, they're telling us that what happened? Okay. Okay, so the ball hits the wall and takes 0.1 seconds to stop and then rebounds. Calculate the magnitude of the force with which the ball hits the wall. So what we're going to do here is we can look at the impulse. Okay, so this is 5.1.3. You know that F delta T must give us the change in momentum. So since the ball is hitting the wall with this, so this is our V initial, and then our V final is going to be 0. Okay. So let's see, we're saying force is going to be the change in momentum over delta T. So that's the mass V final minus V initial over delta T. The mass was 950. I'm multiplying it by 0 minus that. It's going to be 0 minus 7, which is negative 7 over 0,1. Okay, so 950 times 7 divided by 0,1. I end up with 66,500. Okay, so that is negative 66,500 newtons. So it's just 6,500. What was the question asking for? Determine the magnitude of the force with which the ball hits the wall. So it's just in the opposite direction. Okay, so newtons. Okay, so that is 5.1.3. And then 5.1.4, write down the force that the wall exerts on the ball. So it's just going to be the same force. Okay, so we said it is 6,500 newtons. Then name and state the law. So it's Newton's third law that is used to arrive at this. And how do you state that? And say that when body A exerts a force on body B, saying that body B reacts by exerting the same amount of force. So exerts a force of equal magnitude, but in the opposite direction. Opposite direction. Okay, so that is how 5.1.4 will be answered. So Newton's third law, and then you state the third law. Then 5.2 are telling us that there is a grade 12 learner with a mass of 75 kilograms that is on a skateboard of mass 2 kilograms that is moving at a constant speed of this much east over smooth surface. There is a ball of 500 grams that is moving at that velocity west that is thrown to the learner. Then the learner catches the ball, and then the final kinetic energy after the collision is this much. Calculate the initial speed, 5 Mach. So what I'm going to do, since I know that kinetic energy is given as a half mv squared, let me start by getting the final velocity. Okay, so I'll have my 146 is equal to a half, then the mass of everything combined. So the learner, the skateboard, as well as the ball. Okay, so that's going to be 75 plus 277 plus, this is a half of a kg. So 77,5, and then bf squared. Okay, then I'm going to have my vf as the square root of 2 times 146 over 77,5. When I punch this into my calculator, I'm ending up with 1,94. So V final is 1,94 meters per second. But the question is asking for V initial. Then we need to apply the momentum, conservation of momentum. So I'll say mass of the learner, velocity of the learner, plus mass of the ball, velocity of the ball. These are initials. Must give us the mass multiplied by the V final. This is going to be now the combined mass of everything. Okay, so initially we had a 75 and then a 2, which gives us now a 77. The V initial was a 2. Plus, the mass of the ball was 0.5, but it is moving in the opposite direction, which is negative V. The mass of everything combined is 77.5 multiplied by 1.94. Then I need to do my subtraction, so I'm going to transpose this to that side. So I'm going to have negative 0.5V is equal to 77.5 multiplied by 1.94, subtracting 77 times 2. This gives me negative 3.65. Then I'll divide both sides by negative 0.5. Okay, and then my V is going to be saying negative 0.5 becomes 7.3 meters per second. So that is 5.2. All right, then question number 6. They're telling us that an object that is having a mass of 85 kilograms was initially at rest on the ground, then it's pulled vertically upwards at a constant acceleration of this much by means of a light rope. Ignore resistance, the mass of the rope, or any effects. Then they want us to draw a body diagram of the mass while it is moving upwards. So 6.1, we know that for as long as the object is moving upwards, there's going to be the tension, and then there's going to be the weight. Okay. And then 6.2, name the non-conservative force that acts on the mass. Okay, so we can go for drag or the resistance, but they told us we must ignore the resistance. Okay. And then any rotational effects. So we can go for the, what do you call that? All right, then 6.3. They're telling us to calculate the work done on the mass by the gravitational force when the mass has reached a height of 11 meters. So this is 6.3. So for us to get the work done, it will be the force, the gravitational force, multiplied by the delta x, and then the cos, I'll say 0. Okay. So our gravitational force is going to be the mass and then the g. So that's going to be 85 multiplied by 9.8 multiplied by the distance and then the cos of 0. Okay. Then when we multiply 85 multiplied by 9.8 times 11, that gives me 9163 joules. This is what I'm getting for 6.3. Then 6.4, state the work energy theorem in words. So we know that the net work done is equal to the change in kinetic energy. Okay. Then 6.5, use the work energy theorem. Calculate the speed at the height of this. 5 marks. Now, when I look at this question, remember this object is moving upwards. I can look at it as a projectile. Okay. So if I use that scenario, I might end up losing the marks, but I will get the same answer. Okay. So let me, what do they want? They want the speed when the object is at a height of 11. Now let me use the work energy so that I don't deviate from what we have. Okay, so this is 6.5. So what I'm going to do is, since I had a free body diagram, I can start by probably getting the tension force. I mean, I was given the acceleration of the system. I can look for the tension, and then look at the work done by almost everything there. So what I'm going to do, I'll say W net is equal to the change in EP plus the change in EK. Okay. But why do I need, no, there's no need of using this. I'll just use the change in EK. But for me to get the work net, I'll get the work that is done by the tension minus the work done by the FG. Should be equal to the change in the kinetic energy, which is going to be a half m v final squared. You can subtract the v initial squared, it's fine, but we already know that the v initial is a 0. Okay, so we need to get the tension first of all. So we're gonna say that F net is equal to MA. If I just focus on the body or the free body that I drew. So it's gonna be tension minus the weight should give us the mass and the acceleration. So which means my tension should be the mass acceleration plus the weight. So the mass is 85. The acceleration is 0.7. They said 5. Perfect. And then plus our weight, which is 85 times 9.8. Okay. So 85 times 0.75 plus 85 multiplied by 9.8. I'm getting 896.75 newtons. Okay, so initially, now I need to get the work done by this. Okay, so it's 896.75 multiplied by the distance, which is 11, and then the cos of 0, since it's moving the same direction. Okay, that's gonna be 9864.25 joules. Okay, so 9864.25 minus the gravitational, we got 9163 is equal to a half times 85 v final squared. Okay, so when I subtract that 9163, I'm getting 71701.25 is equal to 40. Is it 47.5? No, 42.5 v final squared. Then I'll divide both sides by 42.5 over 42.5. This cancels that, and then I need to find the square root on either side. So my v final is gonna be 4.06 meters per second. So even if I were to use the equations of motion, I was gonna get the 4.06. How? If I use the Vf squared is equal to Vi squared plus 2a delta y. We're looking for Vf. So it's gonna be square root, V initial is a 0, plus 2 multiplied by our acceleration, which is 0.7. Now I can't use that. No, I can actually. So it's 2 multiplied by 0.75 multiplied by 11 to give me that. But this does not apply to the work energy theory. Okay, then 6.6. They're telling us that a 30 kilowatt motor is used to lift the mass of 85 kilograms to a height of this. Calculate the percentage efficiency of that. Okay, so what we're going to do first of all, we know that our network was 9864. 6.25, the net work done by the tension, because we're focusing on the motor, and then the motor is having the cable within it. So we can say that power is given as the work done divided by the time. Is it possible for me to get the time, which will be work multiplied by the power? So the work done was the 9864.25 that we just calculated over the power, which is 30,000 watts. Okay. Then I'm gonna get, I divide that, I'm getting 0.329 seconds. Then I need to look for also the energy input, which is still gonna give me power multiplied by the time. So I'm moving in circles. So still the 30,000 for the motor, multiply the time it takes, which is 0.329. I mean, I'm just gonna get the same answer of this. And then when I look for efficiency, it's gonna be the input over the output times 100%. So our input is 9864.25. The output is just the same thing. We're multiplying by 100%. So the motor is 100% efficient, which is very rare. According to the question, this is what I'm getting, but in real life, it's hardly possible for something to be 100% efficient. Okay, question number 7. The siren of a rescue vehicle emits waves at a frequency of 360 Hertz, and then the frequency of the sound as heard by the listener that is standing by the roadside is 405. Define Doppler effect. So Doppler effect, we know that it is just the change, okay, in the frequency of sound detected, frequency of the sound detected by the listener. Okay, and why is this? It's due to the change in the velocities of the listener and the source, but relative to the medium of sound propagation. Okay, there you have your 2 marks. Then 7.1.2. Was the rescue vehicle moving towards or away from the listener? Explain the answer, making specific reference to the frequency, wavefronts, as well as the wavelength. So the fact that the frequency is higher, okay, is going to be moving towards. Okay, so what's going to be our explanation? I'm going to say that the observed frequency is higher than the emitted. Okay, so as the vehicle approaches, okay, the wavelength decreases. The wavelength will decrease, and since wavelength is inversely proportional to frequency, then the frequency will be high. Okay, then 7.1.3, take the speed of sound in air to be 340, calculate the speed with which the vehicle is moving. So I'll do it this side. So we know that frequency of the listener is equal to V plus minus velocity of the listener plus minus velocity of the source times the frequency of the source. So they told us this was a 405. They told us that's a 340. I'm going to say plus on top. Velocity of the listener is a 0 over 340 minus velocity of the source, which we want, times 360. Okay, so what I'm going to do, I can have 405 over 360 is equal to 340 over 340 minus Vs. When I do my cross multiplication straight away, can have 340 minus Vs is equal to 340 times 360 over 405. Okay, so when I simplify what is on the left, so on the right, I'm having 302,22. Then I just have to move this to the side. Vs must be 37,78, which means it's 37,78 meters per second. Okay. Then 7.2, the driver of the vehicle continues at this speed past the stationary listener. What change or changes, if any, would occur in the following? Write down the values. So the frequency of the siren as heard by the driver. So this must still be the same. Okay, 360 hertz. The frequency that is observed by the listener. So now that frequency is going to be 340. It's going to be minus 0 over 340 plus the 37,78 multiplied by the 360. Okay, when I do that, you know that it should be smaller. I'm going to have 320,47 hertz. And then the speed of sound is still going to stay the same. Okay, 340 meters per second. So that is question number 7. Question 8. Point A and point B are 0,04 meters apart as shown the sketch not drawn to scale. X lies this much, and then sphere X has 1238 electrons that were removed from the surface. So what is the nature of the charge on X? Choose positive or negative. I'm going to go for positive. Why? Because electrons were removed. As long as electrons are removed, then the sphere will stay more positive. Then calculate the magnitude of the charge on sphere X. So I could use the formula or the equation. This is 8.2 of Q is equal to NE. They need the charge. So the number of electrons were 1238. Multiplied by electron charge is 1,6 times 10 to the negative. What is this? Yeah. To the negative 19. That's gonna make sense. Determine the charge. Oh, that's fine. So if that is removed, so if I multiply that, I'm gonna get 1,98 times 10 to the negative 16 coulombs. Okay. Let me just check this paper. Okay, mass of electron. Is this? Okay, that's fine. I'm gonna take that to be my answer. And then define the term electric field. So electric field is just the region of space, okay, in which a charged particle or a charged object experiences what we call an electric force. And then 8.4, draw a net electric field pattern of two identical with opposite charges. Okay, so we know that opposite charges usually do attract. Okay, so we're gonna have 8.4, that's a positive, it's a negative. Just have field lines that are moving. As long as the field lines do not cross or do not touch each other. So the arrows should also be indicated correctly. Okay, so that is 8.4. And then 8.5. At point A or B, or at what point between A or B is the magnitude of the electric field due to the charged sphere X greater? We must explain our answers. So we know that electric field is given as a force over Q, which is the same as AQ over R squared. Let me use this. So we can see that the electric field is inversely proportional to the radius squared, which means if the radius is increased, the electric field is going to become smaller or weaker. And if the radius is smaller, the electric field is going to be stronger. So I'm going to go between point A or B. So I'm going to go with A. Okay? And the reason for that, I can say that E is inversely proportional to 1 over R squared. That could be my answer. But I can put it in words and say electric field is inversely proportional to the distance of separation, or to the square of the distance of separation. Then 8.6, calculate the electric field of sphere X at B if sphere X is replaced with that. So let's do that. KQ over R squared. So 9 times 10 to the 9 multiplied by now our Q, which is going to be 2 times 10 negative 9 over the distance of separation, which is going to be 0.03 squared, because the difference between that is that. Okay, then I'll just do the substitution. 9 times that and that, I'm getting 20,000 Newton per Coulomb. Then 8.7, a negative point charge Y with this is replaced at B. Okay, this is B. Let me just put it this way. Okay. So B is somewhere there. We have X, and then we have A. Okay, so we have 3.2, and then we have negative 2.8. Initially, remember, it was a 2, it's just a 2 times 10 to the negative 9 at point X. They want us to draw a vector diagram to show the direction of the forces on the charge X as a result. So, why can't I just put it down here? We can see that B is positively charged. No, Y with this is now placed, so it's a negatively charged, 2.8. And then at A, we have a 3.2, which is positively charged, and then X was negatively charged. Okay. So, between A and X, since the signs are opposite, there's going to be attraction. So, which means at X, the force of AX is going to act to the right. And then since these two are of the same signs, is going to be repulsion, which means the force of B due to X is going to be on the opposite direction. So this should be your vector diagram. The force on X as a result of A, force of X as a result of B. That should be the vector diagram. And then 8.7.2, they want us to calculate the net electrostatic force between the two. So we need to calculate the FBX and then the FAX separately. Okay, so I'll come down and say this is 8.7.2. FA of X, KQ of A, Q of X divided by the distance of separation, 9 times 10 to the 9, multiplied by my A, we said is 3.2 nanocoulomb. So that's going to be 3.2 times 10 to the negative 9. Our X is negative 2, so just use the 2 times 10 to the negative 9 over 0.01, but everything is squared. Okay, so when I punch that into my calculator, I'm getting 3,2, and that I'm getting 5,76 times 10, 1, 2, 3, 4 to the negative 4. This is newtons. And then f v of x, still the same formula, substitution, negative is positive 9, multiplied by 2 times to the negative 9, multiplied by, we say it's going to be 2,8 times 10 to the negative 9. Dividing this by 0,03 squared. This is going to give me 5,6 times 10 to the negative 5 newtons. Then my F net is going to be 5,76 times 10 to the negative 4 minus 5,6 times 10 to the negative 5. Okay, so that gives me 5,2 times 10 to the negative 4 newtons. So that is the net electrostatic force. Okay, then question number 9, telling us that a circuit diagram is set up as in the diagram below. Resistors R1, 2, and 3 are identical, which means they have the same value. Switches S1 and S2 are closed. Ignore the internal resistance because it's for third term. Good. Then they want us to state Ohm's law in watts. So we know that Ohm's law will tell us that the potential difference across an electric conductor is directly proportional. It's directly proportional to the current through the conductor, directly proportional to the current through the conductor at a constant temperature. So the temperature has to be the same or constant for that to happen. 9.2, they want us to name the component of a non-ohmic conductor in the diagram above. So I'm going to go for the bulb, or some people call it the lamp. Okay, because resistors are all ohmic. The ammeters, these ones just measure, so they cannot be used as non-ohmic conductors. So I'm going for the bulb because name the component of a non-ohmic conductor in the above. So we know that the bulb, what does a bulb have? What do we call those springs inside that give the light? That could be also an option to tell us that those constants. Okay, then 9.3, write down the reading of the voltmeter with both switches closed. So if both switches are closed, these systems are going to be in parallel. And if that is true, which means the voltage is maintained, it has to be the same. So it's going to be a 12V. Then S2 is open, and it's just these two that will be in series. But we know that the total voltage across the VR2 and the VR3 must be equal to the whole V. So still 12 volts, since the voltmeter is connected across the terminal. Then 9.5, switch S2 is closed and S1 is open. Now the moment you open S1, there is no current that is flowing. Nothing is happening there. They want us to get the voltmeter ready. So it's going to be 0V. Then S2 is opened. How would this affect the ammeter reading? So if this resistor is out and we have just this one, is the ammeter reading going to stay the same, increase or decrease? Now let's take this to be 2 ohms, 2 ohms, and then 2 ohms. These two are in series. For them to be combined, we shall have just a 4 ohm resistor, one block that is a 4 ohm. Now, the moment we have a 2 ohm and a 4 ohm combined, if both switches are closed, we shall have a product over the sum, which is like 8/6. That's 4/3, which is 1,3 ohms. That's going to be our effective resistance. Now, if this resistor is out, we're going to have an effective resistance of 4 ohms, which is bigger. So if the resistance is bigger, the current is going to be. Let's see. If that is going to make sense, let's see. Telling us if S2 is opened, okay, so there's no more flow of current this side. It's just the same current that is flowing through the circuit. Originally, the ammeter reading was constant. So if switch S2 is opened, how would this affect the ammeter reading? But the ammeter reading is connected, not even close to any of these. So the ammeter reading is going to stay the same, guys. It stays the same. Okay, then 9.4, both switches are opened. Resistor R1 is removed. How would this affect the voltmeter reading? So both switches are closed, but then R1 is removed. So there's no resistor here. It's just that. Is there any voltage across? Is there any voltage across? Yes. So how will it affect the voltmeter reading? Voltmeter reading is going to stay the same. It's going to stay the same. So guys, that's all that we have to do. But remember, this is a proposed memorandum. Yes, there could be hiccups here and there. We're human, okay? If there are any issues, please just slot them under the comment section. We shall rectify them. Welcome to this episode where I shall be looking at the revision of the Physical Sciences Paper 1, okay, for September for the preparatory examinations, okay? So in Paper 1, there are a few topics, or the structure of the paper that we can look at is number 1. We always expect to have some 10 MCQs, okay, multiple choice questions, and they normally account for 2 times 10, which is like 20 marks. And these MCQs will cover all the topics of Paper 1. Then number 2, we have the motion, okay, or laws of motion. That's another topic. And then number 3, besides this motion, or we can just break down the motion and say it's normally the vertical projectile motion, okay, where the laws of motion need to be used. And one thing that we need to put into consideration is basically the directions that we normally use. Okay, so the laws of motion normally take between, I think, 2 questions. And then from there, we can have our momentum, in as much as momentum is also still motion, but it's fine. So that's momentum together with the cousin called impulse, okay? And then after that, we can have our work energy and power. And then from the work energy and power, we need to know at least that theorem, okay? What is it equal to, and how do we transform it from words into its application? And then next we have what we call the Doppler effect. Okay, usually this is one question, just like the work, energy, and power. And then from Doppler effect, we have what we call the electrostatics. Okay, electrostatics. We need to remember the Coulomb's law and the formula, okay, of calculating the force and all of that. So it's also one question. Then besides electrostatics, we have what we call electricity, which is basically electrical circuits. And then from electricity, we have the motors and generators, electrodynamics. Normally call them motors and generators. And then lastly, we can have our photoelectric effect. Okay, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have basically 9 aspects, so areas that we shall be focusing on. Okay, so I'll try to follow the order of the question paper. Okay, but in most cases, when I'm advising learners, if you're writing any paper, start with any question that you are comfortable with so that you can maximize the amount of time at your disposal. Okay, question number 1, which is the multiple choice questions. They're telling us that various options are provided as possible answers. The following questions must choose the answer and write only the letter A to D next to the question number. Okay, so question 1.1. They are telling us that the impulse delivered by a net force, okay, impulse delivered by a net force that is acting on an object is equal to impulse delivered. So we know that impulse is also the change in momentum. Okay, change in momentum is also the same as impulse. The change in P is the same as the impulse. But now we're talking about the net force. So impulse delivered by net force is equal to the change in momentum. So I'm going to go with option C because option A talks about the initial momentum. Nope. Final momentum, rate of change of momentum. Rate of change of momentum is the force itself. But now they're talking about the impulse. So change in momentum would be the best option for that question. Then 1.2, the graph below represents the relationship between the net force as well as the displacement it undergoes. And then the force and displacement are in the same direction. So if we have F net is equal to delta X and something that we don't know, what are they looking for here? Because that's not mass and acceleration. Okay, which one of the following statements can be deduced from the graph? They're telling us that the area between the graph and the displacement axis represent the net work done. I think that makes sense. But does it make sense? Net work done, if you look at the area that is under here, because we know that for us to get the area here, it's going to be force multiplied by the displacement, which is correct. Okay, which is correct. Work done. Let's see. The area between the graph and displacement represents the power. No, with power, there has to be time. We don't have any delta t, so we can't use this. And then the gradient of the graph represents the change in kinetic energy. Change in EK is equal to W net, the net work. And here we're just looking at the net force. Okay, so this is out also. Then the gradient represents the work done. When you talk about the gradient, so it's like F net over the displacement, which is like the work done by the force. Is that true? Nope, 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 nope. That is not true. Because we know that work done. Okay, remember we said work done is this force times the displacement. Now, if you have the force over the displacement, then that is like the reciprocal of work. So the best option for me would be option A. Then 1.3, a ball is dropped from a certain height above the ground and bounces a few times as it hits the ground. The VT graph describes the motion of the ball from the time dropped. Ignore the effects. Okay, so from here, velocity 0, which means it was just dropped. It attains the velocity by the ground. Okay, then bounces off and reaches its maximum at D, and then goes back again for the bounce, and then reaches also a 0 or the maximum at that point. So in the relation to the velocity time graph for the bouncing ball, which statement is correct? Okay, we need a statement that is correct. They're telling us that down is taken as a positive direction, and the ball is at its highest position at point C. Nope. So this C just cancels the whole scenario. This is out. Remember, maximum position is basically D and that other point, okay? Or even point B. I wouldn't really call that. Okay, let's see. But I'll go for this one to be the maximum position. Okay, then option B, down is taken to be positive. This is also wrong, okay? And the ball is at the highest point at D. So the last part is correct, but then the first part is wrong. Then C, down is taken as negative, okay, which is correct. And the ball is at its highest at C, which is wrong. This last part is wrong. And then down is negative, the highest point is D. So D is the best option. And then 1.4, they're telling us that an ambulance approaches this person as he is standing beside the road. As the ambulance drives away from him, the pitch and the wavelength of the siren that he hears will undergo the following changes. Okay, so we know that the pitch refers to how loud or how low the sound note is. And if the ambulance is moving away, the pitch is going to be lower. Okay, the sound notes are going to sound low. And what is wavelength? Wavelength refers to the distance. The distance between will just increase. So option D is the best because I'm seeing lower and greater. This is lower and shorter. So D is the best option then. Then 1.5, an absorption spectrum of an element forms because of atoms in the element that are or that will absorb, because this is an absorption spectrum. So there is no an absorption spectrum emits. No. So A is out, B is out. Let's look at C and D. So absorbs light, photons, and atoms, electrons, making a transition from high to a low. Absorbs light, photons, and atoms, electrons, making a transition from low to a high. So when it absorbs the light, it gains energy. And there's no way you can start from being a hero to a zero when it comes to this sort of absorption spectrum. You always have to start from a zero and then become a hero. So option D becomes the best. Okay, start from zero, you go up. All right, then 1.6, two objects with the same mass, with a certain distance D between them, exert a force on each other. Okay, if the mass of one object is doubled and the distance stays the same, the force between the two would also be doubled. Because we know from Newton's law of universal gravitation, Gm1, m2 over r squared. If you change this by 2, which means the entire force is going to increase by 2 also. So option C would be the best. If ever it was the distance that was doubled, then the force would be now a quarter. Okay, if both masses were increased by 2, or they were doubled, then the force will be 4F. All right, then 1.7 diagram below shows a point P at a distance R from a charged sphere Q. And then they are telling us that the electric field strength at P is directly proportional to R and to the right. So let's start by finding out what's the formula for electric field strength. So we know that it is K. Is that really correct? Because it's a KQ over R squared, yeah? Something like that. But now when you look at the electric field strength and the distance, they are inversely proportional. Let me just confirm with the formula. I don't want to mislead people. Let's confirm it. We said electrostatics. Okay, so it's KQ over R squared. Thank you. All right, so if that is the case, so option A is out. It's not directly proportional. Option B is out. It's not directly proportional to the square of the distance. So these two are out. Okay. Then C and D inversely proportional to the square of R. That's okay. Inversely proportional to the square of R. And then they're telling us it's to the right. And then this one is giving us to the left. So we know that if P, we normally take P to be a positive charge. Okay. And if it's a positive charge, what's going to happen here? It's going to be attraction. Okay. So the electric field is saying it's going to be attraction, this one, this side, this one, that side. Okay. At P. So when you're focusing on P, the force, this force will work on P in that sort of direction. Does it make sense? And then this one will work in that sort of direction. So I want to believe that P is going to have inversely proportional to the square of R, and it's going to be on the left of P. Okay, so that is 1.7. Then 1.8, which of the following statements about an AC generator is true? They're telling us that the minimum potential difference is not 0 volts. This is wrong. The EMF produced decreases at the number of windings. This is wrong. The EMF must increase. The maximum value of the AC can be increased by increasing the period of rotation. Nope, you can't. Then the maximum value of the AC produced can be increased by increasing the speed. That's correct. So option D is the only correct option there. Then 1.9, a battery with internal resistance connected to a fixed resistor R. The voltmeter is connected across the battery. As we can see in diagram A, the battery is replaced with one with the same EMF, but with a larger internal resistance. Okay, as in B. So this is 0,4, this is 0,2, okay, as we can see. Then they're asking us that how would the voltmeter reading and the current through the fixed resistor change compared to A when the switch is closed? So when you look at this in diagram B, so our focus is mainly on diagram. Is it B or A? Because they're telling us that the battery, because our focus was A, the battery is replaced by one with the same EMF, but with a larger internal resistance as shown in B. 1, 2, so the same EMF, but it's just the internal resistance that is greater. How is this going to affect the reading of that? Now, one thing we need to know is that the current, okay, is it going to increase or decrease. So if resistance, whether it's the external or the internal, if any of them increases, and we're seeing that it is just one resistor, so everything is in series, definitely the current must decrease. Okay, so I'm looking at option A and then option C. There's no way current will stay the same if the resistance values are changed. Then with the voltmeter, we know that voltage is directly proportional to the current. So if the current reduces, even the voltage must reduce. So option A becomes the best option there. Then 1.10. 3 light bulbs are connected in series. Okay, the bulbs are marked 12V, 3 watts. The effective resistance produced by a single bulb in the circuit is, they are connected in series. Perfect. They're asking us to get the resistance. We have the power, which is 3 watts. We have the voltage, which is 12. They're asking for R. So we can use a power formula. We know that P is IV, but our interest is resistance. Okay. So if our interest is resistance, which means we're going to have to say that P is V squared over R. Let's just do this, which is a V squared over P. Our voltage is 12 times 12 divided by 3. Okay, so by 3 is a 1, by 3 is a 4. So 4 times 12 gives me 48. So 48 ohms will become the best answer then. All right, then question number 2. A group of learners decide to design a device that contains or that consists of a light ball on a string that is hanging from the roof of a cargo truck. The device is used to determine the acceleration of the truck when the truck is stationary or moving at a constant speed. The ball will hang straight down. But when it undergoes constant acceleration, the ball hangs down at an angle theta as shown. Okay. Then they want us to draw a free body diagram, okay, of all the forces that are acting on the ball. So if that's our ball, we know that there is a tension force, and then there's going to be weight there. So meaning that we're going to have something like that, and then we just drop it down. So that is weight, then that is your tension. All right, so that is what we would have written down. Okay, remember this is a component of the tension, which is okay, perfect. And then 2.2. In this case, the mass of the ball is 50 grams. So let's change this to kilograms. It's going to be 0.05 kilograms. Perfect. And then the angle theta is 18. Calculate the horizontal force on the ball. So one thing you need to remember is that if this is the tension that is acting, okay, if I'm to resolve this into the horizontal and the vertical, okay, gonna have something like that. So if this is a theta, even this one is gonna be a theta. I don't know how you want to do it, but this one is gonna be a T cos of theta. And then this horizontal of mine will be a T sine of theta, okay? But now, in which direction is it acting, okay? Is it to the left or to the right or what? So since this must be in balance, I'll take my horizontal to be in that sort of direction. Because remember, for me to get my resultant of T1 must be up, then one must be in this sort of direction, because I cannot put it to the right, otherwise this resultant will be in that direction. Okay, So then, since they want the horizontal, I'll just do the substitution and say mighty sine of theta is equivalent to the tension. Do we know the tension? Oh, this is a t cos of theta. I don't know. We can look for because the force is not going to come out without the t. It's 4 max. So if that's the case, then let me start by looking for because I need that force. Oh, what's the way forward? I can say that my t cos of theta is equal to mg. Okay, looking at just the upward forces. Then I look for t, which is going to be mg over cos of theta. So if I do that, then this is going to be my mg, which is 0.05 multiplied by 9.8 over the cos of 18. Okay, so what is my tension? So let's punch this, 0.05 multiplied by 9.8. You're dividing it by the cos of 18. That gives me 0.52 newtons, okay? So that's our tension, meaning that for us to get the horizontal force, it's going to be 0.52 the sine of 18. Let's see. Sine of 18. That gives me 0.16 newtons, okay? So that is how I would have gone about with that question, okay? Remember, the rounding off just needs to be maintained to 2 decimal places. Okay, because my calculator was giving me something bigger than that, but it's okay. Then 2.2.2, they want the magnitude of the acceleration. Now, one thing we need to know, is there friction on this? Because it's consisting that determine the acceleration when the track is stationary or moving, okay? Okay, so the question never talked about anything to do with what? With friction, meaning that I can use my F net, okay, and say that my F net is equal to MA. So what is our net force? So we know that our net force is basically what we got as the horizontal, meaning that the 0.16 is equivalent to the mass, which is 0.05A. Then divide both sides by 0.05, 0.05. Okay, when I punch that into my calculator, okay, 0.16 divided by 0.05, I'm getting a 3.2. This is meters per second squared. Okay, so that is how we calculate the acceleration of that body. Then 2.3, A and B are 2 identical blocks, each with a mass of 5 joined together by a light string. The blocks are being pulled together with a force of 65 at 40 degrees. The 2 blocks accelerate to the right using this acceleration, and then the tension is 26 in between. Okay, calculate the friction on each block. Calculate the friction on each block. Okay, so when you look at body A, if I try to sketch the free body diagram, okay, because I need to see how many forces are acting on A. So from A, we have the 26, okay? We say there is a frictional force, okay? And I think that's all. When I look at B, I'm going to look at the horizontal component, which is going to be like 65 cos of 40, okay? And then on the other side, I have the tension, which is a 26, and then I also have the frictional force. So I have more forces acting on this than on this. Okay, so come down and use the F net. Okay, we're saying F net is equal to MA, meaning that if we have, let's say, 26 minus our Fk, we should be able to get the mass and then the acceleration. Mass is a 5, the acceleration is a 2,17. Okay, so I do the substitution there. Okay, meaning that my Fk for A is going to be a 26 minus, what is 5 times 2,17? I'm getting 10,85. Okay, when I subtract from 26, I'm getting 15,15 newtons. When I look at the B part, I'll still use the same thing. F net is equal to MA, meaning that 65 cos of 45, we are subtracting 26, you're subtracting Fk, it should give us the same mass and acceleration, which we got as 10,85. Okay, move this on that side, and then we transpose 65 cos of 45 minus 26 minus a 10,5 is equal to Fk of B. Okay, let's not forget that. So it's saying 65 cos of 40, not 45. Okay, it's a cos of 40. Okay, we are subtracting 26, and then we are subtracting 10,85. This is 85. Okay, so the friction for B that I'm getting is a 12,94 newtons. Okay, so that is how we would have calculated the friction on each block. But then the question is asking, explain why the frictional forces are not the same. Okay? Why the friction forces are not the same. Now, one thing we need to know is that, yes, the blocks can be of the same weight, but they may not necessarily be made out of the same material. Okay? And then two, when you look at the angle, this 40 degrees, there is a way it's going to affect the friction that is acting on block B. And yet, with block A, there is no angle, there's no force like that is acting on that. So to answer this question, we could say that we know that the coefficient is constant, okay, for a specific surface. So one, we can say that surfaces can differ. Surfaces can differ. And then the force, okay, the force on B is at an angle, meaning that it is only a single component, the horizontal component, and not the entire 65 that will work on it. Okay, it's at an angle which decreases the normal force. Okay, so that is what we would have done and said with that question 2. Question number 3, VPM. They're telling us that a ball is dropped from a height of 19,6 above the ground. It rebounds from the ground, reaching the original height h. Wow. Ignore the contact time of the ball with the ground and the effects of air resistance. And then they are asking us the definition of a projectile in physics. So we know that a projectile is basically an object, okay, an object which has been given an initial object which has been given an initial velocity, and then from the initial velocity, it moves under the influence of the acceleration due to gravity, or we can say influence of the gravitational force. Okay, so that is the projectile one. We give it an initial push, an initial velocity, and then we let it go so that it moves under the influence of the gravitational force only. Okay, so that is a projectile. Remember, projectile could be different from free fall. Okay. Then 3.2, what is the total displacement of the ball? Remember, it was dropped from here. Okay, it covers 19.6 in that direction, but then it bounces back to the original position, meaning that it's a positive and a negative, which gives us a 0. Okay, then use equations of motion only to determine the time that is taken by the ball to rise up to the same height. Now, since we know that our displacement is a 0, we could use any equation that has displacement. Okay, question is asking for the time. So we have something like displacement is equal to V initial multiplied by time plus a half a t squared, or a delta t squared. Do you have the initial velocity? It is dropped, meaning that the initial velocity is a 0. Okay, I think we can use this. Can we use that? Yeah, we can use that. If not, we have V final. We don't have the V final, so we can't use the first one. And then the third one, V final squared is equal to V initial squared plus twice A together with the displacement. We don't have the final. So I think the second one will work best. Okay, let's see. Okay, so I'm going to take the downward to be my positive. Okay, so meaning that start by writing the formula. Delta y is equal to V initial multiplied by delta t plus a half g delta t squared. Okay, so we're saying this is 19.6. Since the ball was just dropped, that's going to be 0 multiplied by delta t, which we are looking for, plus a half. The g is going to be 9.8 multiplied by t squared. Okay, this is a 19.6. A half of 4, or half of 9.8 is 4.9 t squared. Divide both sides by 4.9. Divide by 4.9. Okay. When I do that, what do we end up with? From my calculator, I'm having 19.6 divided by 4.9, which gives me a 4. And then take square roots, meaning that t is going to be 2. So if the ball took just 2 minutes to drop down, it should also take 2 minutes to go back to the original position. So time taken by the ball to rise up to the same height. So that is 4 seconds. Okay. And then 3.2, the velocity with which the ball leaves the ground after rebounding for 3 marks. So what we are basically looking at is that if we are ignoring the reaction time, then we shall assume that the velocity with which the ball leaves the ground is like the final velocity with which it hits the ground, if I'm to think of it critically. Okay, final velocity with which it hits is the same final velocity that it will use as the initial. So let me look for the final velocity using the first equation. V final is equal to V initial plus A delta T. So my A is going to change to a G, meaning that our V final is the 0. We say that is going to be 2 multiplied by 9,8 because the time is 2. Ish, someone will cry and say, but now you started with A, now you're putting a 2 first. Ish. So it's going to be 9,8 multiplied by 2. Then that gives me 19,6 meters per second. Okay, so that is what we're going to have, but the direction will be upwards. Okay, so that is how we would have claimed those 3 marks. Then 3.4, they want us to sketch a position time graph for the complete motion of the ball. Show the time taken for the ball to reach the ground, the time taken for the ball to reach the starting point, the initial and final positions. Okay, so one thing we need to remember about the position time graph. Okay, so this is the position which I'm gonna just label as a Y. Okay, the displacement in meters. This is the time in seconds. Now it all depends on how you want to put your representation. Okay, so if I start from a 19,6, ball is gonna bounce. Okay, and then after the bouncing, it will go back to the same height. Okay, so now what's going to happen is that the point at which it reaches the ground is 2 seconds. And then this point here, the time needs to be 4 seconds. So I think that's all that I need to just represent, and then I'll get my 3 marks because we have all the factors that they wanted. All right, then question number 4, they're telling us that ABC, okay, ABC is a frictionless track. There is no friction. A is a point that is 6 meters above the ground. Blocks P and Q of mass 4 and 6 respectively. Okay, this is 4, that is 6. And the spring of negligible mass are clamped together so that if the fully compressed spring is aligned between blocks P and Q. Then at position A, the system moves as a whole, moves together, no stress. Okay, but they are moving at 4,5 meters per second. System slides down B at the bottom, and then boom, they break up. That want us to state the law of conservation of mechanical energy in words. So we can say that the total mechanical energy, okay, total mechanical energy in an isolated system, is conserved or simply remains the same. Someone could also say that the sum of the gravitational potential and the kinetic energy in an isolated system remains the same or is conserved. Okay, so that is 4.1. Then 4.2, use the law of conservation of mechanical energy to calculate the speed of the blocks at the bottom of the ramp. Now, one thing we need to know is at point A, okay, the blocks are having both the mechanical and then the potential because the blocks are moving. That's what they told us. Okay, that at position A, the system moves as a whole with that sort of velocity. But still at this position, there is also mechanical energy, the EP. So we have the EP and then we also have the EK. Now, at the bottom here, the combination is only having EK because the EP is a 0. Okay, we only have the EK, which will be the EK max. Okay, so what are we gonna do? I believe we just need to look for the mechanical energy. and then try to work that out. I don't know if I can do it. It's fine, let me do it here. Okay, so let me start by finding the EP. Okay, the EP at A. That's gonna be mgh. So I'm gonna look at the combined mass, which is 4 and 6, which is a 10. So 10 times 9,8 multiplied by 6. What do we end up with? Okay, 10 times 9,8 times 6, which is 588. And then let's look at the EK at A. That's gonna be a half. Okay, I can look at the two masses because the velocity is the same. Okay, so a half of 4 multiplied by 4,5 squared plus a half of 6 multiplied by 4,5 squared, which would have been the same as me just adding up the two. Okay, so 0,5 multiplied by 4 multiplied by 4,5 squared. We are adding 0,5 multiplied by 6 multiplied by 4,5 squared, which gives me 101,25, meaning that my mechanical energy at A will be a combination of the two, which will be 689,25 joules. Now, I'm going to get this 689 and then I equate it to the EK at point B, or along the flat surface. So I would say that we said 689. EK max is equal to a half mv final squared. So 89689. 25 is equal to a half multiplied by the entire system, okay, which is going to be a 10 multiplied by the V final squared. So that's going to be a 5. So 689,25. I'm dividing it by 5 and then finding the square root to get my V final. Okay, so punching that into the calculator, 689,25. We said we are dividing it by 5. We're getting 11,74 meters per second. So that is how we would have obtained those 4 marks, by just comparing the energies at the different points. Okay, that is how we would have answered 4.2. Then they're telling us that at the bottom of the ramp, the clamp is released by a remote control so that the motion of the system as a whole is not affected in any way. So as the spring expands or stretches, the blocks move apart. The speed of block A is now increased by 10%. Now remember, both blocks we're having the 11,74. Okay. Now if it increases by 10%, what is it going to become? Okay, we're going to look at that. Use the law of conservation of linear momentum to calculate the velocity of block P after the spring has expanded. So what we're looking at is a scenario whereby we know that momentum before is equal to momentum after. Okay, so initially they were together. So it's a mass M of A, mass 1 and mass 2 multiplied by the final velocity is equal to mass of block 1, V fine of block 1, plus mass of 2 and the V fine of block 2. What did they tell us? That the speed of Q increases. So let me call this P and Q so that I don't confuse people. This is Q. Okay, so 10% of 11,74, what is it going to become? We know that that is going to be 0,1 multiplied by 11,74. Why don't I just see 1 at once? Because that's going to be 110 divided by 100 times 11,74, which becomes 12,91 meters per second. Okay, so that is the new velocity for Q, or the final velocity for Q. Then let's do the substitution. That's going to be 4 plus 6 multiplied by 11,74 is equal to the mass of P, which said it's a 4, multiplied by the final velocity of P plus the mass of Q, which is a 6, multiplied by the 12,91. So let's transpose everything to that side and then see what we have. So 10 multiplied by that, I'm going to have 117,4. I'm subtracting 6 times 12,91, which becomes 77,46 is equal to 4 VFP. Divide both sides by 4, which means our final velocity for P is going to be 117,4. We are subtracting 77,46. We said we are dividing it by 4, which is 9,985. I'm tempted to round it off to 10, because someone can say it's 9,99 meters per second. Okay, so that is what we would have obtained, okay, as our answer. Then 4.4, they want us to calculate the magnitude of the impulse which block Q exerts on block P. Now remember, when we're talking about impulse, we're basically discussing the change in momentum. Okay, so impulse is equal to the change in momentum, meaning that our P final minus the P initial. This is given as M, V final minus V initial. So which M can we use? We can use the M of P, okay, which is basically the mass of P. And that mass is going to be 4. What is our V final? We said it's going to be 9,99. What is the V initial? We got it as 11,74. Okay, when you punch this into the calculator, it's going to be 4 into minus 11,74. It gives us a -7, okay? But remember, the negative simply indicates the direction that we're basically looking at. So meaning that our impulse is going to be 7 Newton per second. Is it Newton second or Newton per second? It's supposed to be a Newton second. Okay, so that is what we would have done in that particular aspect. All right, then we move on to the next part. Okay, then question number 5. Question number 5, they're telling us that a diver, okay, of mass 80 kgs steps off a diving board at point A, which is 4 meters above the level of the water of the swimming pool. Then the diver enters the water at point B and comes to rest at point C. While this guy is falling through the air, the average frictional force of 172 newtons acts on the diver, and then the total work done on the diver while he moves from A to C is that much. Then we have the picture. Okay, they want us to state the work energy theorem in words. So these are free marks, guys, whenever you see this question, because it's always there in almost all the papers. So we can say that the work done, okay, on an object, the work done on an object is equal to the change, is equal to the change in the object's kinetic energy. Object's kinetic energy. Okay, so that is how you have to put it. The work done on an object is equal to the change in its kinetic energy. Okay, then 5.2, use the work energy theorem to calculate the speed of the diver at point B. Okay, now what they gave us was basically the work done. Okay, so we can use that and say that W net is equal to the change in EK. Okay, now what we need to realize or understand is with the work that is being done, we have a frictional force, and then we also have this guy's weight. So before I even start, if I were to look at the free body diagram of this guy, okay, there's weight, and then we say there's a frictional force that is acting to oppose the direction of the motion. So since this guy is going down, meaning that the weight is going to be greater than the frictional force. So the work done by these two could be just the same as work done by the weight, which is the Fg, plus the work done by the frictional force should be equal to the Ek final minus the Ek initial. So work done, remember the formula is force delta x and then the cos of either 0 or 180. So the weight, this guy is 80, so it's going to be 80 multiplied by 9,8, because now that will be, because this guy is 80 kilograms, multiplied by 9,8 to get the weight. Okay. Then the cos of 0. Do I need to get the cos of 0 as well? Yeah, times 4 cos of 0 plus, they told us that the frictional force is 172 multiplied by the displacement, which is 4, and then that's going to be cos of 180 because it's opposite. Okay, if you want to avoid the cos of 0 and the cos of 180, just focus on the direction. So friction is negative, so then there will be no need of the 180 to come out automatically. So that is equal to the half mass, which is 80. We're looking for the velocity. Is that correct? Yes. So V final squared minus a half times 80, the initial velocity with which he jumps. Are we going to take it to be a 0? Definitely, because it's more like he's dropping himself into the pool. Okay, so when I look at the left-hand side, so 80 times 9,8 multiplied by 4, I'm getting 3136. Okay, now this is going to be minus because of the cos 180. 172 times 4 gives me 688. This should be equal to, this is a 0, which is 40 VF squared. Okay, so 3136 minus 688 gives me 24. 48 is equal to 40 VF squared. Divide by 40, divide by 40, meaning that our VF squared is equivalent to 2448 divided by 40, which is 61.2. Okay, and then let's find the square root on either sides. So our V final, 61.2 gives me 7.8 meters per second, 7.82. Okay, so the velocity with which this guy hits position B is 7.82 meters per second. Guys, so that is how I would have gone about that question. If you have a cheaper way or a quicker approach, please advise us. Then 5.3 is the mechanical energy of the diver conserved. Yes or no? Give a reason. Okay. Now, remember, we said under conservation of energy or mechanical what? We said in any isolated system, okay, the mechanical energy is conserved or remains constant, meaning that the net mechanical energy needs to be a zero. Okay, but when you look at this, they gave us the net to be, okay, the total work done is negative. So the answer is going to be a no. Okay, reason, the net work done is not zero. The net work done is not zero. Okay, someone could say that it's a no because there is presence of friction forces that will be doing work. Then 5.4, use energy principles only to calculate the distance from B up to C. Okay, so which energy principles are we going to look at? We can say that WNC, work done by the non-conservative forces, will be equivalent to the EK plus the EP. Okay. Then we were given our non-conservative, which is the -6, what. So the only thing that I need to look at is these changes. So I can have my EK final minus my EK initial, my EP final, my EP initial. Okay. When I do the substitutions, I have -6, 240. My EK final is going to be a half. The mass is 80. And then the velocity, remember this guy is going to be at the bottom because they told us this guy comes to a rest. Y falls through an average, okay, comes to rest at point C, meaning that our final velocity is going to be 0 there. We are subtracting a half times 80. The initial velocity is what we got, 7.82. Okay, 7.82 but squared. Plus the EP final at point C. Remember, C is more like, they told us point A, which is 4 meters above the level of the water. Diver enters, comes up, falls through air, and do we know the displacement there? Do we know the initial displacement? Because, okay, let's take the initial velocity when he was jumping. Does that make some bit of sense? If we say, okay, he was jumping, and then we want to look at that sort of whatever, meaning that we cannot use the 7,8 because the 7,8 is only representing the velocity at this point. And then at B, he has velocity initially and finally. So if I'm using just this point, or if I'm taking it from point B, because if I'm taking it from the initial position, then that will be a 0 even initially. It was supposed to be a 0. If I'm taking it from B, then this can be a 7,8 squared. Okay. Now, if I take it from B, my initial, my final is going to be the mass multiplied by the 9,8 and the displacement. So which displacement are we talking of? Is it going to be a D? Because there is looking at it from that perspective. And then there is also looking at it from a different angle. I don't know which one would make more sense. Okay, if I look at B as my point of reference, okay, if B is my point of reference, but it's not going to make sense initially and finally. It's fine. Let me just use the original reference grid to say that we're starting from point A, meaning that it's going to be a 0, and then that's going to be a 0. Then for the final, I'm going to have what are we going to have there? It's going to be negative D because it's down below the pool. Then I'm adding the MGH, which is 80 times 9,8 multiplied by -4, which is also below. Okay, meaning that this dies out. Okay, and if that dies out, I'll have the -6240 is equal to the negative. But why am I? Okay, let me simplify that. We know that 80 times 9,8 is going to give us negative 784. And then this is saying we're multiplying it by 4, which is 3136. Let's move it that side. It's going to be a plus 6240 3136 gives me 3104 is equal to -784D. Divide both sides by 784. Okay, so when I divide that 784, I end up with a 395, which is like a 396. 396 meters. So that is how I would have worked that out. Okay. Then question number 6, which is the Doppler. They're telling us that an ice cream truck that is playing a tune approaches a stationary listener. Okay, approaches a stationary listener in the street. The ice cream truck is moving at a velocity of 11 meters per second. Okay, and then the sound waves emitted have this wavelength. Then the speed of sound in air is that. And they want us to state Doppler effect. Okay, so this tells us that the change, Doppler effect is the change in the frequency. Some people call it pitch of the observed sound. Why do we say sound? Let's call it observed frequency. Of the observed frequency by a listener, because of the sound source and the listener having different velocities. Because of the sound source and the listener having different velocities. Okay, so some people will also put it as the apparent change in the velocities. Okay, but then these velocities must be relative to the medium of propagation. So it's one long sort of a paragraph, but just try to remember. Okay. Then 6.2, they want us to get the frequency produced by the ice cream truck. Remember, they only gave us the wavelength. So we know that V is equal to F lambda. We need the frequency, meaning that it's V over lambda. The speed of sound in air is 340. You're dividing it by 0.34. Okay, you divide that, we're going to get 1,000 hertz. Okay, then now we move on to calculate the frequency as it's heard by the listener. We need the F frequency of the listener. Okay, so we can use the Doppler formula and say that frequency of the listener, start by writing the formula down, is given as V plus minus VL over V plus minus Vs times the frequency of the source. Now, what was the scenario all about? An ice cream truck approaches, okay? So when it approaches, meaning that the frequency heard is going to be greater. So it's V plus and then V minus times Fs. So let's substitute. What do they want? Or what are we looking for? We want the frequency of the listener. Okay, so it's going to be a 340 plus the velocity of the listener is a 0, and then 340, the track, we had 11 comma something, 11 meters per second. The frequency we got was 1,000. Okay, so that is what we would get. Then when we punch this into the calculator, so it's a 340 over 340 minus 11. We're multiplying it by 1,000. That gives me 1033. Okay, 1033.43 hertz. Okay, so meaning that the listener will get a bigger sort of frequency value compared to what was emitted. Then, how will the frequency that the listener hears compared to the frequency calculated in question 6.3 if the ice cream truck was moving away? Will it increase, decrease, or stay the same? So if it is the frequency of the listener, it's basically going to decrease. But if it was the frequency of the source, it was going to remain the same. All right, 6.5, state any other application of Doppler effect within our lives. Now we have very, very many, okay? Number one, we can use what we call the Doppler radar, the one that is mainly used by the traffic cops. Then we can also use it in the Doppler flow meter to measure the heartbeat of the fetus, okay? We can also measure the speed of blood. Okay, you can say speed of blood in a Doppler flow meter. Remember, we said to measure the heartbeat of the fetus and so on and so forth. We have very many, but the question just wanted just one. Okay, consider the representation of the absorption spectrums of two similar stars. Okay, now what we are seeing is that there's a shift in the lines. It's like they are moving in that direction if you compare B and A. If you're starting from A, then they're moving that side away from B. So the question is star B moving towards AO away. So B is moving towards. Okay, so how do we tell that it is moving towards? Just look at the double line. Okay, we're going to use the double line as a reference. Okay, so what we can say is that the double line of B has moved to the red side. Or is it? No, it's blue side. Okay, we're saying the double line of B has moved to the blue side. Okay, once it moves to the blue side, meaning that it is moving towards the frequency or the wavelength is decreasing. Then what is this type of shift called? So this is what we call a blue shift when it's moving towards. Then 7.1, a small sphere. Okay, a small sphere A that is carrying a -5 microcoulombs hangs vertically from a ceiling by means of a string. Point P is 100 millimeters to the right. So let's change this to meters, which is going to be 0.1 meters. Did the charged sphere A lose or gain electrons to acquire this charge of -5? Now, we look at spheres to be neutral if they are not charged. Okay. Then the moment the net charge exceeds 0, then they've gained something. Okay. But now we're talking of electrons, and we know that electrons are negatively charged. So this sphere gained electrons. Okay. If it was a positive, then it would have lost electrons. For it to be more positive, okay, you lose electrons. And then 7.1.2, calculate the number of electrons lost or gained by charged sphere A to acquire this. Okay, so we use that formula of the N is equal to Q over E, whereby Q is the charge and then E is the electron charge. So you're going to have 5 times 10 to the -6 over, we can use the negative, there's no problem. The electron charge is -1,6 times 10 to the -19, okay? And then when you just punch this into your calculator, I'm getting 3,125 times 10 to the exponent of 13 electrons, okay? So that's how much was gained or was transferred. Then 7.1.3, they want us to calculate the electric field at P due to the charge. So formula for electric field is KQ over R squared. Okay, K is a 9 times 10 to the 9. Our charged sphere is 5 times 10 to the -6. You're dividing it by the distance, which we said was 0,1 squared. Okay, simplifying this, I'm getting 4,5 times 10 to the 6 Newton per coulomb. Okay, so that is how we would have gone about with 7.1.3. 7.2, there is an identical sphere B that is carrying some charge that we know nothing about on an insulated stand. It's brought closer to sphere A. Then the charged sphere swings to the right. In other words, there's some bit of repulsion, okay? And then the angle created is a 30 with the vertical, and there's a tension of 25 newtons. Distance between the two will be 50 millimeters, which will be 0,05 meters. Okay, 7.2.1, is the charge on sphere B positive or negative? Repulsion happens just in the same signs. So this must be negative. Okay, so what is the reason? We know that like charges like charges repel each other. Like charges will repel each other. All right, then 7.2.2, they want us to get the magnitude of B. Magnitude of B. Okay, so I think we can look at this thing if you try to do the resolving. Okay, whereby we look at the tension. If we are to resolve it, we're going to have the horizontal and the vertical. So my horizontal is going to be T sine, which is like 25 sine, okay? And then my vertical is going to be T cos of 30, and of which this T cos of 30 is also equal to the weight. But that is not a big deal because we already have what the T is. All we need is the force that is acting between these spheres, okay, which is a repulsive force, meaning that this force at B should be equivalent to the tension, the horizontal tension. I don't know, that's my understanding of this. So we're going to say that the horizontal component on this sphere A, because our focus is A, is going to be 25 sine of 30, which becomes 12.5 newtons. Okay. Then A is going to also experience a repulsive force in the opposite direction. Okay. Because there's repulsion everywhere. No, the sign is acting this side and then the repulsion is that side. Okay, so with the repulsion, I'll use the forces and say F is K Q1 Q2 over R squared, the electrostatic force. So that's a 9 times 10 to the 9. Our Q1 was a 5 times 10 to the negative 6. This is B, which we don't know, should be divided by 0.05 squared. Okay. Then I'm going to equate this force because remember we say that this force is the same as the T sine of 30. So I will equate it to the 12.5. Do your magic, mean that it's going to be a 12.5 multiplied by 0.05 squared. I'm dividing it by the 9 times 10 to the 9 times 5 times 10 to the negative 6. Okay, so when you simplify this, I'm getting 6.94 times 10 to the negative 7 coulombs. All right, so that becomes question number 7 as expected, okay? We move on to the next question, which is question 8. They are telling us 3 identical light bulbs, A, B, C, each with a resistance of 8. Okay, so 8 ohms, even this one is 8 ohms. Okay, connected to a 12V with an unknown internal resistance as shown. The resistance of the connecting wires is going to be ignored. S is closed, and then the ammeter reading is 2. So where's the ammeter? So meaning that the total current is 2 amps. Then they're asking us to define the term electrical power. So electrical power is basically the rate at which work is done. Okay, rate at which work is done. Okay, then 8.2, calculate the reading of the voltmeter. Okay, so they want us to get the voltage that is across. How many marks is this? It's 5 marks, which is a lot. Meaning that we have the current, right? But we also have the values of the resistors. Now, A and B are in series, meaning that if we combine these two together, we have a 16 ohm. Now, this 16 and this 8, they are in parallel. Okay, so I'll say resistance A plus B becomes 16 ohms. And then the resistance between C and the overall result, the series, I'm going to say product over the sum, 16 times 8 over 16 plus 8. Okay, so I prefer to use this sort of formula because this is the resistance for the series. Now I'm looking for the resistance for the parallel. Okay, so we're saying 16 times 8 over 16 plus 8. I'm getting 5,33, which is the same as 16 over 3 ohms. Okay, now if this is the total resistance that we have, okay, that's the total resistance that we have. We have the ammeter. We were given the voltage to be 12. Is it the voltage or the EMF? It's the EMF. But then the switch was closed. Okay, so since we are looking for the voltmeter reading, we know that V is equal to IR. So it's going to be 16 over 3 multiplied by 2, which is basically 32 over 3. And when I punch that in the calculator, it's going to give me 10,67 volts. Okay, so this 10,67 is more like the external voltage. And then 8.2.2, they want us to calculate the internal resistance of the battery. So if I use the knowledge of external and internal, because this is the external voltage, I know that my EMF is given as V external plus V internal. Okay, so that's a 12, a 10,67, and then that's going to be the current multiplied by internal resistance. When we subtract that, okay, so what is 12 minus 10,67? That becomes 1,33, is equivalent to the current, which is 2R, and the resistance. So over 2 over 2. So what is our answer? I'm getting 0,67, meaning that the internal resistance is 0,67 ohms. Okay, so that is how we would have also worked out the internal resistance. If that is too hard for you, then you can even use the original formula for EMF, I into capital R plus R. We have the current, we have the EMF, we have the effective resistance, and then we're looking for the internal. I believe you can still get the same thing. Then 8.3. Can we compare the brightness of the bulbs A, B, and C? And let's justify our answers. Now, one thing you need to know is that the voltage across C is the same voltage, or is the total voltage across A and B. Okay, but A is having a different voltage. B is having a different voltage, meaning that our V, the 10,67, is the same as the voltage across C, which is the same as VA plus VB. Okay, now since these two are identical, they will split the voltage into two equal parts. Now, when you look at the current that is passing through the 8 is not going to be the same current that is passing through these two, because this is going to be 16. If it's 16, which means there's less current that is going to pass through the two bulbs, and then there's more current that is passing through C. Now, how do we answer this? So we can say that bulbs A and B are connected in series across the battery, meaning that they glow equally. Okay, so we're saying that A and B are in series. Let me put it this side. We're saying A and B are in series. Okay, and they also light equally. The brightness will be basically the same. whereas C is in parallel with A and B. Okay, it's in parallel. Then the voltage drop across C has the same magnitude as the terminal potential difference. Okay, so since A and B split and C doesn't, okay, it's parallel to A and B. With C having more voltage than A and B, okay, we say the voltage is the same for both A and B, okay, but the total of A and B gives us C. Therefore, we're saying C will be brighter than A and B. So any explanation around that? Okay, we could use the current situation, the voltage, or anything. Then 8.4, they're telling us that the switch S is now opened. Okay, how would the voltmeter reading change? Choose increase, decrease. So the voltmeter will increase the reading. Okay, why? Because there is no current and the reading is going to be the 12, which is the EMF. What is the reason? The reason is that the external resistance has increased. Okay, external resistance has increased, and then the potential difference decreases. We're saying V internal decreases, and then looking at the equation of V external is equal to EMF minus V internal. Okay, we're saying that the terminal potential difference across the battery will increase. The terminal potential difference across the terminals will increase. Okay, so we're basically looking at what brings about the increase. So if the external resistance has increased, less current will be flowing and EMF is a constant, total current must decrease. Okay, anything around those lines would be perfect. Question number 9. Question number 9, we're almost there. They're telling us that the simplified diagrams below show two electrical machines. We have A, we have B. Then they want us to classify the above machines into a DC motor and generator. So number one, we have A, we have B. We need to classify and give reasons. So A is a generator. Okay, what is, because they said classify the above electron machines into a DC and give a reason in each case. So when you look at it, it's like this handle is for spinning, and then we get the electrical energy. So what we can say is that this generator converts mechanical to electrical. Okay, it converts mechanical energy to electrical energy. Now, when you look at B, it's like it's connected to a DC source. Okay, and if it's connected to a DC source, meaning that this is a DC motor. We had two options, either a DC motor or a generator. So this is a DC motor. And what is the reason? We say it converts electrical to mechanical. Okay, the 9.2, what type of generator is represented? So what type of generator is this? Now, with this generator, we are using the manual approach. So it's going to be a DC generator. Okay, but then the manual part is not the reason. The reason as to why it's a DC is because of the split ring. Okay, there is a split ring. A split ring, we call it a commutator. A split ring, or sometimes we have a split commutator. All right, then name the principle on which generators work. So which principle is that? Okay, so the principle that generators use is what we call the electromagnetic induction. Electromagnetic induction. All right, then which one of the following graphs RS represents the voltage output by the generator? Now our focus is on DC generator. Ne? So a DC generator, which sort of output is it going to have? So anything that is DC will always have these humps. Anything AC will have the sine graph. So graph S is the correct option there. The 9.5, if we have an AC generator that produces a maximum of this much, connected to a heater of 40 ohms, calculate the average power dissipated. So on our formula page, we have a formula as power average. Okay, so the average power just follows the same combination as power. So I can say V squared over R. Okay, but remember this average just works with RMS values. Okay, so meaning that I have to look for the VRMS if I have the Vmax. So come down and say that VRMS is going to be Vmax divided by the square root of 2, which is 311,13 divided by the square root of 2. Then we can do the substitution, okay? So 311,13 over root of 2, dividing it by the 40 ohms. So remember, resistance is always more like a constant. It never changes to maximum or RMS. It's just the current and the voltage. So when I punch this into the calculator, I'm getting 1210. 1210,00 watts. Okay, that is question number 9. Then question number 10, which is the last one. Study the table below, which shows the different colors, okay, of light and the frequencies they emit. So red has this frequency, yellow has that, green and blue, just like that. Define the term threshold frequency. So threshold is like minimum, okay? So we're gonna say threshold frequency or minimum frequency. We're saying this is the minimum frequency of light that is needed to extract or to emit or to remove an electron from a metal surface. Okay, then a photon has this much of energy. Use calculations to determine what type of color. Okay, so for us to get the color, we need to find the frequency. So we can use the Planck's formula and say that this is 10.2 E is equal to HF. Okay, so if our energy is 3,72 times 10 to the negative 19 is equal to H, which is 6,63 times 10 to the negative 34 times the frequency. Let's divide both sides by the Planck's constant, 6,63 times 10 to the negative 34. That cancels that. When I divide there, my frequency becomes 5,61 times 10 to the 14 hertz. So the question is asking which color. Okay, so it's color green. Okay, color green is the emission that we are getting. Okay, then we move on to the next question. They are telling us that the metal, Okay. Metal casing has a work function of this much. So this work function is like the W naught. Which color of light will not release electrons from the surface of this metal? Okay. Now, if this is the work function, we need to determine the threshold frequency F naught, and then compare it with the frequencies that we already have. So come down and say that W naught is equal to H F naught. So 3,32 times 10 to the negative 19 is equal to 6,63 times 10 to the negative 34 times the minimum frequency. Do the needful and divide both sides by 6,63 times 10 to the negative 34. This cancels that. So our threshold is 5 times 10 to the negative 14. Now, if this is the minimum, anything that is above 5,0 is fine, is perfect. What is the question asking for? Which color of light will not release? Okay, anything below 5, so we have a 5, we have a 5,6, we have a 6. So meaning that red is not going to emit. So the answer here will be a red with our calculations. 10.4, explain what effect an increase in the intensity mentioned in 10.3 will have on the release of photoelectrons from the surface. Now, intensity in most cases has no effect, okay? Because what matters is the minimum frequency, the threshold. If you can meet the threshold, then we are good to go. Okay, so we can say that a change in the intensity will not have any effect, will not affect the frequency. So what effect? No change, no effect. Okay, then 10.5, calculate the maximum kinetic energy of the photoelectrons released from the surface when it is exposed to this frequency. Okay, so we need to use the formula for the energy. Okay, and then we know that E is equal to W naught plus EK max. Okay, our E is given as HF, and then W naught will be given as, I think it's the same question that we're looking at, the 3,2 times 10. Okay, so do I need to substitute now? No, let me substitute, it's fine. So the E, we said it's a 6,63 times 10 to the negative 34. And then the frequency we are having is 1,1 times 10 to the 15 is equivalent to the 3,32 times 10 to the negative 19. Question is asking, calculate the maximum kinetic energy. So plus EK max. Do your magic and then transpose everything to one side. So when it's supposed to be subtraction, not a division. Okay, when I multiply this and then subtract that, I'm getting 3,97 times 10 to the negative 19 joules. Okay, so that becomes the maximum kinetic energy. All right, guys, so that brings us to the end of this paper. I wish you guys all the best in your preparation. Be confident, believe in yourselves. It is possible. Then go ace that physics paper on Friday. Bye-bye for now. Let's meet when we're discussing the memorandum to the papers. Bye-bye. The session, I just want us to recap or remind ourselves of what vertical projectile motion is and what exactly can be accompanied or be found with vertical projectile. So we know that if, let's say, an example, if an object is thrown out of the window, maybe a frog that is jumping or a ball that is being kicked around. All these can be regarded as examples of vertical projectile, or basically projectile motion. So in most cases, they tell us that we must ignore the air resistance or the friction that is taking place within the space or within the direction of motion, so that our calculations can make sense. So there was a gentleman by the names of Galileo who made a study about vertical projectile motion, and initially it was just believed that when you throw something, it must just come back straight to the earth as long as you've thrown it, let's say, upwards. Okay, according to this gentleman, he believes any object that is thrown upwards or dropped or projected must always take some sort of a curve, sort of directional movement, which means that this object must have two components: the horizontal component and then the vertical component. So when we talk about vertical projectile, our main focus is basically the vertical component. Okay, so in all of this motion is affected mainly by the acceleration due to gravity, which is 9.8 meters per second. Okay, so we're saying at the same time the projectile can move horizontally according to the principle that this guy discovered. And then when we look at the combination of the vertical and the horizontal, that's when we can get the actual resultant projectile motion or graph. Okay, then what other thing that we need to also talk about will be the definitions that we normally come across, the terms or terminologies under vertical projectile. So number one is what we call the free fall. So any object that is acted upon by gravity. So any object acted upon by gravity is believed to be under free fall. Acted upon by gravity is said to be under, let's say, state of free fall. State of free fall. So in other words, this is motion that is entirely influenced by acceleration due to gravity. And then terminology number two, we can talk about a projectile. What is a projectile? So a projectile is basically the object that starts its motion. An object that starts its motion with basically an initial velocity. Okay, this does not mean that the object has to be just thrown upwards, or it covers everything. It can be thrown upwards, it can even be dropped, or any other scenario. And then we have what we call a trajectory. So a trajectory is basically the path that is followed by a projectile, or the path that is taken by a projectile. That is a trajectory. Okay, and then number four, we have the terminal velocity. So terminal velocity is more like the maximum velocity that is reached by a falling object. I'm just gonna summarize it and call it maximum velocity that is reached by a falling object or object under free fall. And then free falling objects, we said they are mainly influenced by acceleration due to gravity. Okay, so under vertical projectile, we have what we call scenarios that we're gonna focus on. Okay, we can I don't know, I'll call these cases. So the first case is where we find an object thrown upwards. Object that is thrown upwards. That is scenario number one. And then what happens in that, what we need to know, we shall discuss that. Then two, let's say this is thrown upwards, let's from the ground. Okay, and then scenario number 2, an object that is thrown upwards but from a certain height. Same scenario but from a certain height. An example, you stand on top of a tall building and then you throw something up. What happens? That will be like scenario number 2 or case study number 2. Then we also have case study number 3. And this case study, we look at an object that is thrown downwards. Object that is thrown downwards. So in most cases, from a certain height. From a certain height. An example, a platform, a cliff, or even a balcony. Okay, that is thrown downwards with some bit of velocity, whereby the initial velocity is not 0. And then number 4, what if the object is just released? Object is released or just dropped from a certain height, whereby the initial velocity is 0. That is case scenario number 4. And then lastly is case scenario number 5, an object that is released from a moving object. Object released from a moving object. An example, if you're in a hot air balloon that is moving upwards and then you drop something. So whatever object you've dropped is gonna possess the initial velocity. That will be the velocity of that air balloon. Okay, then the other thing that we also need to familiarize ourselves with is the Newton's laws of motion. Okay, we have quite a number and we just need to be really selective in which one to use. Newton's equations of motion. Newton's equations of motion. Okay, so we know that first equation, which is V final, is equal to V initial plus, you can say, acceleration times delta t. But in most cases, we're not gonna call it the acceleration. In this case, since the object is under the influence of gravity, that acceleration A is gonna be turned into the gravitational force, which is G. So in other words, it's gonna be V final is equal to V initial plus G delta t. Okay, where the G is gonna be 9,8. We're saying A is the same as G, which is 9,8 meters per second squared. This is equation number 1. So this can only be used if we don't have any displacement. So if there is no displacement that is involved, then that is the equation to use. Then case scenario number 2, or the equation number 2, if we have Vf squared must be equal to Vi squared, initial velocity squared, plus the 2a delta y. It can be delta y since we're just focusing on the vertical projector. The distance moved is in the y direction. So this is equation number 2, and we only use this if we don't have any time. Okay, if you're not using time, then this is the equation to use. And then lastly, we have change in y, or delta y is equal to Vi times delta t plus a half a delta t squared. But what we are saying is that the a is gonna be replaced with a g. In most cases, a is gonna be replaced with a g. Now, depending on the direction of motion, okay, because we need to take also consideration when doing that. So I usually prefer to take upward motion to be negative, okay, if it is upward, and then downward motion to be positive. So if we're focusing on downward, then this will be a plus, plus, and plus. Then if it's an upward motion, this can be minus, minus, and minus. That is my approach. It's also believed, we know it can also work, whereby someone can take the downward motion to be negative, okay, and then the upward to be positive. You just need to state your case. You'll always get the same answers in whatever calculations you're gonna do, for as long as you maintain the signs that you deciding to go with. Okay, so having looked at that, I believe we're good to start with the questions. Okay, I'm just gonna go through some questions. If time allows, I'll cover as much as I can. Okay, question number 1. We're being told that a cricket ball of mass 156 grams is dropped from point A on a tall building that is 15 meters high, and then it strikes the concrete pavement, and then it bounces off. And then it bounces off. So this object is dropped, it falls, hits the floor, and then bounces off to a height of 4, maximum height of 4. Then they're asking us to calculate the velocity with which the cricket ball strikes the pavement. So for as long as an object is dropped, then the initial velocity is going to be 0. And this question is asking for the final velocity. So we're gonna say our initial velocity is 0, our final velocity is what we don't know, or what we're looking for. The only thing we've been given is the displacement, change in y, is being dropped from a height of 15 meters. Then we need to select which equation are we going to use. Since our focus is v final, we have the v initial and we have the displacement. So the equation to use would be the vf squared is equal to vi squared. Since the object is being dropped, we said I'm going to take positive to be the downward motion. This is 2g delta y. Then I'll do my substitution. So that's going to be our vi, which is 0 squared plus 2 times 9,8 times the displacement, which is 15. Okay, when I put that into my calculator, I'm just getting something like this is 2 times 9,8, is that true? And then times 15. So that gives me 294. So vf squared is 294, and then I need to find the square root. Okay, then the square root of my answer gives me 17,15 meters per second. Okay, that is question number 1. Then question number 2, 1.2. If the effects of air friction are not ignored, in other words, if they are put into consideration during the fall of the cricket, how would the value that you calculated here change? Will it be higher, will it be lower, or will it stay the same? So guys, what do you think? If there is resistance involved, if there is friction involved, what effects does friction have in the final velocity? So in this case, I'm gonna go for lower. Why? Because friction, we said, is a force that opposes motion. So for as long as it's trying to oppose motion, because the ball is falling downwards, friction will be acting upwards. So which means this ball is gonna fall with a lower velocity. Okay, and then 1.3, they're telling us that the cricket ball is in contact with the concrete for about 0.8 seconds. So that 0.8 is more of a reaction time. Okay, so if we ignore the effects of air friction and we are taking downward motion as positive, okay, calculate the impulse. What do we do when we are getting impulse? We know that from your momentum, impulse and stuff, you might have said that our F net is the same as change in momentum, the rate of change in momentum, something like that, delta P over delta T. Does that make some sense? F net is this. So when we talk of impulse, it's the change in momentum that we're focusing on, which means our change in momentum will be the F net times the delta T. But what is our F net? We know that F net can also be written as ma, m times the acceleration. And acceleration can also be expressed, since in this case we don't have the acceleration of the object, we can use the velocities, okay? And say the mass, which is v final minus v initial divided by the time. Mass times acceleration, which is v final minus v initial over t. We can use that as well before we can get to the actual answering of the question. Okay, so I'm just gonna erase this and just start over. Okay, so what I need to first of all find, what is the initial velocity or the final velocity that we're focusing on. So for as long as the cricket ball is in contact with the pavement for this much, and we're taking downward, calculate the impulse of the cricket ball on the pavement. So our final velocity is going to be assumed to be a 0. Okay, as soon as this ball strikes the ground, and then takes some time. Okay, initial velocity, I don't know that. My g is gonna be 9,8, and then I'm going to look at what's this. I'm gonna look at my displacement to be, is it 4? Yes, I'll look at my displacement to be 4. It makes sense though. Yeah, displacement is gonna be 4. And then from Vf is equal to Vf squared is equal to Vi squared plus 2g delta y. When I try to do the substitution with the 0, this is Vi squared plus 2 times 9,8 times 4. So now that I'm finding the velocity with which the ball started to rise up. Okay, so we are saying the ball strikes. It takes some time just on the pavement, and then it goes up to a height of 4. Okay, so the velocity with which the ball left the ground or the pavement is what I'm looking for. So when I do the maths here, this is gonna be, why am I taking 4? Why am I taking 4? Because it's moving upwards now. So it's gonna be negative 4. Okay, so that is 2 times 9,8 times 4, which is 78,4. So 78,4 is equal to the Vi squared, and then I find the square root of that, which is 8,85 meters per second. So this is just the initial velocity with which the ball is gonna leave the pavement. Then I'll apply my F net and delta P. Okay, so we know that our F net times delta P is equal to the change in momentum, and we said this change in momentum is the same as m v final minus v initial. When we do the substitution, what was the mass of the ball? They mentioned something like 156 grams. Change that to kilograms, it will be 0,156. What is our final velocity? It's negative 8,85. Since it's moving upwards, we are subtracting the initial, which was our final when the ball was striking the ground, which is 17,15 since it was taking the positive sort of direction. Okay, when I work this out, I'm just gonna get something like negative 4,056. This is mass, which is kilograms per meter squared. So since we're focusing on impulse, it's gonna be 4,056, but in which direction? It's gonna be upwards. Okay, then 1.3.2, they want us to get the net average force that is exerted. Okay, so since we know that our F net is delta P over delta T, our change in momentum is the negative 4,056, and we're dividing it by the time. The reaction time was 0,8 seconds from the information that we were given. So we divide it by 0,8. If that happens, then we're going to get negative 5,07 newtons. So this can also be written as 5,07, but upwards. Okay, so the force is going to act upwards. And then 1.4, they want us to sketch a position time graph. Now guys, we have different types of graphs when it comes to projectile motion. We have what we call the position time graph, we have the velocity time graph, and we also have what we call the acceleration versus time. Now we need to know how all of these look like. Okay, so if it's a position, in most cases it will take form of a curve, and then if it's a velocity time graph, we normally use straight lines to draw that. Okay, no, it's fine, we shall probably look at the different scenarios. So sketch the position versus time of motion, which can go from the moment it is dropped up until it reaches the maximum height after the bouncing. So what we need to remember, they said position time graph. So on our y-axis, we're going to have our positions, and then on the x, we're going to have our time. So this is position, which position can also be represented as the y. Okay, and the question is, at what height did the object start falling? Okay, this position is in meters, this time is in seconds. So the object started falling from a height of 15. Okay, and then the object dropped. We don't know the time it took, we don't even need it at the moment. Then this object took some time on the ground, on the pavement, and then it rose again for a certain height, which height we said was 4. So for as long as we have this, then we're good to go. So position time graph will always be a curve or made of curves. So this is the reaction time. Okay, then 1.5. The cricket ball is now replaced with a softer ball, okay, of similar mass. They want us to state how the net average force exerted by the concrete pavement on the softer ball, with your answer is meant to be 1.3.2. We need to write only greater, smaller, or stays the same. So one thing we need to know is that from F net being delta P over delta T, change in momentum, we know that this net force is inversely proportional to the time. So if we are dealing with a soft ball is going to take more time on the pavement floor. In other words, the reaction time is going to increase. Okay, so when the reaction time increases, the net force decreases. Okay, so we're going to say delta T increases, which decreases the F net. So in other words, state how the exerted force is going to say smaller than. Okay, so the answer will be smaller than, because delta T increases, which decreases F net, because we know that delta T is inversely proportional to 1 over delta T. Okay, guys, that is question number 1. Then question number 2 is more or less the same thing. We've been given a position time graph of a tennis ball. Okay, how do we approach a question when a graph is being provided for us? So they're telling us that the position time graph of a tennis ball that was thrown vertically upwards from a second floor of a school building shown below. Ignore the effects of friction. Okay, the height of the second floor is 6.5 meters. The ball rises 0.9 meters from the height of projection. Okay, so from here up to this point, that is 0.9 meters extra. Okay, before it starts to fall to the ground, so which means maximum height, an extra 0.9 meters. Okay, write down the magnitude and direction of acceleration of the ball while it's moving upwards. So the acceleration of the ball will always be 9.8 for as long as it's under projection or projectile motion. Okay, and this acceleration acts downwards. Regardless of whether it's projected up or down, it must always act downwards, since that is the initial direction of gravity. Okay, and then they want us to calculate T1, the time it takes the ball to reach the maximum height. Okay, one thing we know about maximum height is that the final velocity has to be a 0. That's one thing we need to know. Final velocity has to be a 0. So now, since we've been given displacements, we've been given the G is known to us, but we're focusing on the displacements. Let's say the distance traveled, Vy, is 0.9 meters. What else do we know? We know that our V initial, is it going to be a 0? It was projected vertically upwards from the second floor. Okay, so I'm not going to assume that. So I'm going to use this equation. Vf squared is equal to Vi squared plus 2G delta Y, something like this. So we are saying at the maximum height, final velocity is 0. Is that true? Yes. But the question is asking for the time it takes Let me see if I can get an equation that has time straight away, so that I don't have to waste a lot of time. This is Vi delta t plus a half delta t squared. And then F is Vi plus a delta t. I have that. Do I have the initial velocity? No, I have the initial position. It's not gonna make sense. So which means I need to first of all get the initial velocity. Okay, so my Vf is 0, my V squared I plus 2. Now the G is going to be negative 9,8 because the object is being projected upwards. An upward projection, I normally take G to be my negative. Okay, and then times the distance that the object traveled, which is the 0,9. Okay, when I sort that out, when I multiply that, I'm just going to use this to be positive since I've already considered the G to be negative. Okay, that is 2 times 9,8 times 0.9. That gives me 17,64. When I transpose that, Vi squared is equal to 17,64. Find the square root. The square root of the answer is 4,2 meters per second. So this is the initial velocity. So having obtained the initial velocity, then I can use this equation here, the first equation of motion, and say my final velocity is 0. My initial is 4,2 plus, it's gonna be negative 9,8 t. I hope that makes sense. When I move, if I transpose, I have 9,8 t is 4,2. Divide by 9,8 over 9,8. Okay, so 4,2 divided by 9,8, I'm getting 0,428 seconds, which will be more or less like 0,43 seconds. Okay. That is 0,43 seconds. So that is that. That is doing it in 2 steps. But someone can even use this second equation, this, since you're looking for t, and then you get that straight away. Okay, and then 2.3, they want us to calculate the initial velocity of the tennis ball at the instant that it's released. At the instant that it's, so we've already calculated that, okay, which means we've used a very long approach, which has already even answered the next question, but it's fine. So we say this is a 0, Vi squared plus 2 times the 9,8 negative times the 0,9. Okay, and what did we say? We just transposed that. So Vi squared is 17,64. Then when we took square roots, our Vi became 4,2 meters per second. There's no harm doing that again, as long as it's going to give us the max that we desire. Remember, all questions normally have different approaches, quite a number of approaches. Then 2.4. Now they want us to sketch a velocity time graph. Okay, they gave us a position time graph, they want us to sketch a velocity. So we said velocity is always made up of straight lines, no curves. Okay, then I can put my time somewhere here, which is in seconds. So if this is the origin, what was the initial velocity? The initial velocity was 4,2. the one we've just calculated in the previous question. And then it took some time, which was 0.42 seconds, so 43 seconds to get there, which we can label as our T1. And then the graph continues. So it's just a straight line from here into that sort of direction. We don't need to mark this off as 0.43. You can if you have time, no problem. So it's calling this point A, where the ball started from, and then point B, which is more like the maximum height. At the maximum height, that can be point B, and so on and so forth. So after the maximum point, this section just tells us the direction or the velocity of the ball when it's falling down. So that is what one would do. Someone say, all of this for 4 marks. Yes, for as long as you have a straight line, not a curve, you get a mark. Then for as long as this part is shorter than the other part, because remember, this A to B is just the section from point of release up to the maximum point, which was quite a small distance. Okay, and then the 4.2, for as long as you've indicated it, you'll also get a mark. And then the time T1, which is the 4.3, you get the last mark. Okay, then let's look at question number. We need to do this because I feel like it looks more or less the same as what we've done, but it's fine, not a problem. We can look at it. Then question number 3, they're telling us that the sketch below shows the motion of a ball that is thrown vertically upwards from a balcony, and it takes 0.4 seconds, okay, to reach the highest point, after which it falls down past the balcony, boom, up to that. Then from the graph, how high is the balcony from the ground? So the ball is projected from the balcony, which means the distance from here up to there. That's how high the balcony is. So it's just 8 meters. And then 3.2, without any calculation, what is the numerical value of T1? T1, somebody? Remember, this is more like a parabola. And this 0.4, where the time is at the maximum, or the velocity is 0, that is the maximum height. This is acting as our axis of symmetry. So if this is 0.4, even this must be 0.4. So which means that is 0.8 seconds without any calculations. So that is just the logic. And then 3.3, they want the initial velocity. So we shall use more or less this, can use the first equation and say V final is equal to Vi plus A delta T, the initial velocity. So we can use the final velocity at this point of the maximum. Okay, so I'm gonna take the V final to be 0. Vi is what I need. I'm gonna say plus, I'm gonna use negative 9.8 times my delta T 0.4. Okay, so 9.8 times 0.4, I'm getting 3.92. Okay, then Vi minus 3.92 is equal to 0. Then move it that side, which means the initial velocity is 3.92 meters per second. Which direction? It is basically upwards. It's upwards. Okay, and then 3.4, they want the maximum height above the ground that is reached by the ball. Now, since they're asking for maximum height, that is like displacement. Which displacement formula can we use? We can use. I don't know. Let's use the second equation, which is delta y is equal to vi times delta t plus a half a and then delta t squared. I think this can work. So they want the maximum height above the ground, so we're looking for delta y. So what is our initial velocity? We got it as 3,9. So guys, regardless of what value you get, for as long as that value is gonna be used in the next question, please use it, even if it's wrong. Okay, it will do you some good for consistency's sake. So the time was 0,4 seconds plus a half, since the direction of projection was upwards, gonna be negative 9,8, and then we're saying we're multiplying that by 0,4 squared. And I use my machine, 3,92 times 0,4 plus a half times negative 9,8 times 0,4 squared. I'm getting 0,78 meters. So this is just from the point of projection. So 0,78. So just from here up to there, that is 0,784. Now, since they're talking about from the ground, the distance from the ground or the height from the ground, it's going to be the 8 plus the 0,784, which becomes 8,784 meters. And then lastly, no, it's not lastly, 0.5, calculate the magnitude of the final velocity of the ball when it reaches the ground. Okay, so in this case, we can look at number 1, either break down the journey into 2. Someone may choose to focus on the second part of the journey of the ball, which is like from the maximum point up here. Since we know that at this point, the velocity is 0, so which means this will be our initial velocity, and we're looking for the final velocity, which will be 0. This one, the initial velocity. The time it took, we don't know, but we can get an appropriate formula. Or alternatively, someone can take the entire journey of this ball and then still get to the same result. So in this case, I'm just gonna look at just from the maximum height, the first scenario. So if I use Vf squared is equal to Vi squared plus 2a delta y. Since I know my maximum height, I can use that. So they want the final velocity, so this is Vf squared. Initially, at the maximum height, the velocity was 0. So that's going to be 0. Plus 2, our acceleration is negative 9,8. And then our height is 8,784. You could round that off to 2 decimals, there's no problem. So that is 2 times negative 9.8 times the 8.784. I'm getting, does that even make sense? Yes. I'm getting negative, no. If I use negative, then that means I'm using the initial root. But if I'm focusing on just the section from the maximum to, then this is meant to be positive. So that is 172,1664. That is Vf squared. And then I can find the square root of that. Square root, my answer, I'm getting 13,12 meters. So that is going to be our maximum velocity or terminal velocity. So we said alternatively, someone can use that other route of the entire journey. Okay, so if you're using the route of the entire journey, then your displacement is just gonna be 8, because from the point of projection up to the same point of projection, the displacement is gonna be 0, and then we focus on just the 8. Okay, if we try that out, we said our initial velocity. Now let's try it out and see. Maybe let me just jot it down here. Just for the sake of space, I'll erase it. Okay, I'm using just the same thing. Vi squared plus 2a delta y. So we got our initial velocity as 3,92. That's what I want to use. So 3,92 squared plus 2 times now negative 9,8 times 8. 3,92 squared. Is this gonna make sense though? Something is fishy, something is fishy, something is fishy here. Guys, no, it's okay. Let's just ignore that and just use that formula. There's no need for second option. How does it test that? It's okay. Then 3.6, they want us to draw a velocity time graph. Okay, so if this is the velocity, and then that is the time in seconds, velocity in meters per second of the motion of the ball, indicate the following: initial velocity, final, and the time taken to reach the maximum. So our initial velocity, we said, was 3,92. Okay, and then the final velocity, we said it's 13. We said at maximum, what is the time? We said that was 0,4. So we're just gonna draw a line. It must be longer. And then we can put the 13 down. Then we can call this 13,12, but in the negative. Okay, it's not a big deal for as long as you have the initial or you have these 3. It's a mark for each. Okay, then we move on to the next question. Question number 4. Question number 4. What do they want us to do? They are telling us that a boy kicks a ball, okay, vertically upwards from a height of 0,6 meters above the ground. Then the ball moves past the top of the building 21 meters higher than the original point from where it was kicked. And then the ball hits the roof in 3,1 seconds after it was kicked. Then the ball bounces off the roof and then it comes to rest. So the ball is kicked, it goes up, past, reaches maximum, hits the roof, bounces off, and it gets to rest. Okay, then they're asking us to write down the magnitude and the direction of the acceleration of the ball at point X. Where is point X? So point X is not indicated on the question, but regardless of where that point is, even if it's there, even if wherever it is, I don't know whether it's that. So that's gonna be just 9,8, and the direction must always be, we say, downwards for as long as it's gravity, as long as it's free fall. So it's 9,8. I'm sorry guys, it's 9,8 meters per second squared. So now what about the units? Then 4.2, calculate the magnitude of velocity with which the ball was kicked. So we're looking for the initial velocity. What do we have in question? We know that This is 0.6 above, so which means the ball is gonna travel 21 meters from where it was kicked. Okay, and it takes 3 comma where the ball hits the roof of the building, 3.1 seconds after it was. Okay, so I'm gonna look at the 21 from there up to there and then see. So if I look at my downward motion as positive, I can use delta y is equal to vi times delta t. Can use a half a delta t squared. Why? Because the question is asking for initial velocity, which is the vi. Only thing we have is the time and the displacement. Okay, so my displacement is gonna be the 21, which is negative. Initial velocity, I don't know. My time was 3.1, and then a half, my a is gonna be 9.8. Oh, why am I doing that? It's okay. And then the t is 3.1 squared. I'm using negative 21 because I'm taking the downward motion to be positive, which means my displacement when it moves up will be negative. I am not necessarily focusing on the g. Okay, when I do the substitution of all of this, I have a half times 9.8 times 3.1 squared. That's gonna give me 470. Okay, no, not 470, sorry. It's 9.8. It's 47. So the whole of this is giving me 47,089. And then I must move it that side. So say plus 21, which is like a 68,089. And then when I divide this by 3.1, I'm getting 21. So initial velocity is 21,96 meters per second, or any other acceptable option or equation can be used. And then calculate the maximum height that the ball reaches above the ground. Now, since the initial velocity that we're focusing on is 21,96 meters per second, they want us to get the maximum height, and we said at the maximum height the final velocity must be 0. We're looking for delta y. Okay, so we can use v squared, v final squared is equal to vi squared plus 2a delta y. Our v final, that is a 0, is equal to, I'm gonna say 21,96 squared plus 2 times our a, which is 9.8. I'm gonna call it negative because I'm taking gravity to be downwards. Okay, now I move it that side, it's gonna be 19.6y. What is 21,96 squared? Getting 482,2416. Then divide by 19.6. Divide by 19.6. That cancels out, and then my y becomes 24,60 meters. So this is the maximum height that the ball is gonna reach. And then 4.4, we're being asked is referring to the sketch refer to the sketch and state whether the collision of the ball on the roof is elastic or inelastic. So since the ball reached the maximum height, it bounced off. Okay, so wait a moment. Is that question done? Calculate the maximum height that the ball reaches above the ground. Above the ground. We're not done. This 24 is, so remember, the ball was kicked from a height of 0.6. So which means we have to add the 0.6 also. Sorry. Plus a 0.6. Then that becomes 25.2 meters. Thank you. Then 4.4. We were saying the ball is gonna reach the maximum height and then it drops to the roof, just one bounce, and then it comes to rest. So is it elastic or inelastic? So I'm gonna say it's inelastic. The reason being, from the maximum height, the ball bounces, but the bounce just reaches a height that is lower than the maximum and then gets to rest. So we can say that the ball just does the bouncing. Ball bounces lower. Lower than the maximum height before. Lower than the maximum height that was reached. So I did mean that the ball decided to bounce higher, then it was going to be elastic. Okay, and then 4.5, they want us to sketch position. Remember I said position is a curve. Okay, position is measured in meters, and then time is measured in seconds. Okay, position time graph for the complete motion of the ball from the moment it was kicked until it comes to rest. Okay, so if I'm to look at it, remember the ball is gonna reach the maximum. We say 21. So if it's a 21, okay, we have 21, and then which other height do we have? Okay, 4.2. It's 24.6 minus 21, which is 3.6, which means the height of the bounce is 3.6. So in other words, it went up. This is gonna be like 21, and then there's an extra 3.6 for it to reach the maximum where the velocity is 0. So I'm gonna take this to be my 21 negative. Okay, and then to just move, it reaches a maximum height of how many meters? 3.6, because we say 24.6 minus the 21, which is 3.6. Okay, and then it bounces off. They told us the bounce takes place at a time of 3.1 seconds. Okay, and then it takes also another bounce. Do we know that time for the next bounce? We don't know it, but it does before it comes to rest. So what we need is the initial starting point, the maximum point it reached, and then that other point. Okay guys, so that is question number number 4. Question number 5. Question number 5, I think I'll have to stop at a question below what I'd prepared. So this is more or less still the same, but it's okay, we can look at it. They're telling us that Sandile, who is standing on a platform, throws a small metal ball vertically downwards, vertically up from the height of 1,73 above the ground. So this is 1,73 up. Okay. At this velocity, the ball travels past the top of the building and returns to the hand, who is still at that same height. Ignore the effects of friction. Sandile is somewhere here. So with what speed does the ball strike Sandile's hand? So the ball was projected at 8. So since Sandile is still just at the same point, we're gonna say it's 8 meters per second. Nothing changes. Since we are ignoring friction, it's just gravity that is doing the work. Okay, using the equation of motion and not energy principles, calculate the maximum height that the ball reaches above the ground. So Vf is gonna be 0. V initial, we have it as 8. A, which is G, is 9,8, and then the height is what we're looking for. So I'm gonna say Vf squared is equal to Vi squared plus 2 times acceleration delta y. Then we say that maximum height velocity must be 0. 0 squared, initially it's 8, and then since I'm projecting it upwards, it's gonna be negative 9,8 times the y. So 2 times 9,8, that's 19.6. I'm gonna transpose it that side. So 19,6y is equal to 8 squared, which is a 64. Then I divide by 19,6. Okay, 64 divided by 19,6, I'm getting 3,27. 3,27 meters. That is from the point of projection. Okay, from here, or from wherever Sandile is, up to there. But now from the ground, since the question is talking about the ground, which means I'll have to add the 1,73 meters, which will make it, I don't know guys, help me, 1.73, which is 4,9995, which is, we'll round it off, it's just gonna be 5 meters above the ground. 5 meters above the ground, 5 meters above the ground. Okay. And then 5.3. So if a window on top of the building, on the top floor of the building is at 2,5 meters, calculate the time it's gonna take for the ball from the moment it was thrown to pass the top of the window on its return. So this is a quadratic, guys, a quadratic time it takes to pass the window. Okay, let's see. So we must be able to get at least two values if possible. So we can start by doing what? We need to get the final velocity first of all, because in this case we're not focusing on the maximum height, we just want the velocity after the 2.5 meters of distance, or distance traveled by the ball. So that's going to be 8 squared plus 2 times 9.8 negative times the 2.5, because that is the distance from Sandilay's hand to the window. Okay, when you sort this out, 8 squared plus 2 times negative 9.8 times 2.5. Oh Lord, what's going on? I'm getting 15 and square root of 15, so this is 15, and then square root of 15 is 3.873 meters per second. Okay, this is like our final velocity. And then if I use Vf is equal to Vi plus 80, or A delta t. Our V final, we have it 3.873. It's going to be negative. And then our initial velocity was 8. Our acceleration is negative 9.8 times a certain time. Okay, so when I move the 8 that side, it's gonna be minus 8, which is, I missed it, 3.873 plus 8, that's 11.873. Negative is equal to negative 9.8. We now divide by 9.8 over 9.8. That cancels. What do we have? Getting 1.21 seconds. So they say exactly the time taken for the ball from the moment it was thrown to pass the top of the window on its return to Sandilay's hands. So I'm getting 1.21 seconds. Okay, the reason as to why I'm using the 2.5 is because that top part is going to cancel out to be 0 in terms of the displacement. Okay, since this part is going to be the positive displacement and then this negative displacement is going to cancel it out. That's why we're going to just stay with the 2.5 meters. Then 5.4, taking upward direction as positive. Draw sketch of position. Time again. Guys, we said position is a curve. Taking upward as positive. Time is in seconds. Okay, so if we take our position in that sort of format, what do they want exactly? They want us to draw the ball's motion from the moment it left Sandilay's hand until it lands back into his hands. Oops, okay. That is 0. That's pretty easy. Something like that. So what is the maximum height that, or the maximum position that we got? Somebody help us. It was 3.27. 3.27. So just indicate this. 3.27. Is there time that is needed? How long did it take? Do we know that? Is the window calculate time taken? And that is for the window. Nothing. So you can just leave it like that. So for as long as we have the correct 3.27, as long as the shape graph starts from 0, because that's our displacement, the ball was not moving at that point. As long as the shape is correct, and then we label this correctly with the correct units, then we're good to go. Question number 6. I don't know. I feel like we should skip this, or I don't know. Skip it, do it. Skip it, do it. It's fine. Let's attempt it and see. So the ball is thrown vertically upwards at the velocity of 4 meters per second. 4 meters per second from the roof of a building with a height of 10 meters. and then the ball strikes the ground and rebounces to a height of 3 meters. Okay. Okay guys, let me work this out, but if the next question is more like the same, I'm gonna skip it so that we look at just a different sort of scenario. Okay, so they want us to get the time taken for the ball to reach the maximum height. So we said maximum height, final velocity is 0. So our initial velocity is 4 meters per second. Okay, the ball strikes and rebounds to a height of 3 meters. So this is pretty quick. We can say Vf is Vi plus A delta t. Our V final is a 0. Our initial is 4. Since we're throwing the ball upwards, it's going to be negative 9,8 times t. Move the 4 that side, which is 9,84. So 9,8 t is equal to 4. And then divide both sides by 9,8. 4 divided by 9,8. I'm going to get 0,41 seconds. If I round that off. And then they want us to get the maximum height that the ball reaches. So the maximum height, we need to get an equation that involves displacement. So I can use what just happened? Okay. So I'm saying I can use my delta y is equal to Vi delta t plus a half a delta t squared. I want the height. Do I have the time? Yes, the 0,4. Acceleration, I have it. So it's going to be 4 times 0,41 plus a half times negative 9,8 times 0,41 squared. I hope that makes sense. 0,4 plus 0,5 times negative 9,8 times 0,41 squared. I'm getting 0, is that true? Let me just redo it again. 4 times 0,41 plus a half times negative 9,8 times 0,41 squared. Okay, I'm getting 0,82 meters. Okay, so that is our maximum height. And then they are telling us that the ball strikes the ground 1,09 seconds after it was thrown and remains in contact for 0,2 before bouncing off. We need position versus time. Use the ground as a reference and indicate the following. So when they say indicate the following, this is what they're going to mark. Okay. So this is position in M. I'll say this is my time in seconds. So if that is a 0, at what point did the projection start? This ball was projected from 10 meters. So which means our story must start from a height of 10. Okay. So we're saying, I don't know, let me just throw something small. That's a 10. And then this ball is gonna move up to the maximum. What do we get as our maximum height, guys? It was 0,82. So 10 plus 0,82, that's gonna be 10,82. And then this moves. Okay. It hits rock bottom. They are telling us it spends some time. So at what time does it hit the ground? Strikes the ground at this. So this is 1,09. Okay. stays on ground for 0,2. So 1,09 plus 0,2 is gonna be 1,29. Okay, and then it just bounces off to a height. Did they give us that height within the question? Yes, to a height of 3, which means this graph must stop at 3. So this must be at 3. It's just that. As long as you represent the height from which it was thrown, it's a mark. Maximum height reached is a mark. The height reached by the ball after bouncing the 3 meters, so it's a mark. And then the time it takes to strike the ground, it's a mark. Contact time, it's a mark, because the difference between that would be your 0,2 seconds. Okay guys, that is question number 6. Question 7. Okay, this is interesting. This is interesting. Telling us that ball A thrown vertically upwards from the top of the building, that is 8 meters high, at the velocity of this. At the same instant, there is another identical ball that is thrown upwards. So this goes down, and then this one goes up. Okay, it's thrown at the same kind of thing. So I'm gonna just summarize this and say ball A and then ball B. The height, initial velocity, say VI for both balls, telling us A is at 12. At the same instant, B is thrown upwards with a velocity of 30. A and B pass each other after time, so they will be equal to, or the distance traveled will be equal after this amount of time. Then give the direction and the acceleration of B while moving upwards. So one thing we said, they want the direction. We said direction of the acceleration. Acceleration will always act downwards. Okay, then they want us to calculate the velocity of B, ball B, the moment it passes ball A. The velocity that A or B passes A. Okay, so I need to get the final velocity first of all. Final velocity that B is gonna be traveling with. So I'm gonna say V initial plus A times the delta T. Okay, so my initial was 12. Said calculate the velocity of B. Guys, I'm sorry now. We're looking at ball B, which is 30, not 12, plus the 9,8, which is gonna be negative. And then what distance is traveled? We said ball A and B pass each other after 2,13. So I'm gonna multiply that by 2,13 because I know they're gonna meet or they're gonna pass each other after 2,13 seconds. Then I'll do my substitution into the calculator. 3 plus negative 9,8 times 2,135, which is 9,077, which can be rounded off to 9,08 meters per second. Which direction? It's moving upwards. Okay. Then I'll calculate the distance between A and B. 2,5 seconds after it was projected. Okay. So I'm gonna use delta y is equal to VI delta T plus a half A delta T squared. Since they're asking us for distance, we know the VI, we know the T's. Okay, they gave us the T as 2,5. Acceleration, we know it. Okay, so I'm gonna look at probably both balls and see what's going on. There's ball A and then there's ball B. So if I focus on A, my displacement is gonna be our initial velocity was at 12, and the time that we're looking at is 2,5 seconds. And then plus, remember ball A was being thrown downwards, so the 9,8 is gonna be looked at as positive, and then times 2,5 squared. Okay, 12 times 2,5 plus 0,5 times 9,8 times 2,5 squared. That is giving me 60,625. 60,625 meters. So that is how far ball A would have traveled. And then when I look at ball B, okay, if I look at ball B, let me say what is 80 minus 60,625, which is 19, something. Oh, that makes sense. Calculate the distance between A and B. After this kind of time, let me just dissect this. So this would have traveled that much, which is 60,6 something. So what is left is 19,375. Okay, now I'll visit that again. Let me look at B. When I look at B and use the same kind of approach, it's gonna be my 30 times 2,5 plus a half times negative 9,8 times 2,5 squared. Okay, same 30 times 2,5 plus a half times negative 9,8 times 2,5 squared. That gives me 44,375 meters. So this is above the ground. That is above the ground. Okay, let me just do this. Okay, so I'm gonna look at B. So if B has traveled 44,375 from the ground, and we are saying A traveled as far as the 60, something and reached here, and what is left below the ground, we said it's 19,375. If I get my 80 minus the 60,625 to get what is left at the ground, so that for me to get what is shorting, I'll focus on the 19, something and this 44. I subtract the two to get the distance between. So 44,375 minus the 19,375, and then I get 25 meters. So it's just 25 meters between the two balls. Okay, then they want position time. Oh Lord, these people have position time. So this is position in meters, and then we're saying this is the time in seconds. Okay, so we have two balls, remember. One ball is starting from 0, another ball is starting from a certain height. which is 18. So this ball is gonna move in this sort of direction. Okay, I'm gonna use a different color for other balls. So which ball started from 0? It's ball B. I'll label this as a B. And then A started from somewhere there. And then it's gonna hit the ground. So we're saying at this point, when they pass each other, we were told that time is 2,135. 2,135 seconds. Okay. So for as long as we have this position in meters or displacement delta y in meters, time in seconds, and all of that, then we're good to go. Then question number 8. We've seen this, guys. We have seen this. I don't know. I'll beg to skip it. Should I, guys? Yes, I think I'm gonna skip it because it just looks the same. When you look at our first question, when you look at the second question also, it's just the same sort of approach. So I'm not gonna do that. Let me just go to question 9 and wind up. Okay, so same question number 9. Ask is question 8. Next time. Okay, question 9. They're telling us there is a girl that stands on a platform in a classroom. She throws a ball vertically upwards to the floor, hoping that the ball, after it bounced on the ceiling, will hit the ceiling. What's going on? A girl stands on a platform in a classroom. She throws a ball vertically upwards to the floor. Okay, so this girl is standing somewhere here. Around source case, I don't know how to draw girls. Okay, she throws the ball to the ground, hoping that the ball, after it had bounced from the floor, it would hit the ceiling. Okay, then it's making sense. So she throws the ball with the speed of this. So our initial velocity is 8 meters per second, the height from above the floor. Okay, so that is the platform. Okay, we need to ignore the air friction, air resistance. Then they want us to write down the magnitude and direction of acceleration of the ball immediately after it left the hand. So acceleration, guys, it's a giveaway, this one. Direction, downwards. Acceleration, downwards, it's a must. The 9.2 is the motion of the ball while it's moving downwards towards the floor. Is it free fall? Yes or no? The answer is a yes. Since we are ignoring the effects of air friction, and this ball is just falling under the influence of gravity. So we are saying only gravity. It's only gravity that is acting on the ball. Only gravity acts on the ball. Or we can look at the influence of gravity on the ball, or the ball is moving under the influence of G. The 9.3, they want us to get the magnitude of the velocity with which the ball hits the ground. So magnitude with which the ball hits the ground, they want us to get the VF, final velocity. We said our initial was 8. Initial velocity was 8. G is 9,8. Do we have the time it takes? Anything? They only gave us the height, which means the displacement is, guys, displacement is 1,8 meters. So we can use the VF squared. Yeah, VF squared is equal to VI squared plus 2A delta y. We're looking for VF. Okay, so our VI is 8 squared plus 2. Since the ball is dropped down, so it's gonna be positive 9,8, and then the height is 1,8. So 8 squared plus 2 times 9,8 times 1,8. That gives me 99. So VF squared is 99,28. Then I must find the square root. So square root of my answer is 9,96. Okay, 96 meters per second. So that is the final velocity when the ball strikes the ground. Okay, then 9.4, how long does it take the ball to hit the floor? So we're looking for the delta t. Since we have our VF, we can even use that first equation. The VF is equal to VI plus the A delta t. I feel that is way quicker. It's VI plus A times delta t. So our VF, we said it's 9,96, is equal to the initial velocity, which we said was 8, plus our acceleration, which is 9,8 t. Positive since the ball is being dropped. Move the 8 that side. 9.96 minus 8 is going to be 1,96. 1,96, then divided by 9,8. So which means t is 2 seconds. Is it 2? Wait, 1,96 divided by 9,8 is 0,2. 0,2 seconds. Okay, and then the ball bounces inelastically on the floor. This simply means it's just gonna bounce off below the height of projection. So it bounces off inelastically on the floor where the speed of the ball decreases by 20%. And then the ball is in contact with the floor for 0,01 seconds. And they want us to determine by means of calculation whether the ball will reach the ceiling after it bounced off. So inelastically simply means the height kind of decreased compared to what was expected. Now, since they gave us 20%, they are telling us that it decreases by 20%. So someone can find 20 of the final velocity, which we got as 9,96, and then you subtract 9,96 minus this 20 over that. So it's 9,96 minus 0,2 times 9,96. I'm getting 7,97. Okay, that is 7,97. So this is gonna be the new velocity. Okay, they want us to determine whether it will reach the ceiling. Remember, our ceiling is at which height? 3,5 meters. So we need to find the displacement and see if our displacement is going to be 3,5. Okay, so if we get VF squared is equal to VI squared plus 2 times A. Oh God, so I think I'm tired now. I said A delta Y. Okay, we're looking for the displacement. We have the acceleration, we have the initial, we have the final. So we're looking for the maximum height that the ball is gonna reach. And the maximum height, we said velocity will be 0. So 0 is the same as 7,97 squared. Now someone will ask, why are we using this? Remember, as the ball hits the ground, it spends some time there, the velocity decreases, and then the velocity with which it leaves, the velocity with which it bounces off. So let's say there was no 0,01 seconds. Then the velocity with which it hits the ground would be more or less literally the velocity with which it leaves. So in as much as it was the final velocity for the first journey, it's going to be the initial velocity for the next journey of the bounce. Okay, 2 times 9,8 delta y, it's negative since it's moving up. Okay, when I simplify that, 7,97 squared, I'm getting 63,521 minus 19,6 y is equal to 0. Move it that side, 19,6 y, then divide both sides by 19,6. Okay, and then our y is going to be divide by 19,6. I'm getting 3,24 meters here. Okay, so since the maximum height I'm getting is 3,24, and they told us that the maximum height out to the ceiling is 3,5, which means this ball is not gonna reach the ceiling. Okay, so determine by means of equation whether the ball will reach the ceiling. So the answer is nope, the ball ain't gonna reach the ceiling. The ball won't reach the ceiling. It won't reach the ceiling with the target point. Alright, that is 9.5. And then 9.6, lastly, they want us to sketch a velocity time graph. Our first colleagues, this is velocity in meters per second. And then we're saying this is time measured in seconds. So if we look at velocity, remember we said velocity time graphs are basically straight lines. Now at what velocity did the journey start? So it started with 8 because that was the initial velocity. We worked out our final and we got 9,96. Yes, 9697. It's 96. Use a different color. Okay, so this is 9,96. Sorry if my rounding off was poor. And then at what time was that? After how many seconds? It was 0,2 seconds. It was 0,2 seconds. We found it. Let's see. Okay. And then from this point, what happens next? There is a 9,97 when it is doing the bouncing off. So I'm gonna put it 9,97. So which means this is also 7. Okay, when it is bouncing off. So I'm just gonna have this line to that point, and then I'm gonna have, they said it takes 0,01 euro, so this is gonna be 0,21 seconds. So which means my line must pass the middle point, and this must correspond to this 9, something. and then it reaches 0, since it's going to reach the maximum point of the 3,24. So straight line, then straight line. Okay, and then lastly, question number 10. Telling us a boy throws a ball vertically into air from the top of a building, and then the ball strikes the ground after 4,08. The velocity time graph is being drawn for the entire motion. Ignore the effects of friction. Okay, there is our definition question. What is a projectile? You said projectile was any body that was under the influence of acceleration due to gravity. So a body, or we can say an object that is acted upon by only acceleration due to gravity. Acceleration due to gravity. That's the only force. I'm sorry guys, my English, my repetition things. So an object that is acted upon by acceleration due to gravity, strictly acceleration due to gravity, is a projectile. Then what is the acceleration of the ball at 1,02 seconds? Remember, this is a velocity time graph. Okay, and for us to get acceleration is change in velocity over the change in time. You can use those formulas, equations of motion, but there is no need for that. Okay, so if you look at the change in velocity over the change in times, is 9,8 divided by 1,02, getting 9,61 downwards. Okay, that is if I'm to use the graph. Okay, acceleration of the ball at this time. So it's a two-way thing. Since we said an object acted upon by only acceleration due to gravity is a projectile, and this thing is just showing us the velocity time graph, and then they ask us for the acceleration, which means someone can say it's 9,8 meters per second squared downwards. But if we are to use the figures on the graph, change in velocity is going to be 9,8 over the 1,02. How are we getting the 9,8? Remember, we're getting the change, the gradient, change in V over the change in T. So that is what is giving me the 9,6. So it's fine, whichever option you go for, it's correct. So this 9,6 is taking into impact or into effect the values or the effects of frictional force. That's why it is even smaller. And then 10.3, they want us to get the displacement of the ball. So with the displacement, they want the delta y. Okay, we know that delta t is 4,08. Okay, so I'll say delta y is the same as vi delta t plus a half a delta t squared. Our initial velocity was it 0? No, it was 9,8. The starting velocity was 9,8. So that's 9,8, and then the time that we're focusing on is 4,08 plus a half what is happening to the object is thrown into from the top. So I'm gonna take it to be negative. And then the time is still 4,08 squared. So when I punch that into the calculator, 9,8 on that, I'm getting 41,58 negative. So which means the displacement is downwards, 41,58 meters downwards. Then they want you to sketch the position time, and those are the things to look out for. So I'll say y in meters, and then this is the time in seconds. So number one, where did the graph start from, or where did the object? So that is the 0. And what time did it reach 0? What time was the velocity 0? It's after 1,02. So 1,02. The displacement was 0, or the velocity was 0, so that's the maximum displacement. And since it's more like a parabola, twice that is going to be 2,04. Means the graph must also pass through that point. Then we need the time of 4,08, which is twice that. So it's going to be, so this is the maximum height. And displacement is 0 at that time. And this graph continues. So guys, I'm horrible at drawing. Let's do this sort of thinking. Something like that. So this position here, this displacement is what we just calculated in the previous question at a time of 4,08. Our displacement was 41,5 something. 41,58. 41,58. Okay. So 41,58 meters. So guys, for as long as you just show us the t values and the direction and everything, then we shall be good to go. And then other thing is about someone asked now, how about the acceleration time graph? How do they look like? So acceleration is not that hard. I'll just give you, guys, move. Erasing is not working. Okay, so if we have an acceleration time graph, it's just let's okay. So that will be acceleration, and then this will be the time. So it's usually just straight lines. So this is an acceleration time graph, depending on which acceleration you're taking to be positive. So this will be 9,8. So it's just uniform, since it never changes. Sometimes it can be drawn like this, and then like that, depending on how the object is moving. Okay, guys, I think that's enough for the day. What we haven't looked at, probably in the next episode. Let's meet. Hello and welcome to this episode of Physics. Before we go into details, we need to know that electrostatics is just a branch of science. Okay, branch of science that deals with the study of charges or charged particles. Okay, so from this branch of science, we know that like charges are having the same charges that are the same. So positive and positive, or negative and negative, those charges will repel. And then the unlike charges will attract each other. Okay? Like charges will attract each other. So this we need to know. Now, what if we have charges that are at rest? Okay? So if we have charges at rest, then there is a force that will be acting between those two charges. It can either be a force of attraction or a force of repulsion. So for charges at rest, we know that the force between them is what's called the electrostatic force. The electrostatic force. So what does this force do between the charges? So one thing we need to know and remember is that there's a German scientist known by the names of Coulomb that did a thorough study. What really happens when two charges are at rest and what sort of force works between them and what the relationship of force is, the charges and the distance between the charges themselves. So upon his conclusion, he said that this force is directly proportional to the magnitude of the charges, the P.1 times product of magnitude of the charges, not forces, and then it is inversely proportional to the square of the distance of separation. So it's just more like related with the universal law of gravitation for Newton, whereby you look at the force being directly proportional to the masses and inversely proportional to the distance of separation. But in this case, we're focusing on the charges. So if the proportionality symbol was to be eliminated, then K will have to be introduced, whereby F is representing the force, that is the distance of separation. These are the charges, and then K is what we call electrostatic constant. Okay, the constant of electrostatics, which is the same as 9 times 4 to the positive 9. Constant that we need to remember. So for any given two charges at a time, this formula will be used. So this formula brings about what we call Coulomb's law. Coulomb's law of electrostatics. Okay, so what does that law state? We are saying that the magnitude of the electrostatic force is the magnitude of the electrostatic force. Magnitude of the electrostatic force in between 2-point charges. In 2-point charges is directly proportional. Directly proportional. The product, okay, of the charges, or magnitude of the charges, and inversely proportional. Inversely proportional, the square of the distance between them. So the square of the distance between the charges Sometimes we even talk about the centers. Okay, so that is what the formula says. Force is directly proportional to Q1 times Q2 over R squared. So that is Coulomb's law. And we just need to know how we state that. So it's saying it's just similar to the universal where there is a G, and in this case, we just have K. Now, what if we have, let's say, we have an example. We have this as our sphere number 1, I'll call it A. And then this is sphere number 2, I'll name it as a B. And then let's say we have distance from the centers, I'll just say 15 millimeters. Okay? Just for convenience, what if I use this as a 6 MC? And then I can use this as a 12 micro with a C. Okay? And then I need to get the force, the electrostatic force between the two. So both of them are positives, it's fine. I have no problem with that. So we know that our Q1, let me call this Q1, and then let me label this as the Q2. So if that's the case, so this N usually represents what we call nano. And nano is times 10 to the negative 9. So the overall charge is going to be 6 times 2 to the negative 9. And then this symbol mu represents micro in electrostatics times 10 to the negative 6. So the charge here is 12 times 10 to the negative 6 coulombs. This distance needs to be converted to the standard unit in meters. So my force, if I use that formula, is going to be K, which is 9 times 10 to the 9. And then I'm multiplying by 6 times 10 to the negative 9. And then I'm multiplying by 12 times 10 to the negative 6. And then I'm dividing it by the distance. We said it was 15 millimeters. When you're changing or converting millimeters to meters, you usually divide by 1,000. Okay, so you can do that, or you can multiply by 10 to the negative 3, whichever one is easier. That's going to be 0,015. Then I'll square that. Okay, so when I put that into the calculator, times 2 to the negative 6, and then I'm dividing by 0,015 squared. That becomes just 4,13 joules. Okay, so that is the force that is existing between the two. Now, one thing we need to know is that that force is what A is having on B, and then it's the same force that B is having on A. In other words, it's more like Newton's law, Newton number 3. As in opposite and reaction will be equal, but opposite. So the force that A impacts on A impacts on B is the same as that B impacts on A in the opposite direction. So since the charges are the same, which means it's going to be repulsion that takes place. Okay, that is just a simple scenario. Now, what if we have, let's say, 3 bodies? Okay, something like this. And then maybe we're given a distance of 12, maybe you're given a distance of 16 with different charges. I call this A, B, and then C. Let me call this 8 microcoulombs. I'll call this 9 microcoulombs. And then maybe 16 microcoulombs. For this internal problem. Now, if it is 3 charges, what we normally look at is you might be asked for the net electrostatic force. Okay, net electrostatic force of, let's say, A, net electrostatic force on A as a result of B and then C. The net electrostatic force on A as a result of B and then C. Or we can say the net electrostatic force on B as a result of A and C. So in most cases, it's all about combining the two charges. Let me see how we can do this very fast. Okay, so since I'm looking for the net electrostatic force on A due to B and C, step number one, I need to get the force between A and B. Okay, so force A and B, remember we say QA times QB over the RAB squared. So when I do my substitution, that is 9 times 10 to the 9, then times 8, we said micro is 10 to the negative 6. And then this is 9 times 10 to the negative 6. Distance of separation is 12 centimeters, which will be 0.12 squared. And I convert that to meters. So that's a 9 times 8 times 9 times 10. I'm gonna put that negative, okay. And then we're saying this is 0.12 squared. Okay, so this gives me just 45 Newton. Okay. Now that is the force on A as a result of B. So since the charges are opposite, then there's going to be attraction. So it's moving to the left. Okay, then I need to find also the force between A and C. Force between A and C. So the formula, that is QA QC over RAC squared. So 9 times 10 to the 9, that is 10 to the negative 6. Then 10 times 10, that's gonna be to the negative 6. Now the distance we have in 12 and then 16. Okay, so 12 plus 16, that is 28. That's 0.28, but squared. When I put that into my machine, 9 times 8 times 60, okay, then I'm dividing by 0.28 squared. I'm having 16.53. Yeah, Newton. Now, since the charges are the same, this is a positive and then this is also positive, there's going to be repulsion. So that force is going to act to the right. Okay, so that is the right. Now, for me to get the net, I must get the F of AB plus the F of AC. I do the substitution. So if my left is a negative, then I'm going to have negative of 45 Newton plus 16.5. So negative of 45 plus 16.53, ending up with 28.47 Newtons to the left. Okay, so that will be the net electrostatic force if, let's say, I have direct point charges. Then what if the point charges are just at an angle? Okay, an angle of, let's say, 90 degrees. Okay, let's say I have A here. Let's say I have another charge B, and then I have another charge that is C. Let's call the distance here, I don't know, let me call it a 2 meter. I'll call this a 3 meter, just to make it drop it easy. So I'm gonna call this negative 3 nanocoulomb. I'll call this a positive 4 nanocoulomb, and then I'll call this positive 6 nanocoulomb. Okay. Now, if this is the case, and then they ask us determine the net electrostatic force. Okay, net electrostatic force on B, V2A and C. Okay, the net force on B as a result of A and C. Now, this represents what we call the 2D kind of electrostatics, whereby we have the horizontal as well as the vertical dimensions involved. So what we need to find the force that is acting within the vertical as well as the force that is within the horizontal. So this is F vertical, and then this is going to be F horizontal. So the net force for both needs to be found. So I'm going to get the force vertical. Remember we said AQA, QB over R squared. Force on B as a result of A. So if our A was a negative 3, that is 10 to the 9 times, we're saying 3 times 10 to the negative 9 because of the A. And then we are multiplying by 4 times 10 to the negative 9. Distance of separation is 2. I'll just square that. Okay. When I punch that into my calculator, having 9 times 3 times 4. Okay. Over that. This means 7 times 10 to the negative 9. That is newtons. But since the charges are opposite, there's going to be repulsion. So this is going to act downwards. And then let's look at the force horizontal. With the horizontal force, I'll be looking at QB times QC over R squared. 9 times 10 to the 9 times 4 times 10 to the negative 9 times 6 times 10 to the negative 9. I'm dividing it by 2 squared. Okay, so this is going to give me 24 times 10 to the negative 9. Now, since the charges are the same, it's going to be repulsion. So that is to the right. Is it to the left or to the right? Does it matter? It does. To the left and to the right. So that's going to be, remember, let's go back. Let's just go back a bit. Remember, there's going to be attraction. Force is up, it's acting downwards. So this is going to be up. Okay? And then this is going to be to the left. This force is in the, just focusing on B alone. Okay. Then now, if we look at the forces, so it's going to be something like this. Force vertical and then the force horizontal. So this is a 27 times 10 to the negative 9. We're saying this is 24 times 10 to the negative 9. We need to find our resultant. Okay. For us to find the resultant, we use the theorem of Pythagoras. R squared is equal to x squared plus y squared. F horizontal squared plus F vertical squared is equal to our F resultant squared. So 27 times 10 to the negative 9 squared plus 24 times 10 to the negative 9 but squared. So I'm going to find square root so that I have my F resultant. Okay, I need brackets here. Is 10 to the negative 9. And then I'll square it to 10 plus 24 brackets times 10 to the negative 9, but also squared. Okay, I'm having a very small number. It is 1, 2, 3, 4, 5, 6, 7. So 3,612 times 10 to the negative 8 meters. So that is the net electrostatic. Now we also need to find the direction. So with the direction, you need to use the fig where we look at the angle of inclination, which is the arctan of the F vertical over the F horizontal. Okay, shift tan. Our vertical was 27 times 10 to the negative 9 over 24 times 10 to the negative 9. If I put this into my machine, I'm going to have, what am I having? 8,37 or 37 degrees. So that will represent our angle, and then that is our magnitude. All right, so that is if we are being asked to determine the electrostatic force or the net electric force. Then I just want us to look at what we call the electric field. Okay, so electric field is basically a region of space. A region of space where a charged body, sometimes it's a charged body, will experience force. At times we say it's a region of space in which an electric charge experiences a force. So the direction direction of the field at a point in space is the direction in which a positive one charge would move if it was placed. So direction that this force will be operating on that object is basically the direction that a positive one charge would take if it was placed within that region of space. Then we also have what we have electric field point. Okay, maybe let us try that also. Electric field, the point where we say is the force per unit positive charge is placed at the point. The force per unit positive charge placed at that point. We shall go in details when we look at some examples. Then we also need to remember how to represent, let's say, the electric fields. An example, if you're looking at an isolated positively charged sphere. So we know that the field lines must be moved out of the sphere. So normally use arrows in that sort of manner. What if it's negatively charged? Then the field lines should be seen just entering into the sphere. Okay. Now what if we have, let's say, two charged bodies? Remember we said positive and positive, there will be a repulsion. Okay. Now the technique with drawing this, the repulsion, we shall have, and then the field lines must not cross each other. Field lines must never cross path of each other. Must go in. So since they are positive, then the field lines seem just living, seem stored here. Then the magnitude sometimes will also determine how many field lines leave the sphere or enter into the sphere. Sphere with a bigger magnitude will have more field lines. Those with smaller magnitude will see few field lines. And then if it's negative and negative, so still it's going to be repulsion. Yeah. You must touch the sphere. As long as we see the correct pattern and correct format of the field line. So the arrows should be seen entering into the sphere for as long as they are negatively charged. Now this region of space, there will be no force for, because the net force there is 0. So sometimes, let's say if you're talking about the electric field, sometimes you can put a positive Q here or a negative Q there, and then see what will happen. Then what if the charges are opposite? That's when we say it, we shall look at the attraction. A positively charged or negatively charged, we should be able to see field lines that are leaving positive spheres and moving into negatively charged sphere. Leaving something like that. Doesn't matter how it looks like, as long as we see field lines leaving the positive and getting into the negatively charged. Now the formula for electric field, we know must be given as E is equal to F over Q, where E is electric field and then F will be that force at that point, and then Q will be the charge, magnetic charge. Now if let's say we were to focus on the electrostatic force between the electrostatic force between, let's say, the big Q and then the small positive Q. From the Coulomb's law, we know that that will be K times Q, then times a small q over the distance of separation. So if we do the substitution, it's going to be K Q, that Q over R squared times Q. So this is going to cancel that out, and that leads us to this other formula which we normally use, is equal to KQ over R squared. So remember, the force due to the test charge. Due to the test charge. So that we need to remember as well. Then if let's say we want that force, we can just cross multiply that so that we get the times the magnitude of that charge. Then one other thing that I can probably say is that whenever we have, let's say, the net electrostatic force or the net electric field being 0, simply means the charges must be opposite, or the electric field have to be opposite in direction. Okay guys, that's a brief sort of start. Then let me just look at the examination guideline. So with the examination guideline, what is expected of us? Number one, we need to know how to state Coulomb's law, that the magnitude of electrostatic force exerted by one point charge on another is directly proportional to the magnitudes of the charges and inversely proportional to distance between them. To be able to solve problems using this equation, this Coulomb's law, that is for 1D, where the charges are placed in a single line. And then solve problems with a 2D, where we have a 90-degree somewhere, somehow. And then when we look at, let's say, the electric field, we need to be able to describe an electric field as a region of space in which an electric charge experiences force. The direction of the field at a point, the direction at a positive one charge. Okay, we need to be able to draw the field patterns for a single point charge. What if there are 2 point charges? What if they are charged spheres? Then we need to define electric field at a point being the electrostatic force experienced per unit positive charge placed at that point. We saw that. And then we should be able to use this formula, the E is equal to F over Q. Then solve problems with that formula, then calculate the electric field at a point, the number of charges, and so on and so forth. Okay. So this is the examination guideline, and that is what exactly is expected of us. Then we need to look at some worked examples, so exam type questions. This is okay. Question number 1. I can start from question number 1. Next thing. All right. So question number 1 is telling us if we have 2 spheres, M and N. 2 spheres, M and N, on insulated tank M with a charge of negative 4 nanocoulomb that is placed 8 millimeters away from A, is a point that is K, and so on and so forth. Then they are telling us that the net, in capital letters, the net electric field strength is acting east. So we don't know the magnitude of N, we only have E, so the E net, the 2 times 10 to the 5. This distance needs to be converted to meters. Okay. We know that that's negative 4 times 10 to the negative 9 coulombs. All right, let's see. So define the term electric field point. So we say this is the force that is experienced, okay, but per unit positive charge. Per unit positive charge placed at that point. Placed at point or placed at that point. Okay, that is if they ask you to define electric field at a point. That would be it. Then calculate the magnitude and direction of the electric field at P as a result of electric field at P as a result of electric field between P and M. So from our formula, we said E is equal to KQ over R squared. We know that K is 9 times 10 to the 9. Charge, we said it was negative 4, but you don't need the negative sign, just magnitude, that's 4 times 10 to the negative 9. And then the distance of separation is 15 millimeters, convert that to meters. So that's going to be 0.015 squared. Okay, when I put that into the machine, I'm getting 0.15 squared. I'm getting 1,000. Okay, 1,000 Newton per coulomb. Now, which direction is it? So they want the electric field at P, the result of P. So since we're taking this to be a positive one, and then there's a negative, there's going to be attraction. Okay, so the force at P is moving to the east or to the right. To the right. Then they want us to get the magnitude of the charge on N. Magnitude of the charge on N. So since we have the net electric field, I think we can use electric field. Then we can find the electric field at P as a result of N, which will be K, the Q of N over R squared. So that at the end we have our E net being the E as a result of M plus the E as a result of N. Something like that. So since we have the first one, we just need to play around with that. So I'm going to say 9 times 10 to the next equals 9 times the charge of N over the distance between P and N, which is 15 and 45, 0.05 squared. Okay, when I put that into my machine, 0.045 squared, having a very big piece. Just makes sense. 1, 2, 3, 4, 5, 6, 12. It's gonna make sense. It's gonna make sense for that's 12. I don't know. Let me just show you. I'm having 4.44 times 10 to the 12 QN. Okay. So the net that side was 2 times 10 to the 5. So the net is 2 times 10 to the 5. We are saying this is equal to the 160,000 plus 4.44 times 10 to the 12 QL. Yeah. Okay. Now someone asked, why are we adding them? Now, since the net force or the net electric field is acting eastwards, which means all of the charges, all the electric fields must be in the direction. So we are moving this one in the east. So then I'll move this to that side. So 2 times 10 to the 5. Then I will subtract my 160 tau. My 160 tau, I'm getting 40 tau. Is equal to 4.44 times 10 to the positive 12 Qn. Divide by 4.44 times 10 to the 12. Divide by 4.44 times 10 to the 12. This cancels that. Remember, we said we're going to subtract when you transpose that. So Qn going to be 4.44 times 10 to 12. Okay, I'm having 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm having 9.01. Times 10 to the negative 9 coulombs. Or someone can say that is 9 nanocoulomb. Now with the charge, it will be positive. Then 1.4 is charge on the sphere, positive or negative. Answer that. Positive And then they want us to sketch the net electric field perpendicular to M and N. Now we said it's positive, and then the original, this one, was negative. So that is a positively charged and negatively charged attraction. Unlike charges attract each other. So, unlike charges must repel. Whereas the like charges, unlike charges must attract. Whereas the like charges do the repulsion. Then calculate the magnitude of the electric force that an electron will experience when placed. Calculate the magnitude of the electric force. Guys, how do we go about that? Okay. So we know that E is equal to F over Q. E is equal to F over Q. And what did we say? We say that so I'm still on the same question. Yes. Okay, calculate the magnitude of electric force an electron. Okay, since we're focusing on an electron, would experience when placed at that point. So since we have the electric field, the net electric field, we just need to multiply. So Q times E, we know the charge of an electron is going to be the one of times 10 to the negative, as I need the electron charge with my formula. Okay, so I'll get my net, which was 2 times 10 to the 5. And then I'm just going to multiply it by the charge of electrons, which is 1,6. And just confirm. So saying electron charge. Okay. So it's 1,6 times 10 to the negative 9. Okay, so when I multiply, it's true, you can put the negative sign, there's no problem. When I substitute that, 2 times 1.2, having 3,2 times 10 to the negative 8, it will be newtons. Guys, that will be it with that first question. Then my question number 2, they're telling me that the diagram below shows two spheres A having that much charge and sphere B insulated. Distance between them is that, and they want us to draw the field pattern. So a negative and a positive. You know what to do? Attraction. Attraction. So we just so field lines should be seen leaving. Field lines should be seen entering. What's wrong with me? This one lies. Okay, say, say, like that. All right, then 2.2, calculate the magnitude and direction of the force exerted by B on sphere A. Okay, so from electrostatic force, we said F is A, P.1, P.2 over R squared. That's 9 times 10 to the 9 The charge on A is 4,5. 10 to the negative 5. 4,5 times 10 to the negative 5. That is 9,5 times 10 to the negative 5. Distance of separation is 0,35. Okay, and then I'll square that. Putting this into the machine, I'm gonna have 9 times 10 to the 9. That's 4,5 for the multiplication. Okay, then we multiply by the 9,5 times 7. Okay, that much over 0,35 squared. Having 314,08. But since we're focusing on B on A, then the direction is going to be the right. B on A, the right. They give an attraction. Then calculate the strength of the electric field at P, the result of the strength at P. So we're gonna assume that instead of having the charge of P, just have a positive, because they're asking for the strength at P as a result of P. So that will be E is equal to KQ over R squared. 9 times 10 to the 9. And then we need the charge of A. So it was 4,5 times 10 to the negative 5 over the distance is still the same. Okay, so that's going to be 9 times 10 to the 9. Multiplying it by 4,5 times 10 to the negative 5 over 0,35 squared. Very short number. 3, 1, 2, 3, 4, 5. So I'll say 3,31 times 10 plus. Since electric field is Newton per Coulomb, also going back to the right. Okay, question number 3. Two identical spheres again, AP insulated and stands are placed the centers having 10 meters apart. Shown the sketch. So the charge on A is negative 10 nanocoulomb. And then B carries some charge that we don't know. Then the net electric field that. So this is more like this question. Define electric field at a point. Remember we said electric field at a point is the force per unit positive charge that is placed at a particular point. I'm not going to write that. Then they want us to draw the field pattern A and B due to charges A and B. Now, since the net force is acting to the left, but it will be at this point, acting to the left. What do you think? What do you suggest? What do you think? So simply means that since it's negative charge and the net force is the left, so it means the force between this and this is also left. So it means it's more like an attraction force. Okay? That means I'm going to have a positive, then I have a negative. What that means? Attraction. Okay? That is attraction. And then they want us to get the magnitude of sphere B. So in that case, I'm going to use electric field. Okay, so I need to get the electric field between P and between A and P, and then the electric field between B and P. Then I use the net. Okay, so electric field of PA will be KQ over R squared. That's 9 times 10 to the 9. The Q we said was negative 10. Okay, I'm dividing by 2 centimeters, 0.0 squared. So put that into the machine. I'm having 9 times 10 over 0.02 squared. Having 337,500 Newton per coulomb. Then I'm having the E to be, which is Q over R squared. That's 9 times 3 to the 9. That is the QB over 0.08 squared. Simplify that. Having 0.08 squared. Sure. Very big number. Scale. I'll count 1, 2, 3, 4, 5, 6, 7, 8, 11, 12. 1,4,1 times 10 to the 12. I'll call that cubic. Then now look at our inlet being the same as the ETA plus the EB. Now the net that they gave us was 3,943. 3,943 times 10 to the 5 is equal to 337,500 plus the 1,41 times 10 to the 12, but QB. So I need to take this aside using subtraction. Okay. So when I do that, I have 3,945 times 10 to the 5 minus 337,500, which gives me 5,000. With 1,41 10 to the 12 cubing. Then divide both sides by 1,41 times 10 to the 12. That cancels that. Let's see 1,41 times 10 to the 12. Sorry for rounding off in advance, but it will make just little difference. So the charge on B, I'm having 1, 2, 3, 4, 5, 7, 8. Okay, 4,04 times 10 to the negative 8. Guys, that's that. Then they're telling us that sphere B is removed. State whether the electric field at P due to the charge A will increase, decrease, or remain the same. So, since B is removed, it's having an effect on the net electric field at P. If it's removed, automatically it's going to decrease. Okay, then question number 4. Okay. They are telling us that 300 microcoulomb charges ABC, so it's space 0 centimeters on a straight line in a vacuum. Distances are 3 that and so on. Define electric field at a point. We said the region. Is this a region of space? No. What? By unit positive charge that is placed at that point. Point 1 answered. Then they want us to draw electric field lines associated with A only, since it's a positively charged sphere or object. Then the field lines should be seen moving out. So direction Let's sort straight lines, getting lines. 4.3, they want the magnitude of the electric field strength at position where B is and B2A on. So the electric field at this point B as a result of A. So if we place a positive 1 there, we shall ignore the charge of B. So that's going to be E being Kq over R squared. 9 times 10 to the 9, that's 100 times 10 to the negative. Distance 33 centimeters. 0.03 squared. So that's gonna be 9 times that over 0.03 squared. So that's gonna be 1, 2, 3, 4, 5, 6. That's some 39. So 1 times 10 to the 9. It's 10 per coulomb. Or you can write the whole billion there. Fine. Then Coulomb's law in what? Remember we said the electrostatic force. The electrostatic force, whether it's attraction or repulsion, between two charges. Between two charges is directly proportional. Directly proportional. The product of the charges, the product of the magnitude of the charges, and inversely proportional. Inversely proportional to the square of the distance between them. Distance between them. Okay, remember I said that it's if that is true, then they want us to get the net electrostatic force experienced by point charge P as a result of A. So they want the force because of B and because of A. Okay, so I'll just kind of draw that for my convenience. What is this? Here's the 3 and the 4. Okay, so I need to get the force. I need to calculate the force in A and C. Okay, just for convenience. HA C over R squared. So 9 times 10 to the 9. That is 100 times 10 to the negative 6. 100 times 10 to the negative 6. Distance of separation is 3 and 3. It's 6. So that's going to be 0.06. That's squared. Okay, put that into my machine. It's 10 to the 9. Multiplied by 100 times 100 like that over 0.0. Giving me 25,000. Okay, that is nothing. Since the two are positive charge, then let's do that. Since the 20,000. Then I look at the force in B and Q over R squared. It's going to be more or less the same thing. So 100 times 10 to the negative 100 times 10 to the negative 6 over 0.0. That is that is, so that is 100,000. Okay, now when you look at this again, it's 2 to the right. Since it's 1,000, right? Then this is going to be less. Put it up in your right. Now, since the first force and the second force are in the same direction, the net just marginally distributed. 25,000 plus 10, no, 100,000. So that must give us with 100 and 105,000. Yeah, it must. Okay. Then now question number 5 is what I want. Good. Okay, so we have a negative 3 nanocoulomb. P.1 plus 10 centimeters away from this diagram below. Draw the electric pattern. So positive and negative. Doesn't matter which one you call positive. It comes back. Yeah. So in this that is that. Fine guys, you can do whatever you want to do. As long as you see the two lines leaving from the positive and from the negative. Okay, so now next we have 5.5. If there is a negative inside, then they want us to draw a force diagram showing the electric forces exerted on O by Q1. So since positive and the positive is going to be repulsed. No. The negative, the positive, so attraction. This will move in the direction. This will move in this direction. Then since it's a positive and negative, the attraction. Okay, now since they want the force diagram on P2 alone, it's going to be then calculate the net force on P2 as a result of that. So since we drew our force diagram into the horizontal and the vertical, I need to find those forces. If I can find the net result on this. So force horizontal Q1 over R squared. Okay. So we get 3, so it's going to be just 9 times 10 to the 9 times 3 times 10 to the negative 9, then times 4 10 to the negative. Distance is 10 centimeters, which is my distance, which is 0.1 second. Okay. Then I just need to put that into my machine. 9 times 3, and then I'm dividing it by 0.1. 4, 8, 9, 6, 8, 1, 2, 3, 4, 8, 9, then the F vertical, 3 over R squared, 9 times the negative positive 9. That's it. 2 times 10 to the negative 9. This time, 35. 0, 0, 5. Okay, when I put that into the math, over 0.05 squared over 2.16 times 10 to the negative 5 meters. Okay. But since the vertical and horizontal, for us to find the net force or the resultant, we said we use the vertical squared plus the horizontal squared. So I do that, square up brackets, then 8.1 is the negative plus 2.1, 10 the negative 5, but squared. Okay, I'm having 2.31. Okay, that is 2.31 times 10, 1, 2, 3, 4, 5, 5. So with the vertical, I'm getting this. With the horizontal, I'm getting this value. That's the calculator. Then we need to get the direction. We need to get the direction. So theta must be the fixed time. The vertical over the horizontal. We do the substitute. Will be 2.1 times 10 to the negative 5 over 8.1 and 10 to the negative 6. Here when you put that, gets 2.3. This is the magnitude of force. Then that has to be. Then 5.4, we have an unknown charge R. It is placed 3 meters away from unknown charge. As shown, they are telling us that the charge on R is what we need. Okay? If the net electric field affects. So remember what we said, for net electric field to be 0, then the electric field from different angles, let's say the electric field this side, then the electric field this side, must working in opposite direction. Can be to the left, can be to the right, as long as the direction is opposite. So we need to get electric field at P, sorry, at X as a result of P. So it takes Q over R squared, 9 times 10 to the 9. The charge is 8 times 10 to the negative 9. 10 to 6 centimeters, convert that to meters. And then when I put this into my calculator, punch that in the calculator, having 180 tau. Okay, 180 tau meters per coulomb. Then when I look at this side, the E of X, R of X, it's gonna be K over, I'll call this R over R. So 9 times 10 to the 9, that's R divided by 0.01. So when I try my luck with that, because I want this right hand, so 1, I'm having 9 times 10 to the that's QR. Then remember what we said, for us to have a net of 0, must have the electric strength actually in opposite direction. If I do that, it means if I take it to happen in the negative direction. Okay, so that says 0 is equal to my 180 tau plus, let's say, negative 9. So move the 180 to the, or you can transpose that, so that I have 9 times 10 to the plus, is equal to 180 tau. Divide by 9 times 10 to the third. Divide by 9. And that cancels that. And then my QR divide by 9. So I'm having 2 negative. So that can also change to nano. Suppose taking that right. Alright, so that would be that. Question number almost. Question number 6, they're telling us that two identical spheres, P1 P.1 inflating stones are placed at same charge 2 millimeters apart. When P1 is brought into contact and then moved back to original position, gain the negative 12,15, sorry, 12,5. And the charge on each sphere is this. So, guys, one thing we need to remember is that when spheres are brought into contact, there is going to be equal distribution of charges. Look at the separation. The magnitude of charges has to be the same. So number one, they want us to draw the electric field testing around both spheres after they are touched and separated. So since both things negative, so that we obtain that the contact, which means it's just gonna be a case of 1,000. Just remember the food lines have to be the same. So this we have to be centered. See, talking of a negative charge. Okay, that is that. And then 6.2, they're telling us that state the law of conservation of charge. So there are quite a number of ways you can tell us the net charge. The net charge of an isolated or in an isolated the net charge is constant or is constant. So someone can talk about that charges can neither be created, charges can neither be created nor destroyed, nor destroyed. They are just transferred. That's what happens. Transferred from one body to another. Alright, so any one of the two will work for us. They are telling us that an electron of negative, an electron, let's exactly between P1 and P2, will the electron move to the left, to the right, or stay in the same position? Now they're telling us that the electron is flat. And remember we said when there's a repulsion, this area or this region of space will experience what here. Nothing is going to happen to this electron. The forces will be equal but opposite. So we're going to say it's the same position. Okay, it may be 7.4, 7.4, 7.4. Or calculate the magnitude of the electric field due to the charge on sphere 0.10 millimeters to the right, 10 millimeters to the right. So if we have a point of 10 millimeters, what will be? So E, remember we said K2 over R squared. So K is 9 times 10 to the 9. Remember they told us K is 7,5. Plus 7,5 times 10 to the negative 9 over the distance. They told us 10 millimeters. When you convert 10 millimeters to meters, it's going to be 0,01 squared. Alright, so when I do my magic, having 67, 5,000 coulomb. Then they are telling us in 6.5 that the questions of all relate to the original charges. 1 and 4 were brought in quantity given in bold capital letters. What is the magnitude and sign of P1 and P4? So when we look at it, P1, P1, negative 7,5 coulomb. So it's a negative 7,5 plus it gained how much? It gained negative 12.5. What does this give us? Negative 7.5, that is 20. No, okay. So it is negative 7.5, gains that 1. We can write it the other way around. Okay. Same with your integer. So it has that much. Then for us to get what is left on this, we can do more or less the same. Where we look at negative 7.5 minus 4.5. Gaining is a plus. C is a minus. When you do that, you get a positive. That's alternative number 1. Other alternative is by looking at P1. Yes. Divided by 2 must give us 5. If you have your Q1 known, it will be just transposing that. So that is negative 25 plus. When you multiply both sides by 2, you're gonna get negative 2. This is 20, not 25. So when I move that upside, my is just gonna be 45. Then 6.5.2, they want the force between Q1 and Q2 before they start. So the force should say Q1, Q2 over R squared, 9 times 10 to the 9, the Q1 is 20. Is 5. Dividing by the distance, so that is 6 millimeters. So 6 millimeters is 0.3 squared. So when I put that in, then to be dividing by 0.03 squared, having 0.01. So that is the force that I'm having.
suppose that P.1 is just since the charges are opposite, we tell us to do. So P2 equals to 5. We are looking at this one. We understand our correct. It would have P1. And then it's electric field pattern. Balance before the test. So remember, before the test, we're having a positive and negative. And then after the test, there was a pause. So
now with multiple choices, we can use elimination format before we can get to the correct option. Okay. So we have various options that have been provided as possible answers, the following. Each question has only one correct answer, and we need to choose that correct answer and then write that in our answer book. Okay, so I'll start with question number 1. So which one of the following quantities is the tendency of an object to resist a change to its state of motion? Is it inertia? Is it impulse? Is it momentum or acceleration? So we know that acceleration cannot apply that. Okay, because acceleration is the rate in change of velocity. Momentum is the product of mass and velocity. Impulse, it's something else. So the correct option would be A, which is inertia, the tendency of an object to resist motion from Newton's first law. Okay, then 1.2, we have a ball that is dropped from rest at a height above the concrete floor. Okay, and then they're telling us that this ball strikes the floor and bounces vertically up and down on the same spot on the floor. So the velocity time graph is being drawn for us for the bouncing ball, with the points P, Q, R, S representing the different times during the motion. So this point here will represent the time when the ball was just at that height. And when it is dropped, probably it's moving, and then reaches the floor. Okay, and then it starts to move up. And then at this point, it's probably reaching maximum, because you can see that the velocity is 0 at Q. So probably that's the point where the ball reaches its maximum and then drops down, and then at point R, and so on and so forth. So what are we going to say? At which time does the ball reach its maximum height? After the first upward. Okay, so when you talk of first upward, remember here it's coming down. And then between this point and this point, the ball is going up. And then as it goes up, the velocity decreases. We have in that point where the velocity is 0. So point Q will be our answer, and that is option B. And then 1.3, we have two blocks, P and Q of masses M1 and M2, respectively, that are held at rest on a frictionless horizontal floor. Both of them are being compressed with a spring, as shown. So blocks are released, and then the spring decides to drop to the floor. Block Q, this one moves to the right with velocity v. What will happen to P? So in normal cases, under the conservation of momentum or impact, we know that the momentum or the impact that Q will have on P would be the same, but just in the opposite direction. So in this case, they are asking us to determine the momentum of P. Okay. Now, since they were held together with a spring, and then the spring was removed, so we expect the reaction to be the same, but just in the opposite direction. So if Q is having m times v as its momentum, so it's m2 times v, then the same should be applicable to P, but in the opposite direction. So if this is to the right, then this is going to be to the left. So we expect to have m2v, but to the left. Is there an option like that? M2v to the left. That is option D. Okay, then 1.4, they're telling us that the magnitude of the gravitational force that spheres X and Y exert on each other is F. So from Newton's law of gravitational force, if that is X and then that is Y, if these two are separated with distance R, what happens? So we know that the force is directly proportional to the product of the masses, and then inversely proportional to the square of the distances apart. Now the mass of X is doubled. So instead of us having M, we're going to have twice M1. And then you're telling us the mass of Y and the distance just remain the same. Okay, so which means our new F is going to be G, and then twice M1, and then M2 over R squared. We can move this 2 in front so that it is a G, M1, M2 over R squared. Okay, so we're seeing that this is representing the F, and it is the same thing that is there. So which means our final result must be 2F, or twice the original force. So remember, the force that X exerts on Y should be the same force that Y exerts on X, but in the opposite direction. Okay. So they're asking us which one of the following combination is correct for the magnitude of the forces that the spheres exert on each other. So remember I said they have to be the same, but currently our force has to be twice the original F. So this and that, which is option D. Then 1.5, hot air balloon, vertically downwards. Is moving vertically downwards at a constant speed. This is in capital letters, okay? So something is happening. So constant speed, so velocity is the same. Assume that the mass of the hot air balloon remains constant. So mass is the same, speed is the same. Okay, which of the following physical quantities associated with the hot air balloon will change during the motion? So is it the weight? They told us the mass must stay the same, so weight cannot. Okay, is it the momentum? Momentum, remember, is mass times velocity. So if the mass is the same and the velocity is the same, this must also be the same. So momentum is out. Is it kinetic energy? We know that kinetic energy is a half mv squared. So if mass and the velocity are the same, which means kinetic energy is also the same. What about potential energy? We know that potential energy is mass, gravitational force, and the height. The mass, gravitation, or acceleration due to gravity, and then the height. So the height will keep on changing. There's no way height is going to stay the same. So it's the potential energy that is going to change during the motion. All right, 1.6, a learner that is standing by the roadside records the frequency of sound waves that were produced by a siren of an ambulance, okay? So the ambulance is moving at a constant velocity along the road, and then they drew the graph for us. So the y-axis is representing the detected frequency or the frequency of the listener, and then as time passes. So what we can see is that the graph is low, which means the frequency starts by being low, and then all of a sudden the frequency increases. What does this tell us? So if the frequency of the listener overall increases, which means the ambulance is approaching the learner, or it's moving towards the learner. this approaches the learner. Okay, that is the kind of conclusion you can have. So probably it was moving from a distance and then it comes towards the learner. Okay, so which of the following statements concerning the motion of the ambulance is correct? So the ambulance approaches the learner and then passes the learner. You see, if it's approaching then passes, then we will have another extension where the frequency drops again. Okay, so this is a 1-2 approach. It's either approaching or leaving. Okay, so because of this last statement, I'm nullifying A for now. Okay, then let's look at the second option. It moves away from the learner and then turns and approaches the learner. Moves away. So when it's moving away, the frequency is low. And then when it approaches the learner, the frequency increases. There's some truth in that statement. Let's see option C. It approaches the learner and then turns and moves away. No, that is not correct, because if it was turning away, then the second part of the graph would be below, or would be lower than the first one. And then moves away from the learner and then stops. This is out. So I'll take option B because it has some bit of truth in it. It moves away and then turns and approaches the learner. So as it's moving away, the frequency is below or less. And then as it's approaching, the frequency that will be observed by the learner will be high. So option B is the correct answer there. And then 1.7, we have two identical spheres, X and Y, that are carrying +2 and then -6 Q respectively. Sphere X experiences a force F to the right, X to the right, when the distance is that, all right. Then the spheres are brought into contact and then return to the original positions. Which one of the following represents the magnitude of electrostatic force that X experiences now? So just like Newton's law of universal gravitation, it's just the same as the electrostatic force. Okay, what differs is just that this has a constant of K, not G. Okay, and then in this case, we're going to be talking about charges Q1, Q2 over R squared. Okay, I'm not going to simplify everything. I just need to look at what's going on. So I'll maintain the K, I'll maintain the R squared since those are constants. So this will be a 2 times a 6, okay, which will give me 12K over R squared. So currently, before the spheres touch each other, this is the force that each sphere will exert on each other, okay? Then when spheres are brought into contact with each other, okay, so a +2 and then a -6, the charges are going to combine, and then the resultant charge on each sphere will be divided, or will be a result of division between the sum of the charges. So this would be 4 plus -6, that's going to be -4 divided by 2, which means after the separation, each sphere must be a -2 charge. If the distance is still the same, then we try to look for the force, that is K, Q1, and then Q2. So that's over R squared. So that's a K. That is a K. I'm maintaining the K. Q1 is a 2, my Q2 is a 2 over R squared. So that's going to be 4K over R squared. Remember, this was 12K over R squared. This is 4K over R squared. So this is the new force. This is the original. So which one of the following represents the magnitude of the electrostatic force right now? So when you divide 12 by 4, or when you divide this force by this force, it's going to be 3 times smaller. Okay, so if it is 3 times smaller, which means it's 1/3 of the original force. Get this new force, divide by the original force. So the option I'll go with is B. That is 1.7. Okay. Then 1.8 in a circuit diagram below, R1, R2, and R3 are identical resistors. So identical simply means they have the same value and the battery has negligible internal resistance. Okay. What happens to the power that is dissipated by R1? No, they're telling us the power dissipated by R1 is P. Okay. So if the power dissipated by R1 is P, the question is asking us, what happens to the power that is dissipated by R2? Now, if I were to assume that, okay, so I'm saying if I'm to assume, let's say, since they're identical, I can call this 2 ohms, as well as 2 ohms. I can just come up with I can set 10 volts as my voltage there. Just I want to bring about the picture of everything. So the effective resistance within this parallel combination, remember we are 2 resistors, so product over the sum, that's going to be 4/4, which is 1 ohm. Okay, that is for the parallel combination. Now, since this parallel combination is going to be in series with R1, I'll plus the 2 ohms, which means my effective resistance is going to be 3 ohms. Then if I want to find the current, because I need the current that is passing through the current is going to be given as V over R. Okay, so if I have 10/3, which will be the same as 3, something. Okay, let me just leave it as 10/3 ohms. Okay. Then I know that from the formulas of power is given as IV. Okay. Or I can use the combination that has what? Because now this 10/3 is the current that is flowing through this entire circuit. And it's the same current that is going to pass through the R1. So if I were to look at, do I need the voltage? I can use I squared R. Okay. Let's say I'm looking for the power of R1. So it's going to be 10/3 squared times the 2. Just 10/3 squared. That's going to be 100/9. Okay, and then times 2. That's going to give me, I need a fraction. It's going to give me 200/9 watts. Okay, that's the power in this. Then what will be the voltage of R1? Voltage of R1 is going to be 10/3 times the 2, which is going to be 20/3 volts. But if my original was a 10, then I'll have 10 minus 20/3. Okay, 10 minus 20/3, which gives me a 10/3 volts as well. Okay, so we're saying that this voltage is going to be the voltage of the parallel combination. Okay, now we have the voltage, we can get the current that is passing through there, or we can directly look for a formula that has voltage, because we know the voltage across R3 is going to be the same voltage across R2. Okay, the power formula that combines voltage and resistance, is P is equal to V squared over R. Okay, so when I get my voltage, which is 10/3 squared, and then I divide it with my R, which is a 2. Let's see. That's going to be 100/9 and then I'm dividing it by 2. What do I get? I end up with a 50/9. So this is the power in 2. This is the power in 1. So now the question is asking, which one of the following represents the power that is dissipated by R2? Okay, so the question is, how does this, remember, for R1 is the same as P, this P. So how does this relate with this? Okay, how does this 200 over that relate with that? So what I'm gonna do, I'm gonna say if I have 50/9, then I divide it by 200 still over 9. I'm getting 1/4. Okay. So I'm saying 50/9 divided by 200/9. Then I'm getting 1/4. So which means this R2 is a quarter of P. And the correct option is A. So I just had to come up with numbers just to create an idea of what's going on there. Then 1.8, they're telling us that the following is a simplified drawing that represents a DC motor. Okay, so one thing we know about DC motors or AC motors is that they use what we call the Fleming's left-hand rule. Okay, that's the basic thing we need to know. They are asking us, okay, that the diagrams below indicate some changes that we made to the motor. So we can see the north and the south being switched around. And then you can see that the terminals are also being switched around in the second option. And so on and so forth. Okay, what is the question asking for? Which of the changes to the motor above will change the original? Okay, what changes are going to change the original direction of rotation? Okay, so what we need to know is from the original, this is the positive and this is the negative, which means current is going to flow in this sort of direction. Okay, because current flows from the positive towards the negative terminal. We know that the field is from the north to the south pole. Okay. Then if we apply our Fleming's left-hand rule, okay, what is happening? All I can see is that this structure of ours, or this plate of ours, or coil, is going to rotate in which direction? Which direction is this? Okay, this is going to be downwards. So which means it's rotating in the anti-clockwise direction. Okay, if I use my Fleming's, I'm going to end up having something like that. Okay, if this is my force, so this is my thrust of the force, this is the field, and then this is the current. I'm just looking at this part alone. The field, current, then it's going to go down. Okay, once it goes down, then the rotation is going to be anti-clockwise. Okay, so the question is asking us what change, or from the given drawings, which one is not going to be anti-clockwise? In other words, which one is going to be clockwise? So changes were made. If I'm to get the question correct, which of the changes will change the original direction? So we want something that's going to create a clockwise direction, not anti-clockwise. Okay, so let's see from diagram number 1. So current is moving in the same direction, but what has been changed is the polarity of the magnets, that now the field will be moving in that sort of direction. So if I look at, I don't know, I will still just look at this side alone. Okay. Okay, so from our Fleming's left-hand rule again, when I try to twist this kind of thing, okay, so I'm looking at this green line. Does that make sense? Green line, green line. Yes, this is going to be moving upwards. Okay, because current is moving that side. So if I'm to draw more or less the same thing, where this is at 90 to each other, it's going to be moving upwards. It's moving upwards. This is a clockwise direction. Okay. Let's try to look at option number 2. Option number 2, the field is to the right, current is moving in that sort of direction. Okay. With my Fleming's left-hand rule, let me just look at just this portion. Just this portion, okay? Current is moving in this direction, and so this one is moving upwards also. So which means it's a clockwise. Okay? Let's look at option number 3. If I focus, current is moving in this sort of direction. If I look at my field, and focus on this, that current is moving in this sort of direction. Okay. Current, where are you? See your field is moving that way. So it means it's going to move downwards. This one moves downwards, which is the anti-clockwise. Okay, anti-clockwise. So, which of the following changes will change the original? So, number 3 is original. Okay, so 1 and 2 are the changes that are going to change the original direction, since both of them are giving us the clockwise. So 1 and 2, which is option A. Then 1.1.0, 1.10. An atom has a ground state energy, that is X. When the atom moves to a higher energy state, which is Y, there's a line spectrum that is observed. Okay. So one thing we know is that when atoms move, so we say if the energy at ground is X and the energy at the higher state level is Y. When that happens, there's an absorption that will take place when atoms move from low energy levels to higher energy levels. That is absorption that is taking place. When they move from high energy levels to low energy levels, that's when they emit their energy. Or that's when they emit light in the form of that. Okay, so our options have to be C and D. Okay, since there is absorptions moving from a low energy level to a high energy level. Then the change in the energy, since this energy is higher than this one, so the change is always highest minus lowest. So Y minus X, and then that's the absorption. So I'll go with option D. Okay. If there's any difference, please let us know under the comment section. Okay. Then question number 2. Question number 2. They're telling us that a block A of mass M is connected. A block of mass M is connected to block B of mass 7.5 kilograms by a light inextensible rope passing over frictionless fluid, as we can see. Okay, we have a height of 1.5 meters above the ground, and so on and so forth. All right, let me just try to decrease this so that we can see the entire question. All right, I think that's much more better. Okay, this is our height, that's all that. All right. So while block B is released, okay, remember, initially it's been held at this point without moving. When B is released, it moves vertically downwards and strikes the ground with 3.41 seconds, or meters per second. Okay, if we are ignoring friction, can we show by means of calculation that the magnitude of the acceleration of block B is 3.88 meters per second squared, while the block was moving vertically downwards? So what I can see is that if our focus is on block B alone, then we shall assume something like a free fall in that case, where the motion is entirely under the influence of acceleration due to gravity. It's more like a vertical projectile kind of scenario, okay? And if I'm to look at it in that form, then I'll have to apply those equations of motion, okay? In this case, I could say that, what do I have? I have my displacement. So change in y is 1.5. What else do I have? I have my final velocity, which is 3.41 meters per second. What is our initial velocity? It's a 0. Okay. Is there anything else we need? Is there anything else we have? We want the acceleration. Okay. Projectile. Okay, that's fine. So I can say that if I have v squared, vf squared is equal to v I squared plus 2a delta y. Okay. So I know my final, my initial, I know. Acceleration is what I want. I have my displacement. Okay, so this is going to be 3.41 squared is equal to 0 plus, this is 2 times 1.58. Okay, when I have 3.41 squared, that's going to give me 11.6281 is equal to 3a. Then I'll divide both sides by 3. And then what is my a? My a is 3.876. When I round it off, I'll get 3.88 meters per second squared. Okay, so that is how I would go about answering 2.1. Then when I look at question 2.2, okay, 2.2, they're asking me to draw a labeled free body diagram showing all the forces that are acting on B. So when you look at B, there's just weight that is acting downwards, and then there's tension force that is within the rod. Okay, so my free body would be just tension, and then we're saying this is the weight. That is just enough. And then 2.3, can we state Newton's law, Newton's second law of motion in words? Okay, so there are different formats, there are different scenarios to this law, but they are just some keywords that we normally want. Okay, and so one can say that the net force that is acting on a body, an object, is directly proportional. Okay, the net force acting on an object is directly proportional to the acceleration. Net force is directly proportional to the acceleration and inversely proportional. Inversely proportional to the mass of the object. The mass of the object. The net force acting on an object is directly proportional to the acceleration and inversely proportional to the mass of an object. Okay. And one thing we know is that this acceleration will always be in the direction of the force, directly proportional to the acceleration and inversely proportional to the mass